I want to appreciate you guys coming over here and beating the traffic. Hello, everyone. Thank you so much for being here. My name is Linda. I'm the project manager of this Agentic AI Summit. Thank you so much for coming here, joining us on a Saturday, out of your busy weekend. We understand, I want to appreciate you guys coming over here and beating the traffic. We understand Berkeley is a little bit far out, compared to the other areas of the Bay Area. So thank you so much for coming here. We're starting the program right now. And I want to do a quick introduction of Berkeley RDI and then the summit and then the program for today for the Frontier stage. And then the session chair, Xiangding, will introduce the speakers for the first session, Agent Architecture and the Systems. And then we'll get started with all the exciting presentations and talks. Thank you so much. So today at the Frontier stage, we have a lot of industry leaders, primarily product and research leads from the top-tier AI companies in the space. And we have 5 sessions: agent architecture and systems. We have AI for science. We have agent applications. We have AI security and alignment. And then one second, I think I forgot the fourth session, the foundations of agents. And in between those sessions, we also have very, very interesting lightning talks. And then we also have poster sessions, which will be lined up around the edges of this tent. And this afternoon, around 1:45 p.m. or 2 p.m., we'll do the award ceremony of Agent X and the LM Agents MOOC Hackathon. The winning teams will do the award ceremony, and then they will also do some presentations, talks during that session as well. So it's going to be a very packed, very exciting program for the whole day at this stage. Thank you so much for being here again. Looking forward to the exciting discussion and looking forward to navigating, marching into the future of agentic AI. So without further ado, let me introduce the session chair, Xiangding, who will introduce the speakers of the first session, Agent Architecture and Systems.
Okay. Thanks for Linda's introduction. Okay, so the first speaker is Ranjan Sinha, right? So Ranjan Sinha is IBM fellow and CTO, IBM Research AI, and he will introduce the talk about natural language interaction protocol or universal application level protocol for the age of general AI. So let's welcome Ranjan Sinha. Yeah.
Okay, good morning. Great to be here. So we have trained AI models using the entire internet to speak in fluent natural language. But when it comes to AI agents talking to each other, we are still stuck with rigid and brittle approaches because they are based on predefined schemas. So what if agents could communicate with each other just the way that we do using plain language? Just like HTTP unified the web, we are on the verge of a new standard for agents that is based on natural language itself. So the original work on the natural language interaction protocol, which I'll refer to as NLIP, it started in March of 2024. The ECMA Technical Committee was formed in December of 2024, and ECMA is the body that standardizes application-level protocols. So I'm representing the ECMA Technical Committee and the NLIP collaborators in this session. So researchers from industry and academia are helping to design a universal and open protocol that is based on natural language. Now, today's systems use several application-level protocols and APIs with rigid schemas, and it causes challenges in integration, interoperability, and version management. So the question is, could we apply the generative AI technologies to design a more smarter and adaptable protocol? So if you look on the bottom left, that's the traditional protocols, where you have agent 1 communicating with agent 2, and you have the message structures A and B. They all need to be the same, and as well as the one that is over the wire, that's P, right? Because predefined schemas, they all need to be the same. In contrast, the NLIP, agent 1 message structure doesn't have to be the same as the message structure for agent 2, that is B. And you can use generative AI technologies to translate between the structures. The only important thing is that the meaning itself should remain the same. So that's I would say, the essence of the idea. So NLIP provides a simple, open, standard, and common protocol for applications, agents, and services to communicate with each other and to us. It does assume generative AI capability at the endpoints. It follows a multi-turn request and response paradigm to ensure that the meaning is refined and well understood. And some of the obvious requirements for the protocol is got to be secure. It should enable various safeguards such as data privacy, data usage policies. It should be implementable across various underlying transports and API styles. It should support multimedia content, should be efficient, should be implemented in various languages, and should be standardized in an open forum. So NLIP uses generative AI for structure-independent communications. And as I just touched upon that in the first slide, all the three structures must be the same in a traditional protocol you see on the top right. And that forces a rigid API. There could be version upgrade issues. It limits extensibility. And there is tight coupling between the systems. NLIP allows structure independence. And you'd find that the structure for these messages are different or can be different. And we use generative AI because it's really good at passing unstructured text to structured text. And it has really worked in practice. We have done quite a few POCs and reference use cases, and it's panning out pretty well. And of course, the more we do, the better we understand it, and we can update the specifications accordingly. So the scope for NLIP is currently it's communication between two AI agents within and across organizations, or between humans and AI agents. Anything that is legacy software or pre-AI or pre-Gen AI, that's out of scope. Now, there are several multiple single vendor protocols that have been proposed for various aspects of agent tasks, resource management, tool calls, and discovery. Some of the popular ones are the Anthropic MCP, IBM ACP, Google A2A, Cisco Agency, and several more. So NLIP can interoperate with them in two ways. Mode A, where NLIP can be the northbound API, and the single vendor protocol, the southbound API, and use the LLM to translate between them. And in mode B, the NLIP provides the interoperability across the different domains of single vendor protocols. And each domain can have multiple agents using different agent frameworks. And we have done some POCs that have panned out pretty well. But we believe that eventually the industry should converge to an open standard protocol such as NLIP, or at the very least be influenced by it. Now, this is very similar to what happened in the early 1990s. Right? So every business app had its own protocol, custom client, bespoke integrations. You had several pre-HTTP protocols. But once HTTP was introduced and was widely adopted, and under a single general purpose interface like the web browser, it really simplified application delivery, interoperability, and unleashed the potential of the internet and commerce. Today, we have a fragmented ecosystem of AI agents, tools, APIs, and proprietary integrations. LLMs and AI agents don't all talk the same language. AI agents and chat are becoming a common interface for business solutions. So if you can define that single standard protocols, HTTP for intelligent agents, it can really unlock and unleash the scale and collaboration of agentic AI applications. This is the NLIP schema. As you can see, it's really simple and concise. This is it. And you can check this out at our NLIP project on the GitHub page. And I'll provide some links at the very last slide as well. So let's dig deeper into the message structure. I've highlighted the content field because that is really the key field. The rest are supporting metadata. So the basic structure of a NLIP exchange is a submessage. So the format stores what kind of content that you're sending. Is it text? Is it JSON? Is it image? Is it video? The subformat is a bit more of information on the format. So if it is text, what language it is. If it is image, what is that encoding that is being used. And the content is the actual message. So in this case, let's say, what is the weather in Berkeley tomorrow? Label is a simple name or tag, weather info, for instance. So NLIP message can consist of a sequence of submessages, but in most cases, a single submessage suffices. And I have a use case later on that talks about how we have used this submessage field as well. Right? It's really simple. Now, this message format is community-driven. So we are all, the researchers are coming together to define this structure, and it aims to solve the Tower of Babel problem in agent communications. And you find all of these other protocols defining their own message structure. So the salient features is the primary mode of interaction is natural language. It could be typed text or spoken text, which you can convert using speech-to-text conversion, and we have a POC that has worked out really well. It supports vision, audio, and other modalities. Structured text is also supported, but that's not the primary means of communication. There is no need for custom configurations. Your configuration and policy exchange are all done via natural language. And you can use different AI models at the endpoints. We have experimented with OpenAI models, Gemini models, Claude, IBM's Granite models, and they've worked out pretty well. Now, NLIP is not reinventing the wheel. It builds on tools and technologies that's already widely being used. So it runs on top of secure connections like TLS, runs on top of the authentication system, uses the base transit protocol like HTTP, and on your cell phone or computer, the NLIP library can talk to the NLIP server, which then talks to the business application servers for ordering, scheduling, or anything else. So the key message here is the NLIP integrates seamlessly with existing system architectures and doesn't reinvent the wheel. So let's look at an example. So for the next few slides, I have a few examples that will make this a bit clearer. So Agent A is trying to introduce itself to register. And there is a version mismatch between these two endpoints. So Agent A sends a message, I am A running on URI-EU. Register interprets that and creates a structure. It has an idempotency field, and it didn't find that information in the message. So it marks it at X. And then tries to clarify with Agent A, are your operations idempotent? And Agent A responds back, I cannot interpret your message, which indicates that it doesn't support it, and Register smartly assumes and identifies that as idempotency is not supported, so it's false. And it may reconfirm that you are A with URI-EU and do not support idempotency, and it confirms back as that is correct, right? So this is a request and response to ensure that the meaning itself is refined and well understood. There's another example where it's a chat interaction, probably one of the most popular use cases. And this is, so the chat client inquires about the ECMA organization. So it uses the format text, subformat is English, and has the content, what is ECMA? The response from the chat server, again, format, subformat, and the content provides the response for the question. And of course, there are other a few other fields which I've omitted. This is not as relevant. And you can find these examples in the link I provided. That's in the NLIP project page. This is part of the specifications. This is the use case that walks through a federation amongst various agents. So the client sends the same question to the proxy server. The proxy server then sends this to the 3 agents, agent 1, 2, 3, that may respond back with 3 different definitions of ECMA. The proxy then combines the responses and then uses the submessage field and sends it to the integrator app to requesting that it integrate this, synthesize this, and provide one response, and which it does and responds back to the user. So this is an example how you can use the submessage field. In this use case, NLIP has been shown to work with popular agentic AI frameworks like LangChain and Llama Index. And it also supports tool calling using standard protocols like MCP. So in this case, you have a weather chatbot where the coordinator agent that is based on the LangChain receives a user query and delegates tasks to a worker agent that is based on the Llama Index, which then accesses an external weather API using MCP or other protocols. The coordinator then aggregates the responses from this task and then returns a synthesized answer to the user. And it shows how NLIP can work across agent frameworks and uses existing protocols. There's an example, a speech-to-text, where a customer communicates the intent using speech. We use an NVIDIA ASR model to convert the speech-to-text, forward that to the channel recommender agent using NLIP over HTTP. The channel recommender finds the most relevant Reddit channel. This is a Reddit search, a Reddit channel, and then forwards that information to the search agent, which finds the most relevant or the most recent messages in each respective Reddit channel, and then stores that, caches that in the Redis database. And this is an example of speech-to-text, and that's also worked out pretty well. So key takeaways is that NLIP is structure agnostic. It is not tied to any predefined schema. It allows flexibility across diverse data formats. It's natural language centric. You can consider this as an envelope protocol, and this will enable cross-protocol communication. And it's built for generative AI, and it supports use of LLMs to translate or mediate between different message formats. And it's simple, concise, open, and standardized. So the next steps and the status. Currently, NLIP is being defined and standardized under the ECMA TC56. The draft specification initial implementations are in our NLIP project GitHub, QR code on the top right. And we do welcome your comments and feedback. These are still very early days for protocols, so it will really help. And if you're interested in supporting in POCs, that's also very welcome. We are targeting a formal standardization in the second half of 2025. So if you'd like more information, wish to get involved, please visit this NLIP GitHub page and contact us using this email address. So with that, thank you very much. Okay, cool. On time? Excellent.
Okay, thanks for Ranjan's great talk. So let's go to next speaker, Debo Duta, right?
I actually thought that you guys are presenting.
Yeah, you using that?
Yeah.
Okay.
I didn't bring my laptop because of that. Sorry for the delay. How much time do I have? We don't need Thanks. Sorry for the delay. There was a problem with the slides. They have a PDF instead of my slide deck, but we'll try to keep it simple and safe, hopefully. So if you think about okay, as a show of hands, how many people are from academia? And industry? Mostly industry. So that's good. Because what I wanted to kind of talk about is, as you are looking at different architectures for building agents, so let's imagine that multi-agent is going to be the common design pattern for enterprise applications, maybe in a year or two. It's still not there, right? And a year or two is actually being very, very optimistic. So this is your new workload, a swarm of agents. Imagine a new enterprise with 100 agents running alongside, human workers. Basically, my swarm of digital minions, right? So now the question is, where will these agents run? Most people think today it runs in the cloud because that's where we are running all these agents today. There are these platforms, and these mega companies like OpenAI, Anthropic, Google, they're just running everything in the cloud. But that's today. But what we see in the enterprise is that it's going to run anywhere and everywhere, right from your shop floor to a battleship, submarine, all the way to your distribution center in case of retail. So the question is, how will you actually build these agents? How are you going to choose the models? How are you going to choose the systems and the entire stack? And now for an enterprise IT, this is a huge problem because now you've created multiple stacks, multiple systems that they have to manage, and the InfoSec, the security officer, is also challenged because you have to then define the security policies of everything. For people who work in the industry, you know how tightly controlled these systems often need to be because the data has governance rules, especially for certain workloads like in banks, healthcare. Data cannot often leave certain guarded walls. So we believe that one needs to have consistent technical architecture for running these agents. And so the question is, how do we design the next generation enterprise AI systems, not AI systems? Because AI systems in the research community, in the open source community, are sprouting like mushrooms, Cambrian explosion. Of course, there'll be consolidation. So in order to design systems, you go back to distributed systems, right? You go back to the basics of hardcore system theory, and think about CAP theorem, where you see that only two of the three properties of a distributed system can be true, between consistency, availability, and partition. Now the question is there something like this for a multi-agent system? Because why? Because a multi-agent system is also a distributed system. So that's the kind of question that we have started asking within our team in Nutanix AI. And then one of our engineers, I don't know if he's here, Janan, so one of our engineers came up with a conjecture. It was a claim that maybe there is a CAP theorem, indeed, for designing distributed agentic system, and we called it the bar theorem. And because it was a fun talk, we actually said, let's go and have, most of us go to a bar and decide on a napkin what we need to do. So we called it a bar theorem, which is essentially the three dimensions are budget. So how do I respond? How does an agent or an LLM, even an LLM, respond within a particular latency and with a particular compute budget? So that's your budget and authenticity. So how do I know that the retrieval, so let's imagine a compound AI system, which the term was founded over here in Berkeley. A compound AI system is retrieving information. How do you know it's not hallucinating? What's the accuracy level? And then reasoning. So in reasoning, we are looking for human-like chains of thought that are logical. So now, if these are the three dimensions, we claim that any Gen AI system or multi-agentic system can prioritize at most two of the three aspects. And this, obviously, it's a very tall claim. So from within our team, a bunch of us got together to kind of, as computer scientists, when you want to prove a tall claim, you you start with smaller claims. And so we have some initial results that we are soon going to be in ArchiveX, where we've actually shown that for certain scenarios, this is actually true, using formal mechanisms. So, but over here, like, let's look at the bar theorem in real life, right? So if you think about enterprise AI, most of the common use cases, 90% plus use cases, basically talk to my data. Talk to my data, talk to my code, talk to my data warehouse, talk to my time series. And that's basically, you want cheap retrieval, you want less hallucination, because you don't want data retrieval or a query system or a RAG tool give you false results. Then you want to take an action, you want auditable trails, and you want some kind of reasoning, mild reasoning with some small LLMs, and you want it to be cheap too, right? So there are these RPA agents and a bunch of other agents where you can build pretty much with open source small models today. But they may not be very highly accurate for retrieval. But then there are these large compound AI systems that we all know about, deep research agents, coding assistants, and very complex video generation, which is pretty good. But the price that we pay today, somebody's subsidizing it today. When we all have to pay for the ChatGPT and the Anthropics of the world, and there has to be a P&L budget associated, I think the cost will be much more than it is today. Unless this community can design very, very cost-effective solutions to bring down the cost by 2 orders of magnitude, it's going to be hard. So our claim is that this bar theorem is going to be true in real life for a while. Now, if you think about an enterprise, look at a bank, a hospital, we all have to go to a hospital, we have to go to a retail store. When you want to design agents that run all the way from a retail store to a packing distribution center to the headquarters, data centers and in the cloud, if you look at every data scientist today, they all want 4 to 5 LLMs to build an agent. It's not just one LLM, right? You need an embedding endpoint, you need an inference endpoint, you need re-rankers and guardrails and so on and so forth. So if you look at an entire cost to the enterprise, the TCO is astronomical. And most of these data scientists today, including in my own team, a bunch of them are here, everybody loves to run VLLM, again from Berkeley, or pick your favorite inference endpoint in a container and just run it and not have to deal with any other thing. Like, I just run it on my laptop or running it on Olama. So that is what's happening today. But what the IT departments of enterprise is petrified and paranoid, because it just leads to a huge problem with security. It's complex to manage, the security risks, it's just expensive. So our strategy for at least, with the budget part of it and complexity part of it, is to kind of shrink everything down into shared enterprise grade endpoint management, and consistent architectures, starting with Kubernetes, internally inside the company, we've standardized on vector databases using open source. Basically, everything is open source, using Postgres, PG Vector. So we have an entire stack that we use to run multiple agents, and the agents can come from with any kind of tool chain, and you can have any kind of communication protocol. That's for us, the technical community will figure it out. For me, the first thing is, how do I manage the costs? How do I make it easy to deploy? I partner with my CIO to make sure that we can do this inside the company in a simple, secure, and efficient manner. I'll end the talk with a couple of non-technical stuff, which is very important as you design systems. There are three dimensions of AI, at least in Nutanix and in most enterprise companies that I talk to, are people, tech, and process. Of course, this conference and most conferences and the entire valley is focused on the tech, which is the right thing to do. But when we look at deploying these agents in actually enterprise companies, banks, hospitals, companies like Nutanix, retail stores, people become a huge dimension in the sense that we need to upskill existing employees to learn AI, to understand how to even deploy, even operate these agents. Because at the end of the day, autonomous agents are still going to be a thing in the future, right? Thing of the future. It's not happening anytime soon. So, and the other thing is processes. Today's enterprise already have fixed processes. We all love to, in this conference, want to talk about multi-agent systems, talking to each other using some protocol, but that's not how they will be deployed today. There has to be a change in processes. How do you show the ROI? Think in terms of, if you spend $1 million building and deploying agents, are you going to get $5 million worth of ROI? That's still an open question. And the other thing is that coming to an enterprise is not just engineering, right? A lot of people are very concerned. Like, so you have the AI team that wants to do the cool things, the right tech, and then supposedly they are being slowed down, but it's not slowed down, because in a regulated industry, the IT comes in and says, you cannot run this wherever you want. You can't just run a VLLM container where you want. And then there's a legal team that says, how are you going to run this brand new model just popped up in a leaderboard, because I don't even know whether you can even use this. We don't know what the data provenance of that model is. So there are, again, three dimensions in an organization, and these three teams. So I'm usually in meetings with these three stakeholders, IT, the legal team, and the AI team, to figure out how do we change the processes that I talked about in this. And for each of this, is there a theorem that we can prove or a conjecture that we can come up with? How do we keep everyone happy? How do we show ROI in the enterprise while doing the right technology over here? Because we are all technical folks here. So anyway, the key takeaways is that multi-agent systems are going to happen. They're going to happen slowly, as you can see. 4 to 5 LLMs per agent, 100 agents. Think about this. And LLMs are becoming small. They're getting better at reasoning. But you need to run these agents close to where you want to do your business. Maybe in the bank, maybe in case of military, somewhere else, right? In the field, battlefield. And you need to run agents close, and then you need to design these agents. They are distributed systems, so think about what are the real technical barriers. Where is the sweet spot for designing these agents? And manage your infrastructure sprawl. Don't think of that. Even as technical folks, think about when you're building something, how is this going to be managed, deployed, used? So I think with that, prioritize not just tech, but people and processes when you're thinking in terms of computer science. But I feel CS is a wide enough field. It's liberal arts today. You can actually apply computer science to all the three dimensions. And with that, thank you.
Thank you,
thanks for Dable's great talk. So next speaker is Chi Wang. Yeah, Chi Wang is a senior staff research scientist at Google DeepMind. He will introduce mass-gene frontier multi-agent scanning in open source. You will use your laptop. Okay. Thanks. Is this? Yeah. Okay. Okay, let's welcome Chi Wang for his talk.
Thank you. Good morning, everyone. Thanks for joining us at this Agentic AI Summit. This is the frontier stage, so I'm going to present a very new project, new open source project that's pushing the boundaries of the collaborative AI. How new is this project? It's just 7 days old. The first MVP was just out 1 week ago. So good luck with me. I've never presented a project as young as this one. In one word, this is a multi-agent scaling system that runs multiple agents, diverse agents, in parallel, sharing intelligence and refining each other's work. Okay, and you can check the GitHub from massgen.ai link. And yeah, let's dive in. So if you have followed the recent breakthroughs from Grok Heavy or Gemini DeepThink, it's easy to see the inspiration. Harnessing multiple AI minds that tackle complexity far beyond any single model can do. Okay, there's a lot of recent exciting things about it, and the North Star is that we want to build co-evolving agents through collaborative interaction. So many of you have probably know that I've created this AutoGen open source framework since 2023. I've been working on IDEA and now AG2 for these multi-agent conversations. But many challenges still remain, and especially with the change of the new technology. In April this year, I wrote a blog post called Myth of Reasoning, and I talk about this thread of thoughts idea. And the key insight is that the human reasoning is actually much messier than what most people realize. So most time we have intuitive thoughts, and only after that we try to find justifications or find it's wrong and restart this process again. And but we need to make it cleaner for presentation, for communication, to convince others. So the nice chain of thought is not a start. It's the outcome of these massive processes, and by nature it's collaborative. Right? So that's kind of one of the key insights I've been working on in the past few months. And recently I've seen real evidence in practice. So Grok Heavy and DeepThink, they prove that this is not just theoretical, it's practical and deployable. Right? Let's take the Grok Heavy as an example. If you check their performance on last human exam, right? Very, very challenging benchmark. Grok 4 standard achieves about 38%, and Grok Heavy achieves about 15% higher. By doing what? The same model. They run the same model, but just using multi-agent architecture. And they price it 10 times higher, right? $30 versus $300 per month. So that's basically the price just for this multi-agent architecture, nothing else. And by the way, DeepThink, Gemini DeepThink is also available now in Google Ultra, also in the highest tier subscription. So I think these are like the most strongest commercial evidence I've seen so far about the power of multi-agent architecture. But what if you don't have access to those expensive subscriptions, I have the good news for you. Okay, just if you use MathGen, you can just use any existing API keys you have to any models. You can easily kind of run this experiment of multi-agent scaling, right? You can use a single model with different configurations, or mix multiple different models or agents, right, as you want. And how this works is MathGen orchestrator will take a user's query, distribute that task to the multiple agents, and run them in parallel. And the magic happens when there's this shared collaboration hub, right? So all the agents, they can check the real-time updates from others, criticize and refine the results, right? And if some agent finished the work but other agents have new updates, then the agent might get restarted. And eventually they will converge to some consensus and generate a final answer. So that helps refine the quality. And here we can see that the multiple ideas are integrated together. We want to kind of leverage the strengths, unique strengths for different models of different providers and different agents. And we want to run them in parallel to slash the latency. But in the same time, we want the agents to be able to absorb and take intelligence shared from others and improve their own work. Okay? And this iterative refinement keeps going until the consensus. It's very easy to get started. You can simply clone this repo and install some minimal dependencies and get your API keys configured. Okay? And then you can use the CLI to run some configurations. You can configure them differently and try them out. You can either use interactive mode to have multiple turns conversations, or just ask simple questions. Let's do a quick demo here. So I already have VS Code open and already cloned the repo. So I'm going to try to run the latest version. If you are using the main branch, you may get a slightly different result. Here I'm using a 3-agent default configuration and asking, give me all the talks on agent frameworks in Berkeley Agentic AI Summit 2025. Okay, let's run that. Okay, here the system gets started. You can see the question on top and the 3 agents running in parallel. The first agent using GPT-4o, second one using 4o mini, and third one using Grok 3 mini. And you can see all the agents are working in parallel. Some of the agents have access to building web search tools or code execution tools, so they will invoke them when they need to. We can see that some agents already finished work, like the 4o mini already provided some answer and have several rounds of voting already. And okay, after the working, we finally selected one agent called the 4o agent. Let's see, and the 4o agent is doing the final presentation to generate final answer. Right? You can see the whole process, and the 4o got 3 votes here by the end of the interactions. We can check the output for each agent. Here I enter 1, so let's check agent 1's working process. So this is a log, right? We see that it started with some web search. After search, it generated the initial answer, like this. It found a few talks, some panel discussions, and gave a link to the Berkeley website. And later it has some voting about the agents. Okay. I can also check the second agent, the 4o mini. Yeah, it generates some answers. Says it didn't use web search, so it didn't find the right information. Let's see the Grok 4 mini. The initial answer from Grok 4 mini is they don't have access to the information, but later once it sees other agents' answers, it updated the answer. Actually, you can see another answer provided from here. So it actually updates the answer, but eventually it's also voted for all. Okay, and the final answer It's presented by Foro, and it combines the information from all the different agents. Okay, so that's a simple demo. You can try this out and try different queries. There are a few earlier case studies when we had the first version. So this was using the current main branch. And we tried a number of different examples. For example, we asked agents to find who is IMO 2025 winner, which AI wants IMO 2025. And we can also ask open-ended questions like do some collateral writing, write a story for like robot music stories. And we can also ask very hard questions like how much does it cost to evaluate Graph 4 on the HRE benchmark? This is an open question. You can't find any information online to directly answer these questions. But some agents can find a piece of information from the website, and some other agents can use their code execution, data analysis capability to do the estimate. So eventually, the multiple agents can collaborate to try to answer this question. We can also ask questions like travel guide, like if I want to travel to Stockholm in October, can provide a travel guide. Usually, a single agent will find some information, but each of them will find slightly different information, and only when you put them together, you get the best answer. So from this case study, you can see there are several different flavors or reasons why this multi-agent scaling can help. For open-ended questions, usually different agents will have different perspectives, and you already get the best answer from combining them. And for many other hard tasks, it requires many different steps. Usually the initial answer generated by any single agent is preliminary, but after they see others' work, they get inspired and they keep refining their work, and you usually get better answers. You can also understand this from another practical point of view. I don't know how many of you like using multiple AIs at the same time. And when you have a hard question, you try one AI, but you don't really trust the result. So probably you will try another AI and cross-check to make sure you're not fooled, right? So this kind of simulate that automatically, right, by having the multiple agents cross-checking each other's work. But it goes beyond that because it doesn't stop at the first round. It actually tries to push them harder, right, to make them further work more. And until they get the final comprehensive answer. So yeah, you can find some of the case studies from the website as well, from the GitHub repo. There's still a lot of, this is very new, right? This is just a start of this direction. And there are a lot of whole set of challenges ahead. The eventual vision we want to have is to have this recursive scaling so that every time you get a new agent, you add to the system and it amplifies the whole. But we are far from that. So there's a lot of challenges like consensus, shared context, and interoperability, right? We have heard many great talks about addressing these issues. Eventually, we need to solve all these hard problems. But if this really works, then we can have AI that's kind of similar to how we scale ourselves, right? AI can scale themselves too. Yeah, so that's a very brief introduction about this project. This is just the beginning. I hope you can check the repo on GitHub, start it, start discussion, join our Discord channels, and build this together. By the way, the new version I just used it's coming soon, probably this weekend. Yeah, so I will get the chance to try it out and share your feedback. Yeah, thank you very much. I think I still have time for questions.
So any question for Chiwan's talk? Okay.
It can be customized for me running several coding agents, orchestrating other type of tasks?
Yeah. Great question. Yeah, coding agent is one most important kind of capability I want to integrate into this messaging. Why is coding a big deal? Because it's a meta power, right? An agent that can change its own software, can self-improve, can experiment, can learn and spawn even new sub-agents. And yeah, you have seen the strong, powerful coding system like Cloud Code, Gemini Cli, integrated into our developer workflows. And yeah, so but right now they are working alone, right? So the single agent working alone. And if we can integrate that into this multi-agent parallel working paradigm, I think the power will be amplified to a large degree. So that's the big next milestone I want to achieve. Great question.
I have a question about like if we have, for example, multiple agent booking a ticket,
Yeah.
so they try to book it all together. How can we ensure that they don't overbook and double book? Or how can we check that each of our tasks, whether it's failed or not, in a kind of holistic way?
Yeah. This is like it touches very important about like a conflict, or sometimes the agents' work are not easily kind of scalable, right? So that's exactly the kind of the challenges we need to solve, especially when now each agent can go beyond question answering. They also have built-in tools that often can do things. So right now we're not giving the agents that kind of tools. We're only giving them like search, code execution, and they can work in isolation. But as soon as we get to the point where the multi-agent might be working at the same workspace and they have conflict, we have to find a way to resolve that. So that's kind of a great research question to look at next. Yeah. Thank you.
Thank you.
So I have a great
Thank you.
talk. So I have one question. So in context learning, we have, let's say, some poor quality examples. It might hinder the whole trajectory. So I want to see, let's say, if we have multiple agents and we are scaling up,
Yeah.
and some of the runs are lower quality. So what is your vision? How we can make sure that doesn't like hinder the whole trajectory for the agent?
Yeah, exactly. So actually the demo just shows that exactly, right? So two agents actually provide very poor answers in the beginning. Only one agent find the right answer. And I think this requires some fundamental capabilities to the base models and agents. So each agent has to have a basic way, evaluation capability. So giving multiple answers, it needs to know the relatively better answer for the most of the time. Otherwise, it's not work. I think this built on the assumption that the model has been improving to a point that most of the strongest frontier models have that capabilities. But this is a big assumption that we do need to check. I actually wrote this down in my blog post. I think there are several basic capabilities we need to have. This is one of them. Yeah. Thank you. Thank you very much.
Okay, thanks for Sean's great talk. So you use your web tool, right? So next talk will be given by Pabi Melo, right? And Pabi Melo is the CPU and the vice president of Cisco, and this talk is about building an open infrastructure for the Internet of Agents. Let's welcome Pabi.
Thank you very much. Thank you all for being here. I'm here to talk to you all about building the next internet, the open interoperable Internet of Agents. And it was very nice to hear the speakers in front of me actually refer to the need for why we need something like this. So Ranjan mentioned how we need to have semantic communication between agents in order to have truly working multi-agent systems. She mentioned the need to have multi-agent systems that can collaborate and all of that. So this is the world that we are moving towards, and I think it's very appropriate. We are here in the frontier stage. This is the new frontier, the frontier of agentic AI, and more particularly, multi-agentic systems. So I'm going to skip through some of the slides here because I know for this audience, it's probably, the need for agents and so on is probably, old hat. I don't need to belabor the point. But let's talk about why do we need a new internet? I get this question a lot. When I talk about the open interoperable internet for agents, it's like we already have an internet. Isn't that sufficient for agents to communicate with each other? After all, at the end of the day, agents are just software entities, right? Why can't we just use the internet we have? Well, the reason for that is agents are substantively different from the kinds of software entities that we know, whether it's physical machines, virtual machines, containers, microservices, APIs, what have you. What we have today, the behavioral is largely deterministic. And with agents, we are moving, there's going to be a fundamental shift to move from deterministic behavior to probabilistic, non-deterministic behavior. And that leads us to a need for new primitives, new foundational technologies that can enable this kind of communication, this non-deterministic, probabilistic communication to happen in a way that's secure and reliable. So we need to have new ways for these agents to be able to discover each other, to communicate with each other securely and reliably across frameworks, across platforms. And again, one of the former speakers, Debo, mentioned we are going to have a fragmented, heterogeneous type of deployment models. There's going to be agents running in the cloud, agents running on-prem, and all of them need to be able to communicate with each other. And not to mention, the agent communication is kind of somewhere between. We know how to do, obviously we know how to do human-to-human communication. We know how to do human-to-machine communication, and we know how to do machine-to-machine communication. But the agentic communication kind of has attributes of both human communication in the sense that it is non-deterministic, probabilistic, natural language-based, multimodal, all of that. But at the same time, in terms of the scale, the speed, the ephemerality of agents, it's close to machine. So you have machine speed, scale, ephemerality combined with human attributes of the types of communication. And all of this is what leads us to the need for this new internet. And so what we are seeing here is really something that is layered on top of the internet that we have today. So a semantic and syntactic layer, and again, the NLIP thing that Ranjan talked about earlier, and the semantic communication that kind of feeds into this need for a true semantic layer that sits above the internet and enables agents to talk to each other. And that's what we are building towards. So without further ado, I'm going to skip past the slide. This just talks about a number of different use cases that you can see. And maybe I'll talk through this just for a little bit. We are talking here about common use cases that need this kind of multi-agent system. Well, before I get into this, let me have a quick show of hands. How many of you here have built an agent? Wow, nearly everyone. This is a great audience. How many of you have built a multi-agent system? Wow, this is great. This is really a great audience. Now that is unusual. So what I'm talking about here, and I'm not going to ask for another show of hands. I think many of you have built multi-agent systems, but typically a lot of the multi-agent systems being built now are typically built within a single framework. And that's because, that's just the ease of how to build it. However, what this slide is talking about is common scientific and business use cases that need agents that are built across multiple frameworks. Agents built on LangGraph, agents built on AG2, agents built on Llama Index, all having to talk to each other to solve a common problem. And this goes from very well understood domains, right? You can think about like an IT app deployment scenario. And for that, this is something that's very near and dear to us. We are Outshift, we are part of Cisco, we are an infrastructure company. This is something that we do. This is our bread and butter. Very well understood domain. And yet, even in this domain, when you think about the end-to-end problem that you have to solve, all the way from the service ticket, which may be dealt with by an agent that's running in ServiceNow, having to talk to an agent that has the customer data for that particular issue, which may be an agent running in Salesforce. And then those agents having to collaborate with agents that know about your physical infrastructure, your network data, your security data, your observability data, all of that, which may be from agents built by Cisco and running on the customer's infrastructure. So all of them have to come together to solve this problem end to end. And similarly, there are other domains, emerging domains like drug discovery, which are powered by agents. And there you have agents that are like general purpose large language model agents, from people like Anthropic and so on, talking to agents that are trained on drug discovery data, and maybe even talking to embodied AI agents that are running physical robots that conduct experiments. So again, the meta point here that I'm trying to make here is, you have agents that need to communicate. Oh wow, I'm already at, I am running out of time. So this is the collective that we've built, Agency. I'm very happy to say that a couple of the former speakers, are in this collective. So we have IBM Red Hat. It is Agency, AGNTCY. A lot of industry backing for it, a number of startups. I have and it is part of, as of this week, it's part of the Linux Foundation. So it is fully open source. We are on GitHub at agency.org and also on github.com/agency. Please go check us out. I was going to go through the architecture of what we have built out, but suffice it to say, I won't have time to get through this entire diagram. But this represents all of the different stages in an agentic life cycle. So all the way from a common way for agents to talk about themselves, to advertise their capabilities, their skills, etc., so that other agents can discover them, how that can show up in a directory where humans or agents can go discover what's out there, what the capabilities are, how they can be stitched together and allow communication again at that semantic layer, so that agents built on different frameworks, on different clouds, on different platforms can communicate and be understood. And then how all of that can be deployed to your cloud infrastructure with a messaging layer that is optimized for agentic communication. And again, agentic communication has a certain shape to it, if you will. It is multimodal. It needs to be very low latency because there may be a human in the loop. But at the same time, there's large state exchange that needs to happen, one-to-one, many-to-one, many-to-many, etc. So all of those communication modes are supported by the messaging layer that we have built out. Again, all of this is open source. Again, another slide that gives the architecture in a very simplified way. This also talks about some of the other pillars of the architecture. There's the identity piece. Again, I could go on that for a long time. There are very unique challenges posed by agentic identity. There's, of course, the identity of the agent itself. How do you describe that? What is the agent allowed to do? But then there's also the principal, the human on whose behalf the agent is acting, and that human has an identity and what the human is allowed to do, and all of that needs to come together. On top of that, agents are autonomous entities. They typically carry out a multitude of different tasks, and depending on the specific task that an agent is performing at any given time, what they are allowed to do may be different. So you have this tuple of agentic identity, the identity of the human principal on whose behalf the agent is acting, and then the task that the agent is performing at any given time. So all of this needs to come together when you talk about the life cycle of an agentic identity. So that's something that we've considered as part of the agency. There's the big vexing problem of observing and evaluating agentic systems. Now, when you talk about, again, I talked earlier about the fact that why do we need a new internet for agents? Because agentic behavior is fundamentally different. They're deterministic. They're non-deterministic. They're more probabilistic in nature, etc. What that then means is you need to have strong observability around these agentic systems to ensure that, are these agents doing what they're supposed to do? Are these multi-agent systems actually doing what they're supposed to do? Conversely, are they doing something they're not supposed to do? So all of that, so we have observability and security primitives built into agency as well. I will leave you with this. I know I'm at time. Agency.org, please go check it out. There's a lot of code, all the stuff, the architecture that I described, the code that's behind it, the specifications, a sample reference application that will let you build multi-agentic systems in a true standardized way using these standard primitives that we've built. It's on. With that, I will wind up here. Thank you very much.
Okay, thanks for happy great talk. So next speaker is Jay Roach, right? Okay. So Jay Roach is a senior developer advocate at NVIDIA, and he will introduce building GPU-accelerated agentic workflows. Okay, let's welcome Jay's great talk.
Thank you. Good morning, everyone. I'm Jay. I'm a developer advocate at NVIDIA, where I focus on building LLM application. And today I'm really excited to talk to you about how to build agentic workflows by harnessing the power of NVIDIA GPUs. So let's start with a quick timeline. We have had single call LLMs for a while now, where you send one prompt and get completion back. In 2024, it was RAG, where you basically do vector stored lookups to pull in up-to-date information. And this year, it's the year of agents, where you stitch multiple LLM calls, tool invocations, and reasoning loops into fully autonomous processes. But the true power of this new paradigm is realized when agents work together. Think of an enterprise ecosystem where there are multiple departments which have their own agents. So in this, but to build these kind of multi-agent system, like for enterprise level, like it's really difficult building this kind of workflows. You might face many challenges, which could be architectural complexity, making different tools from different frameworks work together, and there's also problem with the performance and the reliability. And to solve this problem and to manage these systems, earlier this year, we open sourced a framework or toolkit called as NEMO Agent Toolkit, and it is designed to be the glue for your existing agent workflow. And it does that by using universal descriptors. So what it does is it basically converts every tool, agent, or memory into a function call. And you can piece this function call together, whether it's LangChain, Llama Index, or something that you have built yourself. So let's take a quick demo about how to build these GPU-accelerated multi-agentic frameworks. So in this case, imagine there's an enterprise with multiple teams, and those multiple teams have their own agentic workflows built with different frameworks. So in this case, there are 3 agents: HR, finance, and IT. And these are built with different agentic frameworks with their specific or relevant knowledge bases for their specific departments. So we are combining these all 3 agents and controlling them using a supervisor agent, which is built with LangGraph in this case. And this all pipeline is built using NEMO Agent Toolkit, which is open source. And this all pipeline is monitored using Phoenix, Arise Phoenix, which is an open source observability tool. And the RAG tool in this case is completely GPU accelerated. Vector database is being run on Milvus, which is open source and supported by NVIDIA. Then there's LLM and embedding models are also running on GPUs. Specifically on NIM, so it's basically a containerized solution to deploy open source LLMs and embedding models with just a single command. And in order to piece those workflow, you have to simply configure a YAML file where you basically mention all the tools that you have access to. And this is too verbose, but what I'm trying to run here is basically running the entire pipeline by giving it a prompt about, hey, what's the parental leave policy? And once the workflow runs, the supervisor agent recognizes this is an HR query and redirects it to the HR agent, giving you the final response. And on the right, it is Phoenix, which is basically tracing the every step of the interaction with this agentic workflow. So this is it. So the future of complex AI isn't just a single agent, but it's multi-agent working together. And NEMO Agent Toolkit helps you achieve that. And the GPU acceleration is what makes this all real time. So if you'd like to learn more about what tools we offer and want to stay up to date, feel free to scan this QR code and join the developer program. That's it. Thank you everyone for listening.
Thanks for GS great talk. Let's move to the next speaker. So next speaker is Nandi Sambroshu. Nandi Sambroshu is a staff scientist at Amazon. And he will introduce evaluating agents that automate complex industrial as OPS. Yeah. Okay, let's welcome Nandi.
Hello, everyone. Good morning. Excited to be here. Great talk so far. So I am a senior scientist in Amazon working on building a multi-agent framework for automating SOPs. So it's complex industrial SOPs, which is beyond simple tasks. Is it better now? Yeah. So, the SOPs are something that human associates follow. They're written by humans for humans, not really meant for machines to comprehend. That's where the additional challenge comes in when we are trying to automate them using multi-agent systems. So they are much more ambiguous, open to interpretation. There is a lot of reasoning going on, diverse tool calling, and then also interaction of multiple agents. So I'll give you an example. So in the shipping industry, it's classifying a product, whether it's dangerous or how hazardous it is. It's a very common problem. So they have to, so associates who make this determination, and not everything can be actually done by ML models. So you need human associates looking at different like safety data sheets or other multiple different data sources and actually making a decision and then classifying it. So how would an agent accomplish something similar, right? So it seems simple for humans. Humans have been doing it for a while, but when you try to have like an agent or multiple agents follow that same set of instructions, there are many nuanced reasoning, and like you have to call the tool multiple tools with precise parameters and interpret the values. Sometimes some APIs may fail. You still have to orchestrate the whole workflow, right? So that's like from an agent perspective. What about the developer? Like there are many decisions the developer has to make, right? So we need to know whether it's just a simple function calling agent or is it going to be a multi-agent framework, reasoning between steps, how much of it should be in the context, how much of the background knowledge of that org or of that of the documents should be put in a knowledge base. And then the reliability. A lot of the speakers before me have mentioned the costs as a big factor. How do you make these decisions? That what's more important for that use case? Accuracy, reliability, cost, latency, etc. So there are lots of decisions that a developer needs to make. So where do you make those decisions before you actually deploy your multi-agent system to automate complex industry tasks, right? So we couldn't find benchmarks that were readily available. So the ones that are currently very popular are like Gorilla benchmarks, GAIA examples. There are lots of results on these, and LLMs seem to be doing well on these, but the same agent framework in these examples didn't really help with comprehending and automating complex SOPs. So we ended up building a benchmark of our own. So we have this is available on archive. We'll be posting on GitHub soon. It's a benchmark of like 10 different industry use cases, like starting from customer support, aviation, retail, even healthcare. So we've created SOPs, like long instructions, along with the tool APIs and the code, like a mock. Like the code is obviously a mock of the real APIs, and also data sets. And at every stage, we have had human intervention, like human validation, like a scientist validating the code, the industry experts validating the SOP and the APIs and the data sets. So it's like, so for a dangerous good use case, you actually have the data set which has the input and output of every API call what you expect. So you have the safety data sheet, the handling and storage restrictions, etc. So it turns out like building the SOPs was not straightforward at all. It was like a very hierarchical and complex way of prompting and creating these different aspects like SOP as well as APIs and data sets. So an evaluation is like much beyond pass and fail. So here, like I'll give an example. So we want to make sure that it goes through the whole execution workflow. So we tried only two paradigms so far, like React and function calling. And as you can see, on an average, it gets 35%, like 70%. 70% actually like successfully executes, and only 35% of them actually have correct answer. So it's like we have a long way to go before we can actually reach the 95, 97% of human level accuracy. So it turns out synthetic data is powerful. So we want to try out these different agentic applications and improvements before we actually go and test out on real production data sets. And so the key thing is that before automating something with multi-agent systems, there are lots of decisions we need to make, and we need to build realistic benchmarks where we can we can feel confident on those before moving to like shadow and production. So we invite people to we also have the benchmark generation code available, so people can build benchmarks, add to SOP bench, so the community can actually keep growing. That's it. Thank you.
Okay, thanks, Nadia's talk. Next speaker is Pushkar Nadkar. So Pushkar Nadkar is a senior principal engineer at Supernova Systems. He will introduce Supernova SN40L unleashing agentic AI with data flow.
Hi, good morning, everyone. My name is Pushkar Nadkar. I work at Supernova Systems, and today I will talk about SN40L. That's the chip that we've built, and I know how it enables the agentic AI. So I'll not go into this slide. Jay already talked about it, and multiple others have already talked about the journey towards this agentic AI systems. Briefly on this, now we have multi-agent systems, which are basically each agent is having its own context. There are multiple LLM calls that are made by these agents, and they also use tools. Now with this, the user experience have changed a bit because the tokens that are needed for serving such applications have exploded a lot. So the inference providers need to provide these tokens at a very high speed. So we have built a full stack solution for serving agentic AI from RDUs to products like Samba Cloud, Samba Stack, and Samba Managed. We can talk about these products later. Today we'll focus on SN40L, which is the chip that enables all of these products for us. So diving deeper, each of the products that we have has a rack backing it. And each rack has around 16 RDUs, and these RDUs are basically the the inference serving engine that we have. Each RDU has compute, which is in the form of tiles, and the backing memory is HBM and DDR. So the tiles themselves have what we call as PCUs and PMUs. PCUs are pattern memory unit, pattern compute units, and PMUs are pattern memory units. So these units are formed in a mesh, and they form the basis of data flow, which we'll touch later. The three-tier memory, the SRAMs that are part of the PMUs, the HBM and DDR form the memory system that will hold multiple models together. Now, what is data flow? So if you see, this blue box is basically the attention mechanism that's there in multiple LLMs. And these attention mechanism can be further divided into multiple operators or kernels. In traditional GPU systems on the left, you have these operators getting inputs from the memory, and then they save the output or the result into the memory once the execution is done. So this forms a stop and go kind of execution, many times bottlenecked by memory bandwidth. Whereas on the right side, you have the RDU, which is basically data flow architectures where these blue boxes are PCUs and PMUs. These operators are mapped onto these PCUs and PMUs, and the input streams, which are this QKV, for example, are just, they form the input stream, and you just let the data flow so that the output result is present back onto the memory. So this spatial execution actually helps to provide a lot of compute density and compute efficiency. For example, Llama 3.18b can be is shown here with multiple layers. Each decoder layer, for each decoder layer, the K1, K2, K3 are actually the GPU kernels that will get executed with a stop and go mechanism. Whereas for Sambanova SN40L, you have just one K0 kernel which will execute in one shot. And these decoders can be further fused into something called as loop decoder with kernel looping. So you have a 3.18b model now just running 4 different executions. So this kind of helped us go from baseline 100 tokens per second. With single decoder, we got to 500 tokens per second, and with temporal fusion or kernel looping, we got to around 1100 token per second for the 3.18b. And along with that, there is power efficiency. We can run multiple models on single rack machines, whereas others will take multiple racks to run such models. And for agentic AI, you have multiple applications with multiple models. What happens is traditional GPU systems with these multiple models need to be served by separate set of GPUs. Whereas for Samanova, because we have DDR, we can actually serve these models on a single rack where all the models, the DDR is almost like 24 terabytes. So you can have as many models as you want, as many weights as you want, as many fine-tuned checkpoints as you want, and serve from the same system with very low switching latency across the models. So this again shows the same thing. You have one endpoint which is serving all the inference requests, and multiple fine-tuned experts can be served on this system. So this helps with memory efficiency, power efficiency, compute efficiency, and you have much better control, and you can enable complex workflows within a isolated environment in your data centers. So for different models, this is the artificial analysis data. We have all the speeds are mentioned here, and these are the models that we are serving. So multiple models from Meta, Qwen, DeepSeek, OpenAI. So yeah, I had very little time, so I had to rush through all of that, but feel free to catch me. I'm here throughout the day, and you can read about it, try it. There are multiple papers out there about the architecture, and feel free to talk to me. Thank you so much.
Okay, thank you for Pushkar's talk. So next speaker is Xifeng Yan. Okay. So Xifeng Yan is a professor at UCSB, and he will introduce transforming agent-based customer service chatbots with declarative programming.
Thank you very much.
Yeah, no problem. Okay, let's welcome Xifeng's talk.
Thank you very much. Thank you very much. Thanks for the invitation. Today I'm going to talk about the need of developing agent declarative language for easing the development of customer service chatbot. Customer service chatbot has been studied for a long, long time. But we know even with the advance of newest large language model techniques, it is still not well done. Fortunately, we have a bunch of new tools available that can help us to build those bots. For example, OpenAI Swarm system, which can package service functions in each individual agent and then coordinate this agent to finish customer service task. We also have this long-time existing open source community that can help us build help us to build the customer service bot. And there are many no-code environments that can help us to achieve this task. But if we look at those environments carefully, we will see that most of them are program-centric, not agent-centric. Even for OpenAI Swarm environment, we will see that it can package functions in agents, but the agent's definition is distributed in those programs, are buried in Python program. We are thinking that whether we can develop a kind of agent declarative language, so the language just describe what agents can do and their relationship. Forget about the Python code, forget about all kinds of implementation details and optimizations. Just have a pure agent-centric file which describes the domain-specific knowledge for a specific customer service and their business logic. So here I just show you one example that each agent actually can handle FAQ, an agent can handle recommendation, an agent can handle the guardrail, an agent can handle very fine-grained flow like placing an order, for example. This is a flow kind of program, and then we have agent to coordinate them together, all in one single file. And then the question is, do we really need it? I think yes. If everyone has used a SQL program, you know that how SQL good is, right? So basically, using SQL program, we are able to decouple the program from the underlying system. Same thing here. If we have these ADO programs, we will not just lock ourselves in one vendor. If you are using Rasa to develop a customer service bot, you cannot use features in OpenAI Swarm. You have to redevelop everything in order to use those features. By separating them, we have more opportunity to have an optimized system. And furthermore, in ADO, we actually try to recommend more and more natural language programming. Currently, if we mix natural language programming with this Python program, it is quite hard for the business users to read and understand those programs. And we have to maintain a separate SOP statements and convert those statements to a Python program. That's not convenient. In addition to those benefits, we also see that ADO can actually simplify maintenance and updates. We know after those chatbots have been developed, we always need to maintain it and we need to continuously refine it. And for ADO, we basically add a few natural language sentences. But if you use a hybrid Python program environment, you have to define agent using Python program. You need to define intent. You need to catch those intent and put all these Python code in order to implement those revisions. That is not convenient at all, especially for those professionals who do not understand Python very well. So here I would like to show you where does ADO sit. So on the left side, you will see many very powerful existing hybrid programming and framework like AutoGen and so on. They're very good. They can take advantage of both powerful Python programming library and large language models. But just through a few slides I just mentioned, I hope that I can convince you that there's a room for a declarative agent language, especially at least in the context of customer service. You only need one file. This file can be shared with the business users because they are written in a language very close to natural language, so can be understood easily. Okay, so we developed a prototype, and you're welcome to use it, give us a suggestion, and you all can join us, try to make it happen. Agent declarative language. Thank you very much.
Okay, thank you for Xifan's talk. The next speaker is Taba. Let's just move to the next session. Next speaker is Taba Shah. Where is Taba Shah? Did that come? Where is Tabasha? Okay. Okay. Tabasha is an AI architect at Innovator, and his talk is about evaluating AI agents for healthcare scenarios, metrics, and stress testing. Okay, let's welcome Tabasha.
Hello everyone. Thank you for joining in. And what I'm going to do today is I'm going to specifically discuss on AI agents and healthcare. Right? Healthcare is one of, I think, the ripe field, ripe business domain and a ripe sector where AI agents can be used. There is a lot of documentation, there is a lot of bureaucracy involved in healthcare, so it's a great field to apply agents. But healthcare also comes with a lot of responsibility in how we are using these agents. So what I'm going to discuss today is at Innovator, how do we evaluate AI agents, right? So I think till now a lot of discussion has been how to make the best AI agents, but again, the most important thing probably is going to be how are we going to evaluate these AI agents. So Okay. Why evaluation? Again, I probably don't need to harp more on that, but starting from the days of good old statistics, evaluation has probably been the most important part of AI, right? And as building models has become simpler and simpler, the challenge of using those models and getting the best outcomes and evaluating those outcomes has become more challenging. And that is what are some of the applications of agentic AI in healthcare? It is across all sections, right? Patient, provider, payer. You can count from prior authorization, patient experience, claims processing, clinical coding, documentation, care management. I can probably spend a day or two just highlighting what agentic AI can do in healthcare, and it's just how can we scale that. When it comes to evaluating agentic AI, there are three main challenges. One is what we call as scenarios, right? Then there are metrics. What metrics can we use to evaluate them? And lastly, it's about safety, right? How do we ensure that the agents which we are building are safe, right? To be used by the end users who are going to be patients and providers. Scenarios, agentic AI is no longer going to be evaluated on data points. They are going to be evaluated on scenarios which are derived from this data, right? And healthcare data sets are traditionally been rare, right? There are some out there like Cynthia, Mimic4, Medline, but beyond that, there are very, very few data sets which actually capture the longitudinal history of patients, right? For example, an example is an AI agent calling a patient to book a referral appointment, right? What are the variances which we need to simulate? Accent of the speaker, medical terminology, educational background, age, and again, there are a lot of variables which we need to simulate, and our approach has been to use grounded simulations, right? So we use actual data plus user research plus LLMs to generate very realistic scenarios, right? And those are the realistic scenarios which will combine both the edge cases as well as the happy path scenarios on which we are going to evaluate our agents. In terms of metrics, what are those metrics which we are going to use to evaluate these scenarios on? Traditional metrics like Blue, RUG, BUD score, they are typically what we have observed is not very useful, right? Then there is a newer approach where for each scenario, you create a new rubric. So recently OpenAI released their health bench, where for each scenario, they would have their own rubric and then they would use LLM as a judge to evaluate the response on that scenario. That is okay for benchmarking, but for actual use cases, real world scenarios, that's not scalable. It's just, there will not be, most businesses will not be having that level of human resources to do those, to that level of scenario evaluation, right? So what has been our approach here? Our approach has been to create a metric taxonomy, right? We have created a entire DAG of what all metrics should look like, starting from the task completion and task efficiency to very task specific rubrics, right? For example, in conversational agents, one of the key rubric is shared decision making, where we able to arrive at a decision with consent of both the agent as well as the user, right? And then we go right to the component level metrics. Are we using RAG? Are we using code execution in our agents? Are we using tools in our users? If that is the case, what is the individual accuracy of these components? What is the precision recall of the RAG? What is the word error rate of the speech to text transcription? So again, we are following an entire taxonomic based approach to start from the very top, where we define what is the task completion, the task efficiency, and then going down towards task specific rubrics and at a very core technical component level accuracies. And lastly, across safety, right? Again, some concerns are across the domain, hate, discrimination, abuse. I think that's throughout the agentic AI world, and there is a lot of work going on both in industry and academia on that. Two very, very important safety criteria when it comes to healthcare we have observed is PII leakage and tool misuse, right? Again, this can have catastrophic consequences when we use these agents with our doctors and providers, care coordinators, patients, etc. There are also very specific healthcare concerns like medical misinformation or medical advice. Some of our conversational agents are not supposed to give medical advice. In many cases, like a chatbot or Q&A, they are not supposed to provide medical misinformation. Even if they provide the right citation, the citation might not be credible enough, right? So how do you observe and how do you obtain those criteria and evaluate the medical misinformation is another very important topic of research and execution which we are focusing on. What's our approach here? Our approach here has been to identify what we call as vulnerability nodes, right? Most of the agents and most multi-agent architectures are typically using a DAG type of or a graph-based architecture like a line graph or OpenAI agents. All of them, they have what they call as a graph architecture. What we try to do is identify what are those key vulnerable nodes. That is it the tool execution node? Is it the code execution node? Is it the web search node, right? And then for those agents, we have very specific guardrails built. And not only guardrails, we also have a policy-based remediation and detection, right? So it's not only detecting those deviations which are not allowed, but also on the fly remediating those, right? So that has been an overview of what our approach has been to create agents which are amenable and can be used in a healthcare domain. So yeah, agentic AI development has scaled a lot with different SDKs, but it's the quality of agentic AI evaluation which is critical in deciding how successful we will be solving in those clinical outcomes in healthcare. Thank you.
Okay, let's move to, thanks Taba's great talk. Let's move to next talker, Samuel Rodriguez. Okay.
Hello, everyone.
So Samuel is the co-founder and CEO of Future Health. And he will introduce automating scientific research with AI agents. Let's welcome Samuel.
Hello. Hopefully this. Great. Okay. Hello, everyone. So I'm Sam. I run Future House, and excited to tell you guys what we're up to. So, oh, wow. Okay, so the fundamental problem that we think about at Future House is that biology is too big for humans to understand. Okay, there are 20,000 genes in the human genome. There are 50,000 different diseases that affect humans. There are 10,000 different cell types in the body, and the rate at which we are publishing papers is increasing exponentially, but we do not have the ability to synthesize all the information in the papers, right? And as a result, there are $100 million bills lying on the ground. So this is a tweet from back in November by Matthew Kirshner, who's a friend of mine who thinks about drug discovery. Wow, this is just going to keep doing this. Let's try, let's just, okay, it's going to keep doing it. We're just going to keep going. So, talking about a company called Trace Neuro, which was founded with $100 million to pursue a new drug for ALS. And if you walk through, this tweet step by step, what you will find is that they are pursuing a new target, a drug for a new target for ALS that was identified entirely from publicly available data, right? And that insight that comes from publicly available data was enough to go and raise $100 million, right? So how many other ideas are there out there that are lying on the ground waiting to be found that could each themselves be worth $100 million? And so this is basically what we think about at Future House. What if we could automate the process of coming up with discoveries, right? So given some quest by a human, so the quest can be go and find a new way of treating ALS. How do you find all the relevant data, find all the relevant publicly available data, also find relevant privately available data, analyze that data, generate hypotheses, and ultimately come up with experiments that you can run in the lab to come up with discoveries that then allow you to update the quest. And what we want to do is that we want to be able to have agents, AI agents, that do each of these steps autonomously so that we can just go and make all of the scientific discoveries that are out there waiting to be made. So this is basically who we are. So we're an independent nonprofit. We're based in San Francisco, in Dogpatch. We launched in November of 2023. We have about 25 people, which is divided between, we have a bunch of wet lab researchers, we have a bunch of AI researchers, and we have a bunch of software engineers. And we're funded primarily by Eric Schmidt, although we also have large contributions from other people, including Open Philanthropy, most notably, and several others as well. And so I'm going to walk you through a little bit about what we're doing. Obviously, this is a 10-minute talk, and we've been doing a bunch of stuff, and so I'm just going to tell you a little bit. But basically, there are 4 steps to our approach. The first step is assembling data sets that we can use to measure the performance of our AI scientists. The second is building tools for the AI scientists. The third is training them. And the fourth is then validating the discoveries that they come up with. I can only tell you about the first 2 for time's sake, but yeah, we're doing work on all of these in every part of the stack. So first to talk about data collection. So what does it look like to assemble a data set? This is LabBench. This is a data set that we came up with last year for measuring the performance of language agents in biology. And it basically measures the ability of agents to perform some specific scientific tasks that are critical for being able to do science. So on the right on the left is FigQA. This is a figure understanding benchmark. You ask a question like, what is the most likely width of the entire image? You give an image. It has some annotations in it, so you as humans can infer basically what the width of that image is. The question is, can the language models do the same thing? On the right is LitQA. LitQA is like retrieval of specific information from scientific sources. So you make big data sets like this, and then you go and you measure the performance of language models on these data sets. So this is a figure from about a year ago, which means it is hopelessly out of date. But we haven't had an opportunity to update it, and so this is what we have, showing various different frontier models at that time versus humans on the different tasks in LabBench, right? And as you can see, they are all the models all significantly underperform humans. Now, at this point, on some tasks, the models are actually as good as humans. But on many of them, actually, they're still pretty bad. This is OpenAI's own data. From OpenAI and Anthropic and the others all use LabBench for benchmarking their models. And this is protocol QA, which is one of the problems in LabBench, and showing for different models performance on protocol QA. Humans are about 55%, and the best deep research is like 28%, so there's still a long way to go. So once you have a data set like this, what do? Well, the first thing to say is that actually, this plot is highly misleading because most of these tasks, like being a scientist requires you to use tools, and most of these tasks likewise require tool use, but we're evaluating the language models here without tools. So you should not trust this, or like, this is like fine, but this is not the full story. So the thing you have to do is you have to go and give the language models access to tools. So this is PaperQA2. PaperQA2 is our literature search agent. So you take a language model and you give it access to a bunch of tools like paper search, like the ability to gather evidence from the papers, the ability to traverse the scientific literature. At this point, PaperQA also has access to like patents, clinical trials. It can like see figures. It can do all kinds of stuff like that. And then this is what it looks like when PaperQA is running. This is the alpha version of PaperQA, which is again probably like 9 months old at this point. You ask it a question like, how has the understanding of amyloid beta's role in Alzheimer's disease changed over time? And then it goes in, it searches for papers. It retrieves those papers. And then it's going to go and like within every paper, look for what are the most important pieces of that paper that are relevant for answering the question. Once it selects out the most important pieces, it is going to go and iterate, so it'll search again based on what it found, and then search again, and search again, and search again, and so on, until it is able to come up with an answer. This is similar to what the Frontier Labs have released more recently, like deep research and ChatGPT search and all of these. Similar idea. Key thing is that this, PaperQA is like optimized for the scientific literature, so it has access to full-text scientific papers, for example, which the models generally do not, and lots of other useful data sources like that. But the key question is, once you do this, once you give the models access to tools, how do they perform on the benchmarks that I described earlier? So this is performance on LitQA, which is the literature search benchmark. And what you can see is that like before you give the models access to tools, they perform significantly less well than humans. And after you give them access to the relevant tools, they actually perform much better, right? PaperQA2 is much better than humans at finding relevant information in the scientific literature, okay? So that's a benchmark. How does it do in real world tasks? That's the question we wanted to ask. So we had this idea where like, there are 20,000 genes in the human genome. Previously, there were only 3,000 Wikipedia articles. So we have this agent that can do literature search. Let's just go and write articles for the other 17,000 genes. So we did that. It took about 2 days. It required us executing PaperQA about 100,000 times, analyzing like 1 million research papers, 15 million pages. Interestingly, there are like 2,000 genes for which there's actually like no information in the scientific literature about them, which is pretty cool. And this is what it looks like. You can go and see the articles at wikicrow.ai. They're not on Wikipedia because Wikipedia is like a volunteer-run organization. It's a little bit hard to work with. But you can see them on wikicrow.ai if you want. And then we had PhD students and postdocs in biology blinded evaluate those articles. And what they found is that there are twice as many errors in the real human-written and human-curated articles on Wikipedia as there are in our AI-generated articles. Like we just give them articles from both. We ask them to identify hallucinations, blinded. They find twice as many hallucinations in the human-written articles as they do in the AI-written articles. And so this is like the first hint of these agents being much better than humans at doing tasks that are required for science. Okay, so now we're taking this idea, we're expanding it to like the other portions of the kind of scientific workflow, right? So I'll just give this is just a peek at our data analysis agent. It is called Finch. You ask it a question like, what can you tell me about molecular drivers of cancer metastasis? Using the data provided, you give it access to some data, right? And then it obviously also has access to the entire scientific literature. It has access to all kinds of different tools, right? And it goes, and after like a minute or something, it comes back to you with like a full report in which it goes and identifies findings, provides you with a entire notebook that is with all the analysis that's done, a ton of reasoning, makes you figures, and so on. And so we were actually able in May to publish the first paper in biology with a new discovery in which everything that needed to be done in order to publish the paper was done by the AI. Literature search, data analysis, hypothesis generation, experimental planning, even making the figures. The only thing we had to do was the actual wet lab experiments. That is called Robin. If you want to look at it, go and look at it. But yeah, so I think I will say data analysis, we are not yet better than humans. We are rapidly improving. and it will happen very soon. And so I think it is just like worth reflecting a little bit on like science is going to change very significantly in the next few years as a result of these agents that are like better than humans at doing the things they need to, doing the things you need to do for science. And it's going to be really awesome. It's going to mean that we can do a lot more science. It will also like change the job of being. It will mean that like being a scientist is a little bit different. But yeah, so stay tuned. If you want to use our agents in the meantime, they are available online at platform.futurehouse.org, and we'll be releasing a bunch more soon. So thank you, everyone.
Okay, thanks for Sammy's great talk. And next speaker is No Cong. Yeah. So No Cong is an assistant professor at Stanford University, and he will introduce from code to cell building AI agents for gene editing, stem cell programming, and beyond. Okay.
Thank you. In this time, I'll just dive in. Really pleasure to be here. Today, I really want to share some of our efforts on building highly specialized, but hopefully towards the generally, scientific agents that really, focus on how can we program genome and cells as cures for a lot of disease that we believe will be highly impactful, for aging, for health, for treating disease. So this is our group. We have a mixture of computer scientists as well as wet lab environmentalists that are working together in the group building AI agents and models. So briefly, we have three parts of the lab. The first two parts focus more on wet lab discovery, building gene cell editing tools, how to program immune and stem cells. And today I want to focus more on the third pillar of our lab, which is building machine learning and AI approaches for exciting medicines. And my thought is like really, as most of us know, right, biology is very the slowest, most painful, experimental scientist field, like we've heard from the speakers earlier. And then even though we have computers, internet, I think the progress of pace of discovery in biology, in medicine, has largely stayed the same. I do believe, as Sam was saying, we have an amazing opportunity ahead to take that from a linear, slow sort of growth into exponential explosion. And this is why we're really excited about using AI models and agents. But the problem is, does AI really understand, or at least the current general purpose AI really understand biology? We believe, as really shown by multiple speakers today, is very hard. Because general purpose LM usually have still problem with hallucination, and we are talking about life-saving medicine. It's really difficult to believe in something that might hallucinate a protein or RNA that doesn't actually work, right? And then there are always a lot of problems giving too many options. But in really scientific research, we need a very specific, grounded, explainable solution rather than a bunch of options or maybe an exam-like answer, right? So, and finally, we think we need to put agents into real action, validating lab, generating these cycles, as we also agree. So our approach to thinking about how to build AI sort of workflows for biomedical innovation is sort of laid out here in sort of an acronym ABC. So A is sort of the interface, which is we think that AI agents will really work with human scientists in a variety of biomedical innovation tasks. But the agents are building on top of a foundation of biological aware, biological specific models, like protein language models. We have been working on RNA language models and other type of multimodality models behind the agent. And finally, to really push the whole field forward, we really believe in the value of getting benchmarks, standards that are setting up across different tasks, complex sort of scientific discovery tasks, as pioneered by many groups, including Filter House, right, as we're studying from Lab Bench. So from these agents, models, and benchmarks, I think we can really push the whole field forward. So I want to touch on three components briefly today in my talk. So starting actually, it may be backward from the benchmark, which I actually think is really critical, even for building an agent that actually we know works. We've been building specific benchmarks such as Genome Bench, where we really take real-world discussion, not from a paper or maybe a random sort of a clip from internet. It's really from real genome scientists in their actual research process. They were discussing science, troubleshooting experiments, and this is thanks to our collaborators over 11 years of collection. We got this benchmark set up, distilled from real human experts when they're actually doing research. And the result of that is we can actually use this benchmark to build really strong reinforcement learning approach, shown here, which we call RL router, meaning that because the ability of different models to perform really well at different tasks, let's say some model might be really good at designing RNA or proteins, some model might be really good at experimental troubleshooting, we realize that we might need 2 layers of RL, right? You have the typical RL focused on the model, but maybe we can have the RL over RL where we really understand what models are really great at doing specific tasks, integrate almost like a MOE type of approach where we can raise a router, almost like an open router approach, where we can route the question, the challenging questions to the best model answers to the task. You can see that the RL router at the bottom really outperforms any of the best reasoning models in this genome bench. So I think this, towards building a specialized, really potent RL approach for science, is going to be greatly accelerating our work in building agents. But it needs to start with a benchmark. And then, building on this work, we've started to build agents, such as CRISPR-GPT, which was published earlier this week, where we can really use that knowledge, for example, in this case, from genome biology, genomic gene editing, to really improve our performance for anything that related to CRISPR gene editing. And you can see that it outperforms a lot of the best models that we tested. I'll give you an example of how this would work with human. You can see that we can have a really nice interface where any scientist doesn't need to know how to code, how to do specialized analysis, can just use natural language, interact with the agent. And you can basically lay out your task, and the agent really understands the whole context of your own project, your lab, that really can help you build a workflow, as you can see on the right, based on the need and the context of your own research. So as you understand better of your research, you can really start building a complex workflow, as shown here, to help you to do design, analysis, and all the things that you wanted, for a specific domain task like gene editing. And we think that this will be very enabling for people because you no longer need, for example, the PI to be involved, or you need to find some expert. Anybody can really use the agent, knowing that this is built from 11 years of expert knowledge and know-how. So this is what we think of power is to really scale biological scientific discovery. And so, of course, we want to validate it in real lab. So since this is just published, I won't go into detail, but basically we validated using, for example, a first-year college student that on the first goal of doing genetic experiment, they can achieve 80 to 90% success. We were really happy that on the very first test, everything basically works. And really thanks to AI agents, and there's really no involvement from the professors or the senior postdocs. And building on that, very quickly, we also have been expanding the effort beyond just gene editing. Recently, we'll be working with Dr. Matthew Porteous, one of the leader of stem cell biology and gene therapy. As you know, Dr. Porteous' work is really behind the first approved CRISPR therapy by FDA, Casgevy, and also Graphite, which is a public company working on stem cell engineering. So we really think that working with a leading expert in the field, we can build very potent specialized agents like stem cell GPT here. This is not yet released, but we're hoping to really validate this agent and release it very soon. It's basically building on top of the work we did before, really give you an expert that help you with everything about stem cell engineering, particularly focus on hematopoietic stem cell and induced pluripotent stem cell, iPSCs. If give you one example, the agent actually can design personalized editing strategy based on, for example, SNPs. As you know, all of us share a lot of DNA sequence, but each of us have some small changes called SNPs that are different. So if I only design a general CRISPR or engineering task, it may not work for another person because of small genetic difference. So to tailor, customize the strategy of engineering a stem cell for each person is really a lot of work for human to do. But with the agent, now we can really say it's almost fully automated because it takes in personalized genomic information and design strategy based on, for example, the donor's profile for that donor's stem cell. So this is really, we see how we can scale almost any domain-specific, extremely labor-intensive task using agentic workflow. as shown here for stem cells. And finally, kind of one last part is I want to show you that we are very interested in bringing this agentic workflow to a broader scope of tasks in biomedicine. And one of the work that's already been pre-printed and really exciting to have a lot of traction already is the Biomni, which is the open source work really led by Yuri Ashkov's group at Stanford CS, but we were collaborators along with Aviv Regav at Roche Genentech, is more towards a generalist platform for building these agents for a lot of different tasks. And then we also will be releasing a functional genomics agent called AutoScreen very soon, where we believe that we can use this agent to perform any type of target discovery, functional screening, for example, like CRISPR screens, human genetic GWAS studies, where we can really build a lot of agentic workflow for a variety of tasks beyond just the CRISPR and stem cell. And finally, one last thing I want to mention is that we have found that, as you know, why don't we let AI evolve themselves and try to improve themselves? Like Sam were just talking about, right? Why don't the AI be able to, at some point, get smarter, almost like a real human, right? Learning themselves, almost like an AlphaZero type of approach. So we've been building self-evolving agents like Stella, which is just pre-printed recently with Dr. Mengdi Wang at Princeton, where we really are thinking about if we give the agent access to a lot of tools and approaches, APIs, and very defined benchmarks and tasks, can an agent really evolve their own ability to further improve, almost doing a self-RL? And we found that, for example, even without much fine-tuning or specialized design, Stella can be a lot of the frontier model like Gemini, even Biomni in some cases, using benchmark, really thanks to Future House's work here. So as basically as we've seen, finally, when we have the agents self-evolving, we can now give them more data. So we have been actually using SR glasses and cameras to let the agent see what is actually happening in real lab. And we can see that the agent can now, using VLM, really empower people to understand and guide their lab experiment in real world, rather than just on your computer. So we really believe that this will open up a lot of opportunities. And sorry, I'm a little over time, but one last thing is we do have a concern that how this powerful agent will really impact real life. So we're working on, we just have announced the first biosecurity workshop at Europe this year, and we're really looking for people to be mindful as we're building powerful tools, the security guardrails that we need for dissemination. Thank you very much.
Okay, thanks for Professor Chong's talk. So next speaker is Rose Yu. Rose Yu is an associate professor at UCSD, and she will introduce the grounding foundation models for physics science. And also for the netting talks, you should land for this night. Yeah. After 10 minutes, then as this.
Hi everyone. Seems I'm the only one standing between you and lunch. I'm Rose Yu. I'm a professor at Computer Science Department at UC San Diego. Today I want to share some of the work from our group of grounding foundation models for physical science. So we know that foundation models are very successful and they can enable very smart agents, but still they can make very silly mistakes. For example, if you ask ChatGPT which weighs more, a pound of water or 3 pounds of air, and then you will say 2 pounds of bricks weighs more than 3 pounds of air. Or if you ask Cloud, if I got to the top floor, which is the street level, how many stories does the building have above the ground? And after launching of reasoning, it will still say that the building have 3 stories total above the ground. So one of the fundamental reasons for this phenomenon is that these models are trained purely based on data, so they're only data-driven methods. They lack a framework of physical reasoning. Simply scaling up the model with more data or more compute is not going to guarantee that these models can produce physically consistent and scientifically valid results. Our research on physics-guided AI seeks to address this fundamental challenge by bringing the best of both worlds from machine learning and physical science. So using very efficient inference techniques and expressive models in deep learning, probabilistic models, we can relax the rigid assumptions in physical science and make much more flexible expression of underlying phenomenon. On the other hand, the rich domain knowledge in different physical science and specialized tools such as differential equations and symmetry provide the guardrails for these machine learning models to generate much more physically meaningful predictions. And the ultimate goal is by intertwining physical principles with deep learning methods, we can develop trustworthy AI for science. So now, at the agentic era, agentic AI equips foundation models with various tools. If we think about physical science, mathematical models and numerical simulations are the most essential tools for scientists. Compared to a lot of the agentic tools people are talking about, such as clicking on a web page or playing video games, these tools in physical sciences are extremely expensive. For example, in climate science, when we run climate models to understand the energy transfer from the ocean to the land to the atmosphere, we discretize the entire Earth and solve partial differential equations, and just a single model run would take 6 months. Similarly, for public health, when we wanted to produce stochastic simulations to understand multi-agent movement patterns and forecast the future progression of disease, generating only 100 rollouts would take about 3 hours. So just have a single reward feedback takes such long time. How can we even build agents that can interact with this kind of tool? So that's one of the big challenges here for physical science. These tools are very expensive to run. And then, in order to run these tools, we also need to know the very specialized domain knowledge because they have very different type of interfaces, API calls, and acronyms. A lot of the generic frontier models don't even understand. Finally, because of the missing physics and the gap between mathematical modeling and experimental data, there's a huge amount of uncertainty in the tools. Even with the exact same initial condition, you will get a completely different outcome, and this type of uncertainty will be further propagated with the internal uncertainty of foundation models. So in our group, we have dedicated a lot of effort in building faster emulators to speed up these complex simulations. For example, we built a state-of-the-art global climate emulator that can speed up climate projection from 6 months to a week. And then this is the first model that can generate stable rollout for 100 years at 6-hour resolution. Furthermore, we help domain scientists in epidemiology build fast emulators for public health that enables 100 rounds from 3 hours to 50 seconds. And now this model is being deployed by CDC to project the future progression of public health. Now with the tools, we need to think about how we can interweave them with scientific agents. Even though these faster emulators can speed up simulation, they're still quite expensive to use compared to some of the common tools available. We have to be very careful about how we should use tools for scientific tasks. When we think about scientists solving a problem, we have these tools such as mathematical models or literature search, and we also have years of training that's stored in the memory of scientists. So we only use tools when we don't know the answer or we are uncertain of the answer, and then we try to solve the problem with our internalized knowledge. So what I want to argue here is that when we use tools for scientific agents, we need adaptivity. Here's the results for different benchmark tasks for physical sciences. And of course, like with tool using, we're going to outperform all the frontier models. But what I want to focus on is that if we force a model to always use the tool, then it basically leads the model to be over-reliant on the tools and not be able to generalize to new tasks. And furthermore, there's extra cost comes with using this very costly tools. So the model basically needs to learn when to use tool and how to use tool. It's only when they realize that its internal knowledge is not sufficient to answer some of the tasks, answer some of the questions and solve scientific tasks, then it will start to seek external tools and help its knowledge acquisition. Finally, I want to showcase this project funded by DARPA, which is trying to build a generative foundation model for automated climate science. So here, we're pre-training the model with large amount of multimodal data from both large-scale numerical simulations and rich text data from rich literature in textbooks and research articles. We fine-tune these models for a variety of tasks in climate science and weather science, for example, forecasting, counterfactual inference, and the scenario creation. What's important here is that we have to ground these models with physical laws. So the technique that we developed is called reinforcement learning with word feedback. And the word that we're developing is based on our fast emulator that can provide feedback based on laws of physics. We can use the uncertainty to guide how the model reacts and use these tools, and then to fine-tune this model specifically for domain tasks. And here I want to show a demo of how Genie works in action. Hopefully it works. No sound. No sound. Wait. Is there a sound? No, I don't think it's. That's okay, I can just narrate this over. So what you're seeing here is, okay, that's fine. What you're seeing here is the demo of Genie. So we're trying to build a multimodal foundation model for hypothesis generation in climate science. And on the left is the visualization of the Earth. And then on the right is a natural language interface that you can interact with the agent. So we select the weather bench, a forecasting benchmark for 14 days ahead forecasting, and we select the time and the location we want to ask. Then we ask the model to analyze the data and plot a linear regression analysis for the average temperature, surface temperature. And then model basically generate code using the agentic approach by integrating our specialized tools such as geolocator, fast emulator, and climate simulations. So then you can see the model can generate this kind of plot by retrieving the data and do the analysis in the backend. Furthermore, we can also examine what the code is being generated underneath so that we can provide a layer of explanation what is happening under the hood for this agent. So we can also locate any point on the globe and ask the specialized questions. For example, if we click on this area and then ask the model to generate a meteorological report for this condition in this region, and then the model will then synthesize the knowledge in the literature and the tools available to generate the following report, then we know this is accurate because we're grounding the model with the physics that we have, so it's not completely hallucinating, and we can also examine the code that's model generated to look at the outcome. We can also ask the model to do forecasting. There's a lot of forecasting models out there, but then often require special knowledge to interact with this kind of forecaster. So Genie provides a natural language interface for a system to basically connecting all these available tools like a forecaster and then produce the outcome also in a natural language format. Okay, so maybe I'll just stop here because I'm running out of time. So I wanted to highlight that at the age of agentic AI, the problems in physical science is really proposing the frontier for AI. There's a lot of interesting challenges the current AI system still cannot solve. And I hope everybody can look at this particular domain and all contribute. At the same time, I think the dream, as many of the speakers have alluded to, is that AI and agentic tools is providing new set of gears for AI scientists by working side by side, who can enable AI system to be more trustworthy with these physical principles, and also use the physical principle to help scientists discover unknown knowledge. Thank you very much. And this is my contact information, and thanks for the funding agencies for supporting this work.
Okay, thanks for Rose's talk. So next thing is about lightning talks. So we will use a lot of laptop.
First, we have Herman. Oh yeah, you go first. And the second, we have Sarthak. Yes, okay. The third is Sumicho. Do you have Sumicho here? Okay. It'd be great that you guys can line up in that order. And so, because the slides will be in that order. The fourth will be should be high. Sorry. Oh yeah, thank you. And then fifth will be Simeon. Okay, probably not here. 1, 2, 3, 4, 5. And then sixth will be Xuan Wang. Do you have Xuan Wang? Okay. Yeah, please. And then Zheng Zhong Tu. Do we have? Yeah. Please line up on the edge of the tent. And then. And then next will be Sarunas. Yes. And then Qin Lu. Do you have Qin Lu here? Okay, good, thanks. And Umar. Okay, cool. And then the last will be Bo. Yes. Okay. And Dean Herman, you can start now. Thank you.
Yeah, hi everyone. My name is Hemant. I'm here representing the data science team from Zoox, and we're going to talk to you today about how we use text-to-SQL using a multi-agent collaborative framework to find complex driving scenarios. So a core problem at Zoox that helps unlock our company's vision is to be able to query and search for scenarios that occur in our driving logs. So what is a scenario? If you look at this example here, our robot is approaching a crosswalk, attempting to turn right, and there is a set of pedestrians on the crosswalk. So this is an example of a safety case that we would analyze to see how many times this occurs and different robot behaviors that correspond to safety cases. So the method that we need to do this needs to be easy to interpret for all of our developers at Zoox, and also be able to scale for pretty much any scenario definition that you can think of in our driving logs. So how do we achieve this? So we use a Agentic AI system to represent all of these behaviors as singular building blocks, and then combine them together as saying robot relevant, agent relevant features to get the result. So this system guarantees an increase in developer productivity to use Agentic AI to generate these SQL blocks. We check the executability of the code to make sure the code is actually runnable and gives you the results. We check the correctness to see if it actually matches what you're looking about. The main thing is interpretability, as opposed to what you might have seen with embedding-based searches, where you use like a vector to search against. It gives you as a SQL, so you can find that. And we also validate the code to make sure that our system actually answers a general set of code. So if you look at an example here, a robot is approaching a crosswalk and a pedestrian is crossing in front. We will split that up into robot relevant, which is approaching a crosswalk, and pedestrian, which is crossing in front. And then we combine that with our agent to give queries for each of those things, and then combine them at the end to give a scenario description. This system helps us to scale up these kind of scenario searches for pretty much anyone in the company, and enables us to search for even more scenarios. Thank you. We are at the poster at the back, and if you have any questions, we'd be happy to answer them. Thank you.
Hi guys, I'm from Amazon Engine. So at Amazon's massive scale, we have thousands of employees using millions of devices on our networks. Behind them are thousands of IT support engineers who keep this ecosystem healthy and running. So our team's goal is to make their job easier and make the system more AI driven. So imagine every device on such a network in a company having its own AI support engineer working 24/7 supporting problems as soon as they occur, or sometimes even before they occur. So we've noticed that, and based on studies, that 80% of the cases that employees face, they tend to self-resolve, but often this is based on static documentation and can only guide users to do what to do, but it cannot perform these actions for them. This can often lead to stale instructions and added friction. When an employee goes to an AI assistant, about 43% of the time they have to still go to an IT support engineer, and of the 57 contacts reflected, only 25% get actually resolved, and the rest flow back into this cycle where they have to go through this cycle again. We propose an edge-extended agentic AI system, which is a multi-agent framework that runs on both edge and cloud devices, collaborates autonomously, and maintains this healthy IT customer support system. It's based on at the foundational level is the data and LLM inference layer, where we have all our chat logs as well as Bedrock to support the inference. On top, we propose to add distributed agent registries with access control that control which agent on each system can have access to which cluster. We have diagnostic and remediation tools through MCP that allow these agents to run code on employees' laptops, and also have adaptive memory for personalization that keeps a record on what's going on each laptop. On the second layer, we have local RAG agents that use smaller LLMs to give offline support, and client agents for performing these user interactions and planning through this cluster. At the very top, we also have each device can broadcast its local telemetry and its health status, and also get flight level analytics on the global side. So from a user's perspective, you can imagine they have a desktop app that abstracts out this whole system. But on that app behind the scene, there is a multi-agent framework running that has these important agents, local MCP registries, and a client agent that interacts with the employee. This local cluster can also interact with a global fleet and a global array of agents to solve these larger problems. And that's our problem. For more questions, you can visit our poster just behind the scene. Thanks.
Hello and good afternoon, everyone. I am Sumit Roghatak, working as an AI architect and thought leader at IBM. So we are building AI agents that are increasingly autonomous, fast, and complex. But what happens when our ability to hold them accountable breaks? So this is a challenge that I call as the accountable singularity, and I feel it's fast approaching. It's actually a technical breakpoint in the systems that could make the current safety paradigms like human-in-the-loop oversight and the central logging computationally and economically unviable. So we need a paradigm shift wherein we move the burden of proof from external observation to intrinsic cryptographic self-attestation, which is essentially the concept of verifiable agency. And that's built on top of three important pillars: immutable reasoning through decentralized ledger, cryptographic proof of compliance through zero-knowledge proofs, and automated consequence through trustless enforcement mechanisms. So this framework actually moves us towards creating a truly accountable AI, but there are some questions that we need to answer, which is like, how can we design efficient zero-knowledge proofs, and what are the crypto-economic models for self-governing and resilient agent ecosystems? So I hope to solve these questions through this research, but I would definitely want to know your thoughts on this. Please visit my poster, which is at the end. Thank you.
Hi everyone, my name is Shubhi Asthana. I am from IBM Research and we are working on agentic debugging frameworks for LLMs. Internally at IBM, we have a large number of agents being developed in the areas of IT ops like site reliability engineering, finance agents, as well as SWE coding agents. These agents are having issues in complex tasks, causing errors like hallucination, incomplete traces, as well as tool call execution errors. So, we have looked at the existing debugging efforts in agents and realized that most of these prompt optimization efforts look at the agent's textual output quality. We have decided to go forward into looking deeper at the execution traces of these agents to understand how systematically and strategically the agents are being executed. For this, we have built a trajectory analyzer, TrajTune framework, which is processing these execution traces, dynamically identifying the errors, and then providing revised prompts within certain thresholds to identify failures such as hallucinations, repeated or invalid tool calls, as well as incorrect tool calling logic. We also have a prompt validator, which is looking at the static errors in the agent's output quality and providing structured format in the forms of React or LangChain format. With our agentic debugging framework, we are able to apply on generalized agents in different domains like finance as well as software engineering, and our framework was successful in reducing the hallucinations that occurred during the different intermediate LLM tool calls. With this reduced hallucinations, we were also able to reduce the number of tokens that were required in the agents that enabled us to try out even for smaller LLM models that provided us higher performance. And the most of all, the agents had issues with tool misuse and overloading of certain tool calling functions, which was optimized with the help of our agentic debugging framework. So for more information, please come to our poster, which is at the main stage. Thank you.
Hi everyone, this is Xuan. I'm assistant professor in computer science at Virginia Tech. I'm happy to talk about our recent work on small vision language models as future of agents. So why we need the small models? Specifically, our goal is towards the open source multimodal and small vision language model agents for real-world applications. There are many specific cases where this is particularly useful. For example, if we are in highly data private domains like healthcare or finance, probably people don't want to pass their data to the centralized, say, OpenAI server. And also in some other cases where, say, you want to analyze data in the air, in space, or deep under the sea, there could be a lot of scenarios where you cannot effectively pass data to the cloud to a more large-scale analysis. So small models can be very useful for these edge deployments in robotics, IoT, and wearable devices. So what's the difference in small versus large models, especially in the agentic applications? Small models still lagging behind in certain abilities like tool usage, reasoning, and multi-agent collaboration. We have a recent benchmark called LLM Think Bench, where we systematically benchmark the small models' reasoning capability versus the large ones, and we have many interesting findings. For example, quantization is the most effective way to preserve many capabilities, but they're still lagging behind in many other things. There are many directions to further enhance small models. For example, if we have training signal, we can have a reinforcement gym environment to further enhance it. Or if we don't have training signal, we can have a self-evolution of the models through multi-agent collaboration. I'll be happy to talk more if anyone's interested in this topic during the breaks. Thank you.
Hello everyone, my name is Zhenzong Tu, Assistant Professor of Computer Science at Texas A&M. So I'm happy to present our work on computer vision agent, which is called 4K agent, Agentic any image to 4K super resolution. So what we want to build is basically a generalist on upscaling any image, including some of the natural images, pet photos, old photos, AI-generated images, and some of the scientific image domains, such as satellite images, microscopy, pathology, fundoscopy, and etc. So what we build is a multi-agent system, which we have a profile module that you can flexibly select any mode to restore any image according to some customized use cases. And we also build a perception agent that can analyze the image and make a customized plan on how to restore and clean this image. And the restoration agent is to execute the plan and then dynamically select which is the best result for each step. So more specifically, the perception agent is going to use a multimodal large language model with some expert to analyze the distortions and degradation and make a customized plan. And then the restoration agent is going to try a bunch of tools. We have included 60 tools, all state-of-the-art for image restoration. And then we have a score function to select the best results according to the visual perception for each stage. We also have a face model, because face is usually the most important and most sensitive part. So we have a face dedicated model to restore that. And according to this highly complicated multi-agent plan, we have built a generalist that can restore different variations of image domains regardless of the image degradation. So let's show some results, okay? So here, suppose this is a pretty shaky capture. We can restore this to very crystal clear. Yeah, and for example, you have your pet friends. We can restore it to this very good picture. And you have an old photo captured 30 years ago. We can also restore it to very good, some hallucinations though. And here is an AI generated image. We can pretty grain and plan, and we can recover and enhance the details to very good, high quality AI generated photo. Thank you very much.
Hi everyone, so I'm Ching from the Amazon search team. So today I'm going to introduce a flexible and efficient RO framework for LLM. So RL is the most popular stages these days to fine-tune the LLM after the supervised fine-tuning with the labeled datasets. It allows you to fine-tune with more enriched signals from the actual world. So there are a lot of infrastructure-wise challenges in the LLM given the complex training capability. And Vero is the open source on 2024 October, and it supports various kind of use cases from the real world. And we have a very large user group from both academia and industry. So here is a feature list for what Vero supported these days. We support various kind of algorithms, most popular modeling architecture, and also to improve the training efficiency on both training side and inference side, we integrated with the most modern inference engine and training engines. So to implement your own algorithm, it is very easy to make a few line changes. So for example, the DAPO is the most recent released version we have integrated in the framework, and that has been proven to be adding additional improvement on some popular algorithm like GRPO. So Agentic is the latest feature already enabled in Vero, which with a full list of features such as the server-based asynchronous rollout, multi-turn conversation, and tooling usage. So given its flexibility and efficiency, I'm talking about Amazon Rufus, which thing I'm working on. It is the AI-powered shopping system in Amazon Web Shopping that helps customer to find the right products, and also you can do a lot of shopping inspiration ideas. To build such a very large scale model, we collaborate with Vero open source framework to enable real large model training, as well as a shopping assistant. We are able to interact with Amazon Shopping APIs internally, and we build rich reward services to provide signals to enhance the model capability to help customer to get enhanced experience. All right, that's all. Thanks.
Hello, my name is Omer, and I'm an assistant professor at the Washington University in St. Louis. So in this talk, my main message is that the foundational system security principles can be leveraged to provide strong security, privacy, and safety guarantees for AI agents. So we all know here that AI agents, or Gen AI in general, is very capable, but it also has pronounced limitations. It hallucinates, it is susceptible to prompt injection, it also has trouble understanding ambiguous natural language instructions. And in the presence of all these limitations, we cannot really leverage the promising capabilities of Gen AI. And the fundamental issue here is that the Gen AI's robustness is an open problem, and the progress on it from the machine learning or the NLP side has somewhat stalled. So a crucial question is, how do we leverage Gen AI given its inherent limitations? In my research, I tackle this problem, and my main insight is that when Gen AI is integrated into computing systems, it is integrated into conventional software stacks. And this raises a very promising possibility that Gen AI, that system security principles can be leveraged to reliably control the success and failure modes of Gen AI. Another important benefit that this provides is that it is complementary to Gen AI's robustness. So in case a model is tuned, for example, via prompt injection, the whole system won't crash. We can still fall back on the system security principles. And as a lot of computing systems where Gen AI is reliable have the foundation or the basis of systems, so it also has wider applicability across web, AR/VR platforms, and so on and so forth. If you want to discuss more, I'll be here, and you can also reach out to me by email or social media. My contact details are available on my webpage.
Okay, is this thing on? Okay. Hey everyone, thanks for not leaving to lunch yet. I'm Sean from AMD Research. I'll try to be very brief. So as everyone in the room knows, large language models are really good at writing Python. They're good at writing application level code. What they're not very good at, as the latest Live Codebench GSO benchmark showed us, is they're not good at optimization. Now what's intrinsically an optimization problem is code for hardware acceleration. So we're interested in NPU because it's new and exciting, but all this is true for GPUs, TPUs, FPGAs, what have you. You need specialized hardware experience, expertise, knowledge of domain-specific languages. New chip comes out, suddenly you need to care about the new data type or a new primitive, something like that, right? It's quite challenging for LLMs. You can't rely on base LLMs to do that. So you need agentic solutions. Where you're looking for solutions, you need an eval, like most things, right? So we have a benchmark called NPU eval we built for this purpose. And surprise, surprise, out of the box, large language models aren't very good. It's a challenging benchmark. So if you're looking for a challenging research problem, well, that's one. But yeah, if you want to see how agentic workflows work, we do have a booth upstairs, so we can visit our booth to see a demo how an agent writes code for NPUs. And some shameless advertising, we are hiring, so our group is interested in robotics. If you're interested in physical AI or systems level research for robotics, please do reach out. And we're also always looking for interns. It's a great opportunity to visit Colorado. That's where I started my internship, and now I work there. I live in Boulder. So yeah, contact me if you're interested in any of these things. If you want to learn about NPUs or hardware acceleration for robotics, we're at the booth doing lots of interesting acceleration work. Here's some samples of our recent projects from our tiny group at RAD. If you want to check those out, if you're interested, be my guest. And yeah, visit us at the booth. Thank you very much.
Hi guys, thank you for still being here. This is Bo. We are from Emory University. So imagine a kid is doing a math problem. It's very difficult. For the first time, it may cost him like 30 minutes, 40 minutes, and the kid still cannot do it. But for later, if the kid is doing it for the third time, for the fifth time, he can still do it better. So this is for human. For humans, when we are doing similar tasks repeatedly, we can be faster and faster. This is a human cognitive process. So we are trying to know, can this phenomena still appear for LLMs? So here in this work, we are proposing speed-up LLM to implement and benchmark such reasoning speed-up behaviors. So if we are just doing individual queries for each question, it's no way to be faster, right? Because each question is individual. So we need to add memory mechanism for LLMs. And also, we need to make the reasoning adaptive, which means for those more familiar questions for LLMs, it may cause a lower reasoning cost. So for benchmarking such behavior, we are trying different task similarity from lower similar tasks to more similar tasks. We are trying out different memory method. We are trying out different reasoning method. So the answer to this question is very exciting. It's generally yes. So you can see from these curves, we can see a lot of decreasing curves, which means the LLMs, when it's answering similar questions, its reasoning time can be lower and lower. So there are other key findings. So if the tasks are more similar, then the cost reduction process can be more significant. And also, such phenomena appears consistently in different memory methods, and such phenomena also appears consistently in different reasoning methods. Yeah, that's pretty much. Thank you, everyone.
So we will start the launch session. So however, you can, after that, we will start at 1 p.m. Okay, thanks.
One, one, two, 1, 2. One.
architecturing an open agentic future with open source and open standards. And today's session brings together the thought leaders from foundational infrastructure, and you will have insights from Matt White of PyTorch and the Linux Foundations, Michael Goin from Red Hat, Jason Kim of Anthropic, Suman Haj from Anyscale, Daniel Hansen of Onslaught, and Chitra Venkatesh from Google. And we are excited to dive into the technical details, so let's get started.
Hey, good morning, everybody. So I'm your workshop host for today, Matt White. I am the Executive Director at the PyTorch Foundation and the GM of AI at the Linux Foundation. As mentioned, we've got a pretty great agenda here. Speakers from Red Hat, Anthropic, Anyscale, Unsloth, and Google. And I'm going to just say a few words on open source AI and open standards, and then I think the best thing to do is get right into the talks. So one thing I want to just address up front here is this confusion around openness. We have a lot of folks saying, yes, this is open source, our project open source, our model's open model, whatever. But I want to introduce these concepts of completeness and openness because it helps kind of clear up these muddy waters. So when we look at, and can everyone hear me okay, or do I think I have to really get close to this thing. All right. Is that better? All right. So for completeness, this is sort of a concept that we borrowed from open science, where we talk about, okay, very thorough research papers, you release all artifacts with a model, let's say its weights, intermediate steps, so forth. And then we have this concept of openness, which really boils down to it's open or it's not open. And that follows the principles of open source. So being able to study, use, modify, so forth, for any purpose. And the challenge that we see today is there's a lot of folks saying, hey, this is an open model. It's not really an open source model because it has a bunch of restrictions in place. And so what we want to do is make sure that as we build an agentic future, that future embodies this principle of openness, right? That we're not holding back, that we're not hiding things behind the scenes, right? That we're releasing, particularly in open science, which we're seeing sort of threatened right now, which a lot of labs are holding back and not releasing full research papers. They're releasing technical reports, and we just want to make sure that we stay, faithful to ourselves and our principles, and especially in research, that we release all details and all components, and that's how we can build a better agentic future that's open. So the benefits are, very obvious around, openness, right? Being able to build the sort of modular components that are needed to be able to then work off of and build off of and innovate, and so we can continue to build and build these agentic components, right? And so prototyping and particularly domain-specific adaptation, it takes a lot of time to develop for a particular domain, and when we release those domain-specific adaptations or domain-specific deployments in open source, it makes it a lot easier for others to adopt those and employ those in their enterprises or their organizations. We can't forget about safety and trust, especially in an agentic world. We do need controllability, we need observability. If anyone's spent time trying to debug what's happening with their agent, sometimes it's sort of like a fruitless endeavor. And then safety, in the industry, we've kind of forgot about safety again, kind of also we forgot about security. And so we need to remember that these are two very important guiding stars for us. And then interoperability is going to be a huge thing, right? So we have protocols that are becoming sort of standard now, A2A, MCP, and so forth. But if we don't build standards collaboratively and they're not open standards, then we will have protocol wars and a lot of interoperability issues that will sort of become a problem at some point. So, and there's just one thing I want to mention on open standards. So there's this new paradigm in open standards development, which is developing open standards like you develop open source. And so traditionally, folks would start a small steering group, develop a protocol and then send that to like W3C or ITF for ratification. Now we're seeing standards being developed in the open, which I think is a much nicer paradigm. It creates a lot of transparency. You can engage the community and help work towards collaborative spec development. And so this is how MCP is being developed, right? And so, we talk about, if you have, you have something you want to implement, you create an issue for it, and then engage the community and let the maintainers review it and provide feedback. So I'm good with that. We have like 5 speakers in an hour, and so I want to make sure that everybody has time to speak. And I think the best demonstration of open source and open standards is to allow these project maintainers to speak about their projects. So thank you very much, and we'll move to our first speaker. All right, so our first speaker is Michael Goen, who's a principal engineer at Red Hat, and he'll be speaking on accelerating agent, scalable and efficient inference with VLLM.
I'm not sure. Here we go. Thank you for letting us speak. I agree. Hi everyone, my name is Michael Goen. I'm a principal engineer at Red Hat. I was previously an engineering lead at Neural Magic. We were acquired by Red Hat at the end of last year. We've been working on VLM for over 1.5 years now, particularly on a lot of the performance engineering and inference optimization parts. So yeah, I wanted to give this talk on what is VLM, why is it important for LLM inference, what does it implement, and why is that important for agents? So first, it's important to state what is VLM's goal. It's a pretty simple and easy one: build the fastest and easiest to use open source LLM inference and serving engine. But first, before we think about that goal, we need to talk about what problem is VLM setting out to solve. So it's really, really important to say it's solving batch size greater than 1, and it's targeting data center hardware, the really expensive H200s, B200s of the world. This is unfortunately not the same workload as trying to run a 2-bit model on your laptop serving just yourself. Still use Ollama and Llama.cbp for that. We love them. But when you're talking about this problem in this scale, we need to think about how do you efficiently schedule requests on each forward pass that you're going through the model as these requests are constantly coming in and out of scheduling, like think about serving a web server or a database at scale. We need to really think about scheduling efficiently. And then how do we manage the compute and memory requirements that come with LLM inference, like the very large KV caches we need to deal with long context workloads that agents love. So taking another step back and reminding what LLM inference is and why is this a hard problem. So if you forget about all the parameters and operations, an LLM is a function to predict the next token in a sequence. And to generate text or generate multimodal output, we need to chain together multiple forward passes through the model to generate each token in succession. So you see on the image on the right, sort of the yellow tokens are our input or our prefill that we process on the first step, and then the blue tokens that we're building up on each time step as we go down are our output or our decode tokens. And so a single request can take hundreds, thousands, tens of thousands of steps or forward passes through the model in order to generate all the tokens you need in your response. And so this obviously isn't efficient if you need thousands of requests for a single request. So how do we batch these requests together? So when you talk about batching, really kind of before LLMs, static batching was really popular. However, because of these autoregressive workloads can go on for very different amounts of lengths, you have some requests that finish in 10 tokens, some that finish in 100,000 tokens. If you batch all the requests together and keep that static, you end up with a lot of empty space and wasted work as you're going through these time steps here where we've already hit our end tokens and we're just haven't scheduled anything else. So obviously one of the most important things that were implemented was continuous batching, so that when a request finishes and we have our static batch, we can just insert in new requests that can pre-fill and run and start fitting inside the existing static batch. Second challenge is KV cache. So KV cache is the idea of if you keep around these two key vectors for each token, keys and value vectors, you can skip a lot of computation for all the previous tokens that you've seen in your context. And now the bulk of your computation is just on the new tokens that you need to process and are generating. This is obviously a great optimization, but it takes some memory cost. And maybe you only need 1 megabyte for each token that you have in KV cache. But when we're talking about 100K context, 1 million context, that turns into gigabytes. And then you talk about wanting to batch requests together, that turns into hundreds of gigabytes. And in large production scenarios, the KV cache ends up taking more space than the model parameters themselves. And so what VLM introduced in order to make this management easy is paged attention, which is an attention algorithm that is based on, virtual memory, kind of taking the idea from operating systems, that's where the V in VLM comes from, and introducing this block table, which gives us a layer of indirection so that the request thinks it has tokens in contiguous memory, but in actuality, these can be stored completely discontinuously in memory. As you can see here, we have 2 requests that are running. They have their own block tables. They think they have their own logical KV blocks. But in physical memory, these can be interspersed and reused even across requests. So that was the start and the genesis of VLM. You can see the paper on the left. And it's been a very rapid 2.5-year journey now of 50,000 GitHub stars, over 1,000 contributors, a ton of usage by the frontier model labs, by industry, by researchers, and it's really served as a great catalyst. And so I'm going to talk about why it has become that important catalyst. Of course, page attention fits in the optimizations there, but there's many other types of inference optimizations that have arisen since then, like chunk prefill, distributed inference, multi-layer batching. VLM has kept up in implementing a lot of these. But then, of course, there's the 100+ model architectures that VLM supports within this software infrastructure. And then, of course, the different hardware providers have taken the opportunity in order to use this software interface and build their hardware backends in order to harness and fit in this abstract software layer. So now I'm going to dive into a few optimizations with VLM and, what are we doing these days? So a really key one is automatic prefix caching. This is actually a really elegant optimization that comes from paged attention naturally. If you do like multi-turn conversations or RAG where you're reusing shared context from requests, page attention just gives you this automatically because you already have the KV blocks in your memory, and for the next request you just fill in its block table with the blocks that are already there in memory. So you can skip a lot of time in prefill, and this really helps improve both time to first token and your token throughput as you get higher and higher cache hit rates. This also works for multimodal data. It's a really powerful idea. Another key idea is quantization. You're probably familiar with this from other projects that mostly focus on weight-only quantization. We also focus a lot on activation quantization, so quantizing both the weights and the activations, allowing us to use those low precision tensor cores and get more compute, more throughput out of the server that we're serving. And you can see we're sort of comparing unquantized versus 4-bit weight-only quantization versus 8-bit activation quantization, and as we scale the queries per second or users per second, we're able to serve a much lower latency and serve more users within our latency requirement with these types of quantization. And of course, KV cache quantization. We want to shrink the KV cache so we can do more batching and have efficient inference. Next, there's also speculative decoding. There's many methods to do this, but generally it's the idea of using some cheap way to generate many different candidate tokens and then passing those candidate tokens in parallel through your target model and then reading the output log probs to understand would the model have predicted these tokens anyway, and if they did, great, you predicted 3 tokens at once instead of 1 token at once. This really helps in the low batch size regime, pushing latency even lower and increasing your tokens per user per second, which is really critical for coding agents, for anything that you want to get a response faster, get tool calls faster, all those great things. And of course with VLM, you're not choosing one of these optimizations, you're able to compound and stack these optimizations together. as a system, offering compounding benefits. Now all those optimizations are talking about single node inference. VLM can of course go distributed, distributing your model across devices on a node and even onto multi-node cluster scale inference. So I don't have a lot of time, so I won't go over different types of parallelism, but we have tensor, pipeline, expert, data parallelism. These are all useful in different scenarios. And again, VLM can mix these types of parallelism together where you would like to do so in very different workloads. For instance, it's very different. You want to use tensor and pipeline parallelism when you're hosting a dense model like Llama 405B, but you would much rather use data parallel and expert parallelism when you're hosting a very fine-grained, sparse mixture of expert model like DeepSeek v3. And finally, there's the idea of disaggregated serving, where we can actually separate the prefill operation from the decode operation. This is a really important operation for like production usage, because this now means new requests coming in are not going to affect our latency or our sort of user metrics as we're decoding. Prefill is very, very compute-bound type of workload. Decode is much more memory-bound. Because we have less tokens we're processing, we're reading KV cache, where we don't have that great of a batch size. So that's all I wanted to cover really quickly. Only had 10 minutes, so sad. But hopefully you learned some, and happy to talk afterwards. Thanks to the over 1,300 contributors we now have in the project. It's a pretty insane metric. Yeah, check it out on GitHub. There's several other projects under the VLM project, LLM compressor, AI bricks, production stack, many other things. And please get involved. Check out the issues, check out the PRs. Let us know on GitHub if there's some feature you really want. Join the Slack and join office hours. We host these bi-weekly office hours that let you know what's coming, what's new in each release, and also have special topics with people from the community presenting on what they do in VLM. So that's all. Thank you.
All right, thanks, Michael. Our next speaker is Jason Kim from Anthropic, speaking on MCP as a foundational protocol for agents.
All right. Good morning. My name is Jason Kim. I'm an engineer from Anthropic, and I'm here to speak about MCP. Thanks to Matt and RDI for hosting in this very crowded but nicely stained glass room. Anthropic has many UC Berkeley alumni or people who are associated, and so I won the battle royale internally to get to speak this time, but surely I won't be so lucky next time. In today's talk, we're here to talk about MCP as a foundational protocol for agents, and we hope this will tie into a lot of the other sessions that you're hearing throughout the day as well. Claude made most of these slides for me with MCP servers, so hopefully there are no surprises, but if there are, surely we'll discover them together. Before I really get started, I think it's kind of important in these talks to try and say the most important thing at the start and at the end, so that if you get a really good push notification in the middle, you still sort of got 90% of what's going on. I think the most important thing is sort of a request from Anthropic and from the MCP community. This is a newer open source standard, and we'd really like your participation. Read the docs, implement it yourself, PR against the spec, against the reference implementations, join the Discord, become a maintainer. These are all things that are helpful, we hope, to everyone, and so we'd really sort of request your feedback and whatever it takes to get involved. All right, so let's talk about MCP. Why are we doing this necessarily? The premise is that we believe, and I think most people agree, models are only as good as the context provided to them. Put another way, Anthropic is an AI safety research lab. The first public product we made was a powerful family of large language models called Claude. We have a number of tools that use Claude as well. But something we're finding lately is that if we have to make a trade-off on incremental benefit, it seems better to spend time giving models context rather than making the base model just a little bit smarter. Actually, I think this concept sort of applies to humans as well. Think about if you were going to hire me to work on your company or your project. it's probably better for you to just hire me now and give me a week of onboarding than to say, like, Jason, go study for a week and make your IQ like 2 points higher. This specific context is really important, and so we want to design MCP to make it easier to accomplish this task. This task is in service of this overarching agentic implementation that you've heard a lot about. It was mentioned in the keynote that just happened before this, before we all sort of like ran up the stairs and came here. As part of giving context to a large language model, what do we mean by this? We mean some of these purple boxes that are at the bottom. We want to give the models up-to-date data that it can retrieve in service of a request. We want to give it tools so that it can call and affect the environment around us. And we want to give it memory so that it doesn't make the same mistakes over and over again. If you've watched early versions of Claude Plays Pokemon, you know why memory is so important. We spend a lot of time sort of getting trapped in these trivial cases. And so how does MCP solve this? We've designed MCP to be an open protocol that standardizes the interface between AI-based applications and agents and the context that we're trying to give them individually. Again, context meaning tools, data sources, interfaces, possibly even other models or other agents themselves. We believe using MCP and adopting it more thoroughly can help us speed up this integration process. We're always working on security, which has been quite core to Anthropic's mission and has roots both in the open source and the enterprise community. And frankly, one of the most exciting benefits is to MCP is to allow us to take advantage of the growing community around us. Every room today is so full, and the registration line was so long, and there's so many people online, and it would be a shame if we couldn't take advantage of the things that we're building if it's shareable, if we can implement them in each other's projects and pass those back and forth. The sharing thing is a little tricky because before MCP, we had a lot of parallel development. And I think this would happen within project teams, within companies, within customer groups. Everyone would go ahead and build their own implementation. So you'd see something in a session and you'd say, this sounds really cool. I've gone and built a project with Claude. I wrote some prompts. I did some API plumbing. I handled authentication. Maybe I wired up a little bit of a test set. And then if anyone wants to do this again, they sort of repeat this process in a vacuum, right? It's like we're never talking to each other except to share weird examples of things that went out of bounds. The advantage to MCP, we hope, is to allow for standardized AI development. There's two parties, so to speak, in the MCP ecosystem. MCP clients, which make requests and connect to these external sources of context, and MCP servers, which are the ones that nominate and provide this context themselves. We've already been doing a lot of this context providing manually. If you think about times you've hooked up a database or an API or a local file system tool to Claude, these are all examples of context that we provide on the MCP server side. And the hope is that we can make these things usable and reusable rather than having to rebuild this thing every time something changes in the space, every time a new model is made available. We know from past track record these changes happen quite often, and so having this approach for standardization we hope will make it easier for us to adopt. What can you do with MCP? I think there's a lot of examples, and I'm sort of interested to see yours, but one example we'll look at here briefly is providing this external context for things that models might know. We can assign Claude tickets in a software engineering context, which you might have seen if you've used Claude Code. And in this case, we can allow Claude to do things like look at our intercom tickets, look at underlying linear issues, reach out to the code base, author commits. These are all actions that Claude doesn't have built into it necessarily, but it's interacting with the world around it. And this type of MCP server approach is the way that we hope we can provide this sort of external context, taking advantage of what other people have built and specialized in. Linear or Intercom or GitHub or whoever, they might have already built an MCP server, and we want to borrow from that so that we can focus on what we want to build ourselves with an LLM. When I was building this, Claude was worried that we might not have internet in this room, so it gave me a screenshot of the same thing as well. We were prepared. So we won't do a full deep dive because of time. I think as I meant what I said up front is we do really want you to go read the spec, read the reference implementations, humbly give feedback to the community on ways this can be clarified. But I do want this to sort of get you thinking perhaps of how this might mesh with the other speakers and the other sessions you might hear today. We talked about this difference between MCP clients, which sort of invoke these context actions, and MCP servers, which expose these actions to us. These are all sort of areas that you might sort of have gone through in your own approach. And so, these are options that you have in terms of borrowing from MCP-based components today. I think we've sort of talked about this before. There's room for people on both sides. Building a client allows you to connect to this network of approaches that other people might have already made available. And building a server allows you to sort of expose a best practice or an interface. If agents are going to use your tool or service or backend or front end increasingly often, you might want to give them guidance on how to use it the same way you would give humans guidance as well. So we're authoring approaches for agents as well as for humans. We're always doing new things on MCP. This is the spec revision from last month. We're probably about due for a new one, so stay tuned for more details. You can read about this as well. And in fact, the place to read about this all that I keep referencing is here just for sort of specific reference. I think I'll sort of close this by going back to what I said at the start. Remember the most important thing. We really do want your engagement as much as possible in terms of joining the community, interacting with the reference implementation, giving feedback on the spec, joining the Discord. MCP is much bigger than Anthropic at this point in time. The success of it is going to sort of involve everyone in the community, but if there are things that Anthropic or myself can do somehow to make it easier or better for you to interact with the MCP spec, please do let me know or let us know. I think this is sort of the main goal we have in mind, and it'll be exciting to see what we can build and what the spec will look like in 2 or 3 months from now. So looking forward to it. Thank you.
Thank you, Jason. Our next speaker is Sumanth Hedge from Anyscale, and he'll be speaking about Ray Scalable Agent Infrastructure. Thanks.
Okay, great. So, hey everyone, I'm Sumant. I'm a software engineer at Anyscale, and I'm going to be talking about Ray as scalable agent infrastructure. More specifically, I'm going to talk about training as well as deploying agents with Ray. So, as you're all aware, we've seen some great progress in post-training this year, specifically around using RL for training models for reasoning as well as agentic tasks. 2 great examples we've all seen are DeepSeek R1, which achieved great progress in reasoning with RL, and also Deep Research from OpenAI, which was an agent for multi-step research, again trained with RL. We've also seen some great agent applications this year with Claude Code, Manus. More recently, we had OpenAI bring out their agent. So I'm going to be talking about both of these components, how you can train as well as deploy agents. Before we get started, so Ray is an open source project that I work on. It's built around scaling compute-intensive AI workloads. We have a great community with more than 50,000 developers and more than 1,000 open source contributors from leading AI companies who are working with and contributing to Ray, such as Canva, Apple, Meta, OpenAI, etc. Okay, so I'll largely focus on training and specifically training agents and post-training with Ray, but I'll also get to deploying agents at the end. Okay, so if you look at open source libraries right now for post-training who have some focus on scalability, they're all built on top of Ray. So post-training right now runs on Ray, and if you look at libraries like OpenRLHF, Whirl from ByteDance, NemoRL from NVIDIA, and SkyRL, which is a newer project that I work on, all of these are built on top of Ray. Before we get into how we're using Ray for post-training, let's try to understand why large-scale RL is hard. Broadly speaking, you have 2 components, the trainer and the generator. And if you go one level further, you actually have 3 components in RL, the trainer, the inference engine, and the environment. And you typically have like specialized frameworks that you're using for each of these. So you'll use FSDP maybe for training. You'll probably use something like VLLM for inference. And you'll be scaling these in different ways. You'll also have to now manage sending data around these different components. So for example, rollouts from replicas of your inference engine to your environment, and then getting observations back. And then once you've actually collected like maybe a multi-turn trajectory, you'll send these to your trainer, and you again have to deal with like maybe multiple models in your trainer for your final optimization step. So all in all, you have a lot of these moving parts, and we'll go into how Ray can help manage this complexity. Before I go into the details, I actually want to take a step back and give some background on some of the core APIs of Ray. This is going to be a bit different, but these basic building blocks that I'll show here are how we're going to actually build complex applications like scaling post-training. So what I got here is actually two simple functions around reading an array and then adding them up with NumPy. And the way you'd convert functions to Ray tasks would be to use this Ray remote decorator, and then you'll also change your function call to use this remote keyword. And what could happen is, for example, you could have the reads run in two separate nodes, and maybe the computation run in a different node. And the return values from these function calls are object references or futures, so you would resolve these with a ray.get call. Similarly, you can also look at translating like regular Python classes to Ray actors, and you'd use the Ray remote decorator again. Lastly, you can also add in resource constraints for your tasks and actors. So for example, your inference actor can request 1 GPU, and Ray will appropriately schedule this on a GPU-enabled node. Okay, so again, these are like low-level distributed computing APIs. We're going to now like tie this back into what we're interested in, which is RL. The main place where Ray fits in here in terms of training is in orchestration. So Ray will handle setting up these different processes, managing, scheduling these on the resources that you want, also around handling data communication between these different components, and also things around auto-scaling and fault tolerance. So what I've shown here is how you might have set up your training, inference engine, and environment components. You can probably have Ray actors for each rank of FSDP that you're managing for different models. You can also have a Ray actor for managing replicates of VLLM in your inference engine. And you can also have Ray actors for scaling out observations in your, for getting observations from your environment. Okay, I will also actually look at some high-level training code just to like kind of show how like Ray has simplified managing this data flow in RL. So again, we're dealing with like regular Python classes here, and we'll convert them to Ray actors with the Ray remote decorator. And then you can instantiate these and with like maybe some specific resources, and also scale, like put down your like desired world size in some sense. Before we go into how maybe training might look like, I've defined this tiny like helper class here called an actor group just to make writing down the training loop easier. This is essentially just instantiating a group of actors, adding some specific options, maybe around scheduling it on a particular set of GPUs in your cluster. And then there's this special forward method, which is around handling a batch of data, chunking these to send over to your data parallel workers, because let's just say we're doing plain FSDP, and then you're going to collect the results with array.get. Okay, this said and done. If you look at how we could write down our training loop now, this is how like code might look like in a driver. This is a heavily like oversimplified view. But for example, what you could do is you could have your input batch of prompts that you could send to a similar inference actor group. And again, you would be slicing these and then sending them over to specific VLLM reactors, and then collecting the results back into the driver. And then you would send this over to a different set of reactors in the environment actor group, which could be scheduled on a different set of nodes. And you'd collect observations and rewards back to your driver. And then finally, you might proceed and get your full trajectories, and you'll do something similar for components in your training. So you'd maybe have a critic actor group, and you'd perform a forward pass with the forward method that we described. And you can see how you're able to actually express complex data flow that I just talked about before with Ray. The single controller model where the driver is orchestrating training at each stage is also pretty intuitive to reason about, and you can iterate quickly with different ideas. It's also highly flexible. So the setup with like maybe FSDP actors that I showed there, you could actually swap that in with maybe say a deep speed or Megatron, while keeping your training code simple and also keeping your code focused around FSDP, just just managing around that rank and not worry about the higher level orchestration. You could also maybe change things around different backends, etc. Okay, so we've gone into details around training agents. I'll also talk very briefly around deploying agents with Ray. There's, again, a lot of complexity here. I won't go into too much depth because of time. But these are some user complaints that Anne Group had talked about in Ray Summit last year. And these are things around observability, around not having enough traffic control for heavy workloads, and also low GPU utilization. We can use RayServe, which is a library around online inference for a flexible, scalable, and efficient computation. It's Python native. You can mix business logic and machine learning and iterate quickly. And you get all the benefits of building on top of Ray with flexible scaling and resource allocation, etc. There's really two aspects as to how you could deploy agents with Ray. The first is around deploying the agent itself or deploying LLMs with the RayServe LLM API. What I've shown here is an example for actually serving DeepSeek R1. You get an OpenAI compatible API. You can let RayServe handle scaling and load balancing. You can scale to massive models, like I just said, DeepSeek R1. And you also get great observability with RayServe. The other aspect of deploying agents is deploying your tools itself, and you can also do that with RayServe. The example I've shown here is around deploying a remote MCP server and having RayServe handle scaling that for you. So again, the same aspects we talked about around auto scaling, load balancing, observability can again tie in here. And there's more details that I haven't got into, but you can read our official examples on this. But you can basically also have more complex composition of multiple tools, etc. And yeah, that's about it. We'd love to see more of you building and deploying agents with Ray. And it would be great for more of you to get involved in the Ray community. Thank you.
Thank you, Sumanth. Our next speaker is Daniel Han Chen, co-founder and CEO of Unsloth. He'll be speaking about training agents with reinforcement learning. Thank you.
Okay. Yes. Oh, yes. Okay. Yes. Hello, everyone. Thanks for inviting me, and yeah, excited to be here. So today I'm going to talk about training intelligent AI agents with RL. My view is RL is the next. Well, it is the next big thing for training any single agent that you like. So for people who don't know me, so I'm part of Unsloth. We help contribute a lot to the open source community. So last year we fixed a gradient accumulation bug fix. We helped introduce something called async gradient, gradient offloaded gradient checkpointing. We also work with multiple teams across the entire world, Hugging Face, the Gemma team from Google, the Llama team from Meta, Mistral. So essentially what we do is we fix bugs behind open source models. So once you get a model on your local device or serve it in VLLM, we essentially fix the bugs but behind the scenes. For example, we fix bugs in Gemma, Llama, Mistral, Phi, DeepSeek, many other models. And we have, I have a Twitter account if you want to follow that. I tweet about, the latest research and stuff like that. So definitely follow me on Twitter and stuff like that. And also, post about, possible model releases, for example, or, bugs in the models as well. Some other stuff that we do, we fixed a few bugs in Phi 3 and 4 by Microsoft. Multiple Llama 4 bug fixes. Now it's actually a very good model, so definitely try Llama 4 out. It's pretty good. You can run Llama 4 on your local device now, using Llama CPP, for example. We recently helped the Qwen 3 team on Qwen 3 Coda and other models. We do have a GitHub package as well, so we have 40K styles in GitHub. We essentially make fine-tuning and RL much more efficient. And we have lots of free notebooks. Please use Google's free GPUs. They have a lot, so please utilize them. And we have 10 million monthly downloads on Hugging Face. So that's our GitHub package. Definitely check that out. And yes, again, please use the free GPUs. So so today is about RL and stuff, and how is it related to agents. So in the old world, you will have like a final model. This is probably like a ChatGPT, a Claude, a Gemini. And so the goal is you start from a random initialization of weights, right? So like some random numbers, 1.4 trillion parameters, just random numbers. And the goal is to get to the green dot. And so imagine this is like some, 1.4 trillion parameter space, right? This is like 1D, but like, okay, 2D. But like the goal is imagine this is 1.4 trillion parameter space and you're trying to move from the random initialization all the way to the green dot. And so the question is, how do you do this? And that is like just optimization, right? That's like gradient descent and stuff like that. We don't want to do that though, right? So like essentially we have found some tricks to make this faster. So the first step is pre-training, where essentially you can train to predict the next token. And so this is like maybe 13 trillion tokens, 30 trillion tokens, and you move from the black dot to the, the bluish dot, or whatever that color is. And that's called the pre-training step. And then we essentially then fine-tune the model with supervised fine-tuning or instruction fine-tuning to create ChatGPT or like a Claude or a Gemini. So the problem is if you just have a pre-trained model, it's kind of useless. It needs to follow instructions. And so that's the next step. This data is like, much less. It's not like 13 trillion tokens. It's much less. And then we do something called preference fine-tuning, or like DPO, RLHF, and stuff like that. This essentially aligns your model to respond, more favorably to like some requests. Like you don't want it to like randomly spill out some random instructions. And then finally, there's like this new paradigm called RLVR, where you want to do reinforcement learning with verifiable rewards, where you have like some tasks that you want to do, like, good, you want to have the model solve math equations or like, do coding. You want to like essentially make the model output this more correctly. And so you do this final step, and that's where you get the green dot. So that's the final model. There was a new paradigm recently where you want to skip, actually, from pre-training all the way to the green dot. So this is like you bypass the entire process. My view is probably not a good idea. You should probably, still do the top parts and not bypass the process. The main reason is because this is actually quite inefficient. If you do want to do this, okay, fine. But my view is like you should do the top part still. Mainly for efficiency reasons. So like my view is like all of AI is all about efficiency. You could start from the black dot and go to the green dot directly, but you'll wait 1 million years. So like you have to like, do these like special optimization tricks. So in terms of RL and like, agents, imagine that you're like, in this Pac-Man game, right? So like, this is how I like to explain it. Like, you're like, essentially you're like, the yellow dot, you can move left, right, up, or down. So you have 4 actions, and that's the action space. You could eat like a cookie, and if you do eat a cookie, you get a positive reward. But if you encounter one of your enemies, you'll get a negative reward. And so the goal of RL is to like, how do we maximize the best possible action and maximize reward, right? So how do we maximize the reward in this environment? And the difference is for ours, you actually don't know the best answer. For example, if you wanted to do normal fine-tuning or like some normal supervised fine-tuning, you already know, oh, let's just, avoid the, enemies. But in RL, you actually don't even know that there are enemies. You don't even know that there are cookies. So the goal is like, you want to move in this environment automatically somehow and maximize the reward. A more concrete example is like, pretend I have a question, what is 2 plus 2? Okay, so like the question is, what is 2 plus 2? You have a pre-trained model and it will spit out, A, B, C, D, -10, infinity, I don't know, dog, cat, anything, right? So like the correct answer is obviously 4, right? So like the question is, how do you force the model to output the correct answer, 4? So my view is like RL is kind of like luck is all you need, patience, just wait. So essentially the model will learn just by waiting. So you wait. It says A, it says B, it says -10, it says E, it says 3. Wait a second, 3 is closer, right, to the actual answer. You want 3, so you reward 3 a bit more than the rest, right? So like, for example, if you output a D or B or cat or dog, you will give a very negative reward. But if you output like some sort of number, you'll get some reward. And if you output a number that's very close to the answer, you'll get actually much higher reward. And so over time, you'll get like -100, infinity, 10, and then suddenly you'll get 4, right? So like, maybe after 10 days, you'll finally get the answer 4. And then the goal of RL is, okay, I see this good answer, I want to maximize it. And so the algorithm kind of like learns to maximize to get the correct answer. And so that's kind of like, my point is like in R is kind of like just patience and luck. So like the goal is like most likely like large model labs, their view is like, okay, let's just wait for the model to learn. Maybe we can get to AGI. It's plausible, possibly. So the trick is your probability of the correct answer must be more than 0. If it's always 0, you're not going to go to AGI. But if it's a little bit, like 0.00001, you might get to AGI. So I think that's their view. So like in terms of algorithms, the most popular algorithm in the olden days was PPO. So PPO has like 3 different models. There's a reward model, there's a value model, and then there's a generating policy and the reference policy. Well, technically 4, but I would just say 3. The trick is we have this new algorithm, GRPO, where we delete some models. This is all for efficiency reasons. Like, remember I said before, AI is all about efficiency. The whole goal is to reduce memory usage. So for example, we replace some parts of a ground truth reward function. You don't need a reward model anymore, it's gone. You can delete the value model, which estimates the average reward, gone. And this seems to work well due to DeepSeek R1 released this methodology. You don't just need to have like a reward function. You can actually do many things in the blue box over here. You can do LLM as a judge. For example, you can actually call a language model to actually verify if the outputs are good or bad. You can do regular expression checking, you can do format checking. You can actually execute code on your device. Does this execute or not? And so these are the reward functions you can actually use in replacement of the blue box. I would say like, my view is like, large model labs, their view is like, can just use LLM as a judge. Just call the model to verify if the answer is good or bad, and just keep scaling this, up to infinity. And maybe you can get AGI, maybe. But this is kind of like the setup for, modern RL systems. For GRPO specifically, the formula is a bit more complicated. I don't actually want to show the formula. I normally actually like showcase this formula is a bit better. So the goal is you want to do the action that is much better than average. So you have to actually minus the average reward. You can't just like optimize reward. You actually have to minus the base reward. So there is another thing called rollout or inference sampling. How does GRPO actually work? The trick is you want to utilize the LLM itself. Right? So like for example, you ask the question, what is 2 plus 2? You ask the language model to generate 4 samples. Right? So it could be 0, 1, 2, or 4. So it generates those four things, right? What we want to do is we want to reward the actual correct answer with 1, and the rest is 0. Right? So like the other answers are bad, and 4 is the correct answer. And then we take this, z-score, or like we minus the mean divided by the standard deviation, and we use this as the actual reward. And why is it called group relative in GRPO? It's because you don't just do this once for one question. You do this more for many questions, right? So for example, what is 2 plus 2? You do 4 rollouts, right? You do, what is 4 plus 4? You do 4. Create Python code, you do 4, right? So like you combine this all together in the RL system, and then that's why that's called group relative. And so there's actually many new research papers talking about like how to make GRPO better. Why is pre-training better than other things like and why are the models easier to train of RL? There's many papers on this as well. Yeah, like a recent paper, Spurious Rewards. Highly recommend to read it. And we do provide notebooks for you to like utilize RL and to make agents much more better. For example, like we show you how to like do formatting. We show you how to make reward functions. The most important factor for reward functions is please do more experimentation. And there is a very common trend like don't just do RL first. You have to prime the model or do warm up with SFT. This allows your model to like learn the format first. So a big problem about RL is it just gets stuck in learning the format. So if you do RL warm up or SFT warm up, it will like skip that process. Yeah. Be careful with exact matches of regular expressions. One of the biggest problems I see with RL is when you do regular expressions, they don't work. So please manually verify if it's correct. Very common problem. And also, like I think that's very, I normally like to advocate is like distance scoring. Do not just score a reward as 0 or 1. Try to make your reward function as distance based. For example, 2 plus 2 is 4. If it's 3, you don't just give it a score of 0. You should give it like a score of some score, right? So 3 is better than like minus 1,000. Yeah, and so we have lots of notebooks on our GitHub repo. Definitely check that out. Yes, lots of notebooks. Yes. And yeah, if you want to collaborate on anything, definitely reach out to me. And yes, I have stickers afterwards. So, after the workshop and stuff, if you want to catch me up, yeah, I have stickers. Thanks a lot for inviting me.
Thank you, Daniel. And I would recommend everyone follow Daniel. I'm pretty much convinced he doesn't sleep. There's a lot of great tutorials online. And so our last speaker is Chitra Venkatash, product manager at Google. and will be speaking on A2A, the future of AI agent collaboration.
Hi everyone, I'm Chitra Venkatesh and I'm really excited to be talking here about agent-to-agent protocol and the future of agent collaboration. I'll be talking about 4 topics. The first, what's broken in today's agentic ecosystem and what are the challenges and how we are addressing it through A2A protocol. Thirdly, I'll be talking about core features of the protocol, and lastly, I'll leave you all with some resources. So let's get started. What's broken with today's agentic systems? To talk about this, let me take a boilerplate example. An example of a trip planner. Typically, assume you have no agents right now. What would you do to plan your trip? You'll probably go to 3 or 4 websites or services, and maybe you use one for booking your flights, one for hotel reservations, one for your activities, and so forth. Now, imagine a world where each of these services come to you and they say that, hey, we have an AI agent that can offer these services. Wouldn't it be great if your flight agent could talk to your hotel agent and then say, hey, what's the check-in time? And based on that, I can reserve the flights. Unfortunately, as developers, we're not able to focus on this aspect of collaboration. Instead, we often find ourselves in cycles of these questions. Hey, which frameworks are these agents using? Where are they hosted? How do I discover these agents at the time of orchestration, and so forth? And if you're a provider, you're wondering, how do I make sure that people discover my agents, they know what my agent is capable of doing? If I have auth requirements, how do I make sure the other person knows about this, and so forth? This is exactly where agent-to-agent protocol comes into play. Without A2A, these agents are great, but great in isolation. They cannot work together. They cannot collaborate. With agent-to-agent protocol, we ensure interoperability and secure communication and collaboration between these agents. So let's talk a little bit more about the core features of the protocol. Firstly, agent-to-agent protocol is an open standard. It's designed to enable seamless communication and collaboration between agents, making sure that we have no more silos. And going back to our scenario of the trip planner, we're making sure that all those disparate agents are able to talk together and communicate. The key features here are secure collaboration, task and state management, negotiations, and discovery. Let's delve into each of these features a little deeper, and I'll be using the same reference again and again about the trip planner example. In terms of discovery, A2A agents explicitly list all their capabilities and skills using an agent card. Now, this agent card is a JSON file that's available at a well-known URL in the agent's domain. It's almost like a business card. It tells you what the agent is capable of. It can tell you whether the agent can stream, auth requirements, and so forth. So in the flight hotel example, let's say the flight example is looking for agents that can answer the question about check-in times. It's viewing agent cards of different agents, and it finds the hotel agent, and it sees that the hotel agent can probably complete that task for it. Next, once that discovery happens, the next point is negotiation. Agents are supposed to collaborate. They are not supposed to be wrapped as tools. It can be very limiting to agents. And this is where, again, agent-to-agent protocol comes into play. Agents can negotiate about output modality. Sometimes it could be other critical parameters that can greatly impact user experience. Going back to that flight and hotel example, the flight agent might say something like, hey, hotel agent, could you give me the check-in times in UTC? That's an example of negotiation. Once that negotiation and handoff happens, another issue we come across with is long-running operations. We often find ourselves trying to do long-running operations, and what we notice is you cannot always support these operations using synchronous communication. Agent-to-agent protocol has this concept of task objects. every task object is associated with a task ID and a status. So every time, let's say, an operation or task gets created, you know what the status is, and then you can get notified because A2A also supports streaming with server-sent events. Going back to the example of the flight and the hotel agent may come back and say, hey, but I need to make a call to the hotel to find out the check-in times. This is gonna take time, so I'm gonna create a task with this ID and this status. Once I'm done, I'm gonna send you a notification. This is again possible because we support streaming with SSE. Next, because all these agents are in different ecosystems, we really want to make sure the collaboration is secure. A2A supports secure collaboration because it uses HTTPS. Additionally, in the case of the flight and the hotel agent, we're making sure that the flight agent does not have access to the inner workings of the hotel agent, does not know anything about it, so we are maintaining that opacity. So summarizing the 4 key features: secure collaboration, task and state management, negotiation, and then discovery. Let's move to the resources section. So if you're interested to learn more about A2A protocol, you can find the documentation at a2a-protocol.org. The A2A project can be accessed at github.com/A2A project, and to install the Python SDK, just use pip install A2A SDK. If you're building using Google Cloud Platform, we provide an end-to-end toolkit for A2A agents on GCP. We offer native support for A2A in Agent Development Kit. ADK is another open source toolkit that can help you build agents. For deployment of options, we have several ways of deployment. If you're looking for a fully managed service, Agent Engine is the way forward. If you're looking for more flexibility, you can deploy A2A agents on Cloud Run and GKE. You can also bring your A2A agents to Agent Space. If you're looking for evaluation services, we support A2A agent evaluations on our Vertex AI evaluation service. You can also monetize your agents by publishing them on Agent Marketplace. We have seen immense response from the industry. We have loads of partners working, contributing. I just remembered from yesterday, there was a recent contribution from Twilio. They were looking to broadcast latency information. So let's say at the time of orchestration, they want to identify the right agent. They look for the latency of different agents and then choose the next right agent for that particular operation. So feel free to check that out. And I look forward to collaboration and contributions from all of you. Thank you so much for having me here, and go Bears on behalf of the A2A team. Thank you.
All right, thank you, Chitra, and thank you everyone for attending today. And I'd like to thank all of our speakers. I know it's particularly difficult to get your talks down to 10 minutes, but I really appreciate it, and thanks. And if you're interested in any of these open source projects, open standards projects, please get involved. Please engage with their communities. Thank you.
I think we have time for one question, if there is any question. If not, we can move on to the I think now we are moving to the next exciting session, focusing on the agentic intelligence in action with MCP, VLN, and Pydantic AI powered by AMD. And we will have here insights from Mati Gassi, who is the currently AI solution architect from AMD. So let's dive into technical detail, and let's first welcome our speaker.
Good morning, everybody. Welcome to AMD's Workshop 101. This is supposed to be a hands-on workshop with bring on your device. We will give you access to AMD GPU MI300. So if you have your laptop, feel free to take it out and get ready for it. There is one technical problem. Apparently the Wi-Fi at Berkeley does block that connection to the GPU we have, so you have to use your hotspot on your phone or any alternative Wi-Fi you have. We did not expect this until we got here. We tried it, tried to communicate earlier, but this is some sort of problem that we didn't expect. But if you have, again, hotspot, that would be ideal. You can connect to your laptop. There is a challenge part at the end of the workshop, so we do have prizes for up to 5 people, I believe, that whoever can finish the challenge and we verify it, you'll win the prize. But my apologies for the technical difficulties. So I hope you guys have your alternative Wi-Fi source, either, again, a hotspot or different source of Wi-Fi. So my name is Maddie. I'm an application engineer, AI solution architect as well, 2 titles. And I work mostly on testing out all the open source AI agentic or applications to see if they work with AMD GPUs, and we can integrate it if it's not working, find out the problems. I also have a couple of coworkers here. Ida is right there. For any of the problems you guys may face in the workshop, we're here to help you. And also Shekhar, who's on his way, and he'll be here soon. So before I start, just a question. So how many of you guys have used AMD GPU for AI development? Half? 1, 2, 3, 4, 5. All right. So I see there's a lot of potential here. So just to start, at AMD, it's been a few years that we just focusing on changing that perspective of AMD is not just a gaming GPU. You can use it for AI work. So to enable that, we have done a lot of work with different communities. PyTorch, for example, you can just pip install PyTorch on any of your AMD GPUs and it works. Hugging Face as well, Hugging Face Transformers is, we got a CI/CD with them, so you can actually get them installed on or work on any of our AMD GPUs. VLM and SGLang, we have a deep collaboration with them, so we have the Dockers also every night for VLM, I think, and for SGLang every couple of weeks or a week, you get an update with the latest one. And in terms of models, we have day 0 support for most of the models. So you see Llama 3, Llama 4 coming, and we have day 0 support for it. Same with DeepSeek, Qwen, and more models I can't talk about. They're coming up soon. But watch out. So any of the models that come out, AMD GPUs is one of the only hardware that you can actually get the model running from day 0. From day 0 might not be the most efficient way of running it because some of the kernels are so new and it needs a bit of work on the backend part. So we have different teams working around the clock when the models are released to make sure the throughput is increased over time. So DeepSeek is a good example. So when it was released on day 0, we had it running from the moment it was released. Within a couple of weeks, we got it 4 times faster than what it was released first. And this is just to make sure that for the customers that we have, or for anybody who's a developer and they want to have the fastest speed, we don't stop at just supporting the model. We continuously work on it to increase the throughput. In terms of today's workshop, we are providing you guys with a link that has access to MI300. MI300 was released a couple of years ago as one of the things that actually got AMD a huge boost in AI. One of the reasons is the high bandwidth memory on the AMD MI300 is about 192 gigabytes. So you do get a lot of room for running larger models. If you have access to a full node, it's 8 of these guys. So you can actually run a DeepSeek or Kimi or any of the bigger models with one node. So it gives you a lot more efficiency for convenient for running the models that are larger, higher batch sizes, or you guys know all the benefits of having a higher bandwidth memory. So in terms of today, we're going to give you the AMD MI300 access. But the topic for today is AI agent. This is a definition I got from Hugging Face agent course. So the simplest way to describe it, what is an AI agent is basically a model that can do reasoning, planning, and most importantly, interacting with its environment. Here I have an example to show this in action. So we have this demo actually downstairs, and you can actually go play with it. And this is based on an open source project called Browser Use. Browser Use actually is one of those AI agents that has all the planning within the system prompt. You can basically type any sort of browsing task you have, and it will take care of it for you. The example I have here is one night I wanted to make chili, and I wanted to see what ingredients comes with chili, and if you can put that in my shopping cart on Instacart. And all I had to do is just type that command or prompt in the GUI, and as you can see, it's doing all the planning. It's trying to figure out what the ingredients are, and then add them one by one to my cart and have it ready for me to purchase. So today we're going to give you a little glimpse of this on how you can actually build something like this, a very, very simple version of it. And hopefully we learn from each other, and hopefully some of you guys will win the challenge. Okay. So in terms of the agenda for right now, what we're going to use is VLLM for the backend. How many of you guys actually used VLLM before or know about it? Great, great, great. It was born in Berkeley, so it's one of the projects that started at Berkeley, and now it's one of the most dominant way to actually serve models. AMD, NVIDIA, we all support it, and I love it. It's one of the easiest way to run any of the models. You just put the name from Hugging Face, and you can run it. For the framework for AI agents, we're using Pedantic AI. The reason I chose that is a super simple open source library you can use to build any sort of agent. We'll get a little glimpse of how to build one. And finally, we're going to show you how to use MCP servers in this framework. So there's a lot of hype around it. Why is MCP so hyped? We'll get a little bit of an idea of how we can integrate it here and why is it hyped. Okay, just for my knowledge, how many of you guys actually got that, alternative source of internet, like roughly? All right, a few guys. I highly recommend it because it's just, these GPUs are super expensive. I wish I had access to this a year ago before I joined AMD, and I tried. I couldn't get one, but now we're giving a lot of free access. We also have that available on our developer hub. Visit us downstairs, you can sign you up, you get free access to this GPU. I'm gonna leave this up for a bit and see if everybody gets connected, just maybe a couple minutes, and I'll move on to actually running the workshop. Oh yeah, I did have somebody actually finish the whole workshop and actually got the challenge working on their phone before, so feel free to use your phone if you have to. All right, anybody needs this to be up any longer now? Okay. All right, so you all should have a screen like this. It's a Jupyter notebook. During this tutorial, I'm just going to go step by step. So, oops. A lot of technical difficulties today. USB-C one or?
Yeah. It's working earlier. Security thing on the, that doesn't work on that.
Can you just plug it directly to the TV or?
Then we lose, it's weird.
Okay, so if you have it loaded before, I can maybe like kind of like guide you. The first step I was gonna do is you guys should have a little tab right here. You should open one, and that will open a terminal. So basically, you'll have a Jupyter like tab here, and then that should have a terminal. So if I just go up here, right above where the notebook is, and you should see a terminal. I know it's small, I'm sorry. So starting there, it should load a terminal for you. So the first step of this notebook is actually running the model. So that would actually first download the model and then load it to your GPU. And it will take a couple minutes. So maybe we can start with that. So the way we do it, if you just scroll down the first step, you could see a little code what the VLLM use. That's where I copy this whole thing and then paste it in the terminal and press enter. So let's do that. I hope you guys got what I meant. Are we good with this part? Anybody's having a problem? Can I get Ida? Maybe you can help here too as well. So the cool thing about this command that you guys running is if you want to grab any of the models from Hugging Face, you just basically need its name and you just do VLLM serve model name and that's it. You just get an OpenAI endpoint that you could use for any sort of open source applications that needs OpenAI based URL. So this is creating that for you. So all I've done is basically gone VLLM serve the model name, and the model name comes directly from Hugging Face. The parameters you see here, they're optional, but for Agentic, you do need to have the tool calling, and that's where it's coming. The couple parameters I have there, for example, I'm just gonna read them. So enable auto tool choice and tool call parser Hermes. The tool call parser is model based. So the way I get that is from VLLM documentation. I go look at it and figure out for what model, what tool parser I need to use. The rest of them, again, optional. You can always look it up on VLLM documentation and get a better understanding. Yeah, so all the code cells in the Jupyter, this probably applies to everybody. You just either do Shift Enter, or there's a play button on the top left, on the top of the notebook. So basically select a cell and run it. So the first cell I have there is basically setting the variable such as base URL. Oh, okay, we're good. Perfect, all right. So here we are, so the base URL, we're setting that to our local host. The port is 8000 that we got from above there. And then we also set the API key. So let's just run it together. Once you run it, if you get the green, that means that it's completed. If it's yellow, it's still running. So right now, the first one is completed, and you got the URL set. And just to test the server to make sure we get a response, I'm just going to run this. So you do need to get a response from the server that, hey, I'm ready to serve you. The model name is this. And you can go ahead and use it. Any problems so far? Are we good here until now? All right. So far we're just setting up the endpoints, the backend parts. So if you just got here, I'm just going to quickly show this. I just saw a couple people coming here. We are giving you GPU access to AMD MI300. You can run this on your phone or laptop. It can't be on the Wi-Fi here. So if you're using the Wi-Fi, you got to switch to your hotspots. Okay. Back to here. Installing dependency, we're going to run Agentic AI installation. It will take a couple minutes. That's good. All right. Next, what we're doing here is just basically all we're doing is connecting the agent to a model that we just run. So basically here what we're doing is telling the agent model that, hey, we want you to use the endpoint we just started. So first we just start with a variable.
It's because you have an online audience that can't see it.
Oh, okay.
So if you're mirroring on all your displays.
Sounds good. Okay, so we set that the agent to actually use the OpenAI base URL that we use. And the next thing is let's just like connect it to our agent. So all I'm doing here is creating an agent instance from Agentic AI. So it's as simple as, hey, Agentic AI import agent. You create a variable, you run it, you have it connected to your agent instance. The next part is just a helper function. So this helper function, all it's doing is just running your agent. So to run the agent, you can do synchronous, asynchronous, or word streaming. So I selected asynchronous running of the agent. Also, because we're going to be using the MCP server, that's what I'm doing. This is all coming from Agentic AI documentation. So, but we're just using it for a helper function. So later we can just say run async prompt, and you'll get the agent response. And to start, we have a very, very simple, what is the capital of France? And we're going to run it together to see if we get a response from the model. Perfect. So we should all get a response now. The capital of France is Paris, and more token generation by the model. But this is just confirming that you actually can connect to the model. The agent is getting a response, and it's ready to be developed further. Any problems so far? We good? Yeah, okay. So what's going to happen if I just say, hey, what's the date today, right? So far, we haven't given this agent anything. If you remember for the agent part, I said the agent is basically a model that you can give it tools, right? Right now, it doesn't have any tools. So if I run, what's the date today? It basically says, hey, I have no idea. You should see something like, don't have real-time capability to check the current date, but I can help you calculate it, or, it's still trying to figure out how to get it for you, but it doesn't have the tool. So before the MCP was hyped, everybody would have to actually write a little function and then add it as a tool to the agent. And that's what we're doing here. So we're basically using the tool decorator from Pydantic and making a very simple one-liner Python function, get current date, and defining it as a tool, right? We also, if you notice, we imported a tool library for Pydantic AI to be able to enable that. And next thing is one of the important part of having an agent is having a good system prompt, and that's what I'm doing here. Basically just say, hey, now you have access to a new tool that could get you date and time. I also connected that signature of the function that we just created to our agent to be able to use it. So, and that's all we're doing. Next, let's run the same prompt we just did. What's the date today? And let's see what happens. So you should now see the agent is actually connected, gets a current date, and now it doesn't have to guess or try to calculate things. So basically right now I'm just trying to show you the power of how having tools can enable the agent to interact with its environment and do things that it couldn't do just based on its knowledge now. But next thing is kind of why is MCP hyped, right? We had to write this function. We had to go define what the date and time function is. And that could be a lot more complicated based on, different things you need. For example, if you want to have an agent to send an email for you, right? you have to go read the Google API, write the custom tool for it, and then add it as a tool and be able to do it. But with MCP, you can actually literally integrate a Google MCP and then just call that instead. So here we're just doing the same example of the time server. So I'm just going to install the MCP server, but again, running the cell. I got the installation method and all the things below it from the GitHub repo of this MCP. You can find these MCP servers. I have a couple links in the next step that you can find them. But let's just go ahead and just follow the instructions of these guys who built this. But one point is we had to now add the MCP server stdio for our Agentic AI library. And one note is, don't play around with the city. This is again open source MCP. If you put a wrong city or something that's not supported, it's going to say connection error. They don't have a very good error checking. What you could do if you want to play with this tool later, you could just basically ask it in a prompt. What's the date? What's the time right now in California? Or ask the agent to calculate that for you rather than you actually go change the tool. So let's just start with defining the agent again, but this time we removed the tool, we connected MCP server to it, and we again call it the exact variable that we defined up there, and then we updated the system prompt. Hey, you're a helpful agent, you have access to this tool, do it again. And one point about MCP server before I move on, MCP servers come with a pack of tools, so one MCP server could have multiple tools, right? And that's the name of the tool actually from that MCP server. That's where I'm getting it from. Again, it's from documentation of the MCP server that I'm using. Let's define our agent again and now run it. Instead of using our tool, this time we are going to use the MCP server. Okay, so you should see something like this. The current date is August 2nd. You can ask it what time is it now, and then again, like select your city. You feel free to play with the prompt. All right, this is the last step of this workshop before I move on to the challenge. Do we have any problems so far, or everybody's good?
At the very beginning, when we started the server, can you just show the output of the terminal again?
Sure, yeah.
Can you repeat the question?
Yeah, so the question is, for the server side, when we started the VLM serve command, can you show exactly what happened and show the terminal output? And thank you for asking that question because we couldn't show that on the screen when this happened. Basically, first of all, you have to make sure you have everything exactly the same way I put there. We're going to disable flash attention and then run a VLM serve. Then what it's going to happen is it will first download the model. So if the model download is by any chance interrupted, you can just Control-C to kill the server and restart it again. It will continue downloading the model from the point that it failed. And then finally, it loads the model on the GPU, and then at the very end, you should see a message like this. Info, start a server process, waiting for application startup, and this basically will be your last message you should see if you run the server correctly. Oh, it should take a minute or two. Yeah. Yeah, so the question is how long would it take for this to basically load everything? This is running on our cloud developer, so it's a very fast internet. The model is about 70 gigabytes, and it will take about a minute to download the model and about a minute to load the model.
So if you want to implement a function that's not in the MCP server or you don't know the name, like for now it's MCP date time server or something, but if you don't know what it is there a way to search, or do you have to write the function if it's not there in MCP?
So the question is, like, if I get it correctly, your question is if you want to define our own custom tool or if you want to use an MCP server that is not one of the ones I showed. Which one is it?
Yes, it's not the one you showed.
Okay.
Or you don't know the name of
Yeah, great question. So basically, right on step 6, you'll see I have 2 links here, right? And it's not limited to this. MCP servers are developed by people all around the world. Some of them are enterprise level, some of them are just open source. So I put 2 links here that, people are tracking these MCP servers being developed. You can just go ahead and just open any of those links. You'll see there's, tons of them, right? if you want to use any of these guys, you can just click on it, and then on the documentation slide, you'll see one, how to install it, different ways to use it, and also what tools that it come with. Sometimes the documentation is better, it actually puts the name of the tool there. Sometimes it actually, you have to go look at the code. Again, it depends on who made it. The cool thing though is if you connect to MCP server correctly, you can actually ask your agents, hey, what tools do I have access to? And it actually would be able to list all the MCP tools that you just integrated there.
Is there a way to stream the response?
Sorry?
Like now we get the response as a line, right? Is there a way to stream that response?
Oh, so the question is, can we get the streaming enabled for the agent? Yes, so if you look at the Pydantic AI, the documentation of it, there's 3 ways to run the model. It's async, sync, and async with streaming. So if you look at that, you actually can find that information there. Okay. Yeah.
So is there a way, is there a way that, like, is there a drag and drop user interface that can actually look at the libraries of MCP that you can draw and basically connect a loop to form an agent loop? And then eventually sort of build the stuff, because what I see is like seldom, I mean, like when you're trying to build these systems at scale, so one of the things that I see is like the multiple functions that you got to call in a sort of a loop. What I was hoping for is like, is there any framework that allows us to do those sort of things, where you can actually design the prompt, connect, do a bunch of things, but at the same time you're also having access to the various MCP servers that you have.
So the question, I guess, is like, is there any sort of like UI base, is that you're asking, that you can drag and drop like an MCP server and get the tools? I honestly,
You're doing it static, right? So you're basically getting a mini file either from Python index or whatever it is, you're installing it.
Yeah.
What I'm getting to is like, as we're building a system at scale, so there could be things like where people want to use what they want to connect with combination.
right. To be very honest with you, I don't know if there's any tool like that available or anything like that. But in terms of, again, like connecting your MCP, so the question is, are there any tools that you can just drop the MCP and see any sort of tools that come with it? I don't know. But with different agenting frameworks, if they're built properly, if you just connect the MCP server, again, you can literally prompt the agent. It's like, you know, give me the name of all the tools you have, or even like draw a graph of like all the tools you have that I can use, or you know, you could do that with a proper agentic framework. But then I don't know if there's anybody built that. Be a cool project if you started. Okay, there's one question there too.
You said you can ask the agent. You said you can ask the agent to list the tools available in the MCP.
Yeah.
Why do you even need the system prompt then?
You don't. So I've had the pain of working with the smaller models, right? So say the same Qwen 3, like 1.6 billion, if I remember correctly, I had to build a project because they wanted to make sure it meets the time requirement, right? The smaller models are not great at actually auto-calling the tools. So a lot of times you say, what's the date today? It makes up an answer. It's like, hey, today is 2050, right? So to make sure the agent is actually behaving better, I'm always sticking to system prompts and kind of like reminding that, hey, you have access to this tool. So if anybody is asking for a date or time, try to use this tool. Yeah.
Also, to his point, there's the listing of the MCP servers that's like a link, like mcp.so.
Yeah.
So if someone made an MCP server that could access all of the available MCP servers on that website, that could work. Do a meta MCP server.
Great question. It's a great project to start again. Thanks for the point. Okay. All right. Let's go to the next step. So this time I'm just trying to use 2 MCP servers at the same time to just give you guys like leave you guys with something that may be useful. I don't know if you guys are gonna use this later, but you can actually turn this agent that we just built into an Airbnb finder. You can say, hey, I'm looking for an Airbnb in this city on this date for 2 nights for 2 adults, no pets, with pet, whatever the MCP allows you to ask, and then get some sort of listing. But to do so, again, I had to go look up how to install the dependencies. So we start with installing node and npm to make sure that we actually have all the dependencies installed. Hopefully I'm still connected to my, okay, yeah. So this should take care of that for you. We tried to make it as simple as possible for this workshop to run. I'm sure you guys are going to have a lot of problems with some of installation and how to get them working. As there's a challenge, you may face some of that later when I show the challenge. But for now, this should run smoothly. Then let's check the versions, make sure we got version 20 for Node, and the rest should look like what I have here. And then finally, again, this is how I got it from Airbnb server's page for the MCP server. You need these arguments to be added to your MCP stdio, and the type is MPX. So we're going to run that. And then finally, again, I'm going to update the system prompt, not because I have to, because I want to make sure that it's behaving the way I want. The MCP server from Airbnb comes with a bunch of functions. So two of the ones that I'm going to use here, and I want to make sure the agent is using, one is Airbnb search, the other one is Airbnb listing details. So that's why I'm naming them. Again, this is coming from their documentation, and I'm letting them know when users ask for a listing, first call, get current time, then get the Airbnb search. Let's run this again. One thing that I just want you guys to pay attention is you can, since you add in a second MCP server, you can actually have this growing. So you just have to include, again, the signature of the variable you've set for your MCP server. And then finally, how do I get the model to use both MCP? I'm not giving it a date. I'm just saying next Sunday, right? So I'm trying to get the agent to first do the planning, calculate what next Sunday is, and then give it, hey, I want it for 3 nights for 2 adults in Vancouver. All right, so running this will take about, I guess, like a minute to get a response. And this is because it's communicating with the MCP server of Airbnb, is trying to get the listing and show you guys a listing of all the matches it finds for you. This is basically the last cell I'm running with you guys. Yeah, so you should get a response like this. We can obviously post-process it to make it look better, but we can also try one of the links to make sure it works. And there you go. Let me go back here. Oh, it says view all listings here. Again, this is something that you can prompt better, or have a prompt to give me the link for each of them, and it will do it. And that's, again, like something that I've dealt with the agents is your system prompt is important, and also the prompt you give the agent is very important. This is basically, again, the last thing I wanted to run. So from here on, for the challenge, you can obviously do it all in the Jupyter notebook that we're giving you. If you want to start a new cell, you could just do this and type your code, or you can just modify the ones that we have. So what are our challenges that you could do in the next 10 minutes, and whoever gets it first wins it? So we have 2 challenges for you guys. Challenge 1. There is an AMD SMI API, right? So if you look at here, again, going back to my notebook, you can actually check to see how much of our GPU you're using, right? This part was the part that I actually had my monitor was not connecting, so I didn't show you guys. But say ROCm SMI will show you the GPU utilization. Whenever you're running, that goes up. The VRAM is 88%. So what we want you guys to do is create a custom tool. So I showed you how to create a custom tool. I also showed you how to integrate MCP server. So challenge 1 is create a custom tool using AMD SMI. It's not the ROCm SMI. AMD SMI has a Python API. It's very well documented. If you Google it, you'll find it. And the goal is to get a response from the agent that, hey, like the VRAM usage is this. Actually, the other slide here. So it should look like something like this. Let me expand it, make sure you guys see it. Sorry. Do you guys see a response like this? Okay. The response should look like something like this. Hey, shoulder VRAM uses percent of the single AMD GPU in use, and you should get something like, hey, it's about, I don't know, 90% or 88%. It should be around there. That's challenge one. Again, AMD SMI, write a tool with a tool decorator to get to this sort of functionality of your agent. Challenge number two is add an MCP server. So go Google, find a free and open, well, it doesn't have to be free. If you want to pay for it, go ahead. We're not going to stop you. But you want to basically add an MCP server for weather. So the whole point is like, hey, like, can you suggest me good days to travel within the next few days? Or how is the weather in California or Berkeley today? That works too. So if I see a response that coming from your agent, that's also acceptable. So basically, if you do any of these two challenges, it doesn't have to be both. One of them, you could choose between the two. You will win the prize. It's based on, again, first come, first serve. Whoever gets it done fast first, they'll win the prize. But yeah, from here on is your part. It's hands-on part for you to do it. I'm done with the workshop part, so if you're not participating, that'll be it for now. But I'll give you guys about 10 minutes from here to see if you guys want to finish it. And thank you for joining us again. One question there? Yeah.
So, is it fair to say the companies will publish their own MCP servers in future for people to find
Can you repeat that? Sorry.
Sorry. Is it fair to say that in future each company will publish their own MCP servers to expose their, like for Airbnb, for example, if somebody wants to find them on Airbnb, what is the purpose of this as opposed to API? API basically goes specifically to the website. You give them certain format, you get the output in certain format.
Yeah, it's a good question. It's funny. I'm from Vancouver, and I was driving up to Berkeley, and I saw a big billboard that was like, "Are your APIs ready for AI agents?" So basically, I think that's where we're going. You look at Google, you look at GitHub. They're all releasing their own MCP server now, right? And they want to make sure they have the enterprise level ready for that. Like this Airbnb we use is not by Airbnb, right? Some random person just made it.
Right.
I think so. It looks like that way. MCP was launched, I think, in November, and I saw in January start to get momentum. And by now, I see a lot of software that are actually integrated. So I think it's gonna go that way. APIs are nice for humans like us. We want to actually have it very well documented for humans to read. But MCPs would be a next level for the agents to actually do the same thing. So it's a good guess. I can't tell for sure, but that's my guess. That's why.
If others don't have a question, I would like to follow up on this. So Chitra actually gave an A2A talk just a short while back, and she talked about this travel planner and all that, and that's a very common scenario in enterprise agencies, what have you. So basically, I'm looking at it and I'm saying, okay, there's like a trip finder, there's like a rating finder, there's Airbnb finder. One day you'll have all these MCP servers, and all that root agent has to do is basically just go and find them and orchestrate between them and interpret the result. Is that fair characterization, or is it too simplistic?
I think it's fair. I mean, in terms of like the agent that we're showing right now, and I just built one, it's like a single agent, right? If you look at more complicated agentic frameworks, not only the same agent you have can have multiple other agents within the same framework. So like I have another project built exactly by Agentic AI that use your orchestrator agent, and you have a bunch of other agents to do some other tasks for you, and they communicate with each other. It's like, hey, you have, instead of me saying you have access to this tool, it'll be similar, but the tool will be a whole AI model that is capable of doing planning and do all the execution itself. And then on top of that, you're talking about A2A, like Google Agentic kit that they just came up with. And that becomes a way of communication across different frameworks, right? It doesn't have to be like just by Agentic AI. You can have agents elsewhere, and they can communicate with each other. And that's kind of like the path I'm seeing it's going. we're still kind of the beginning of the whole agentic phase of our AI, and we'll see how far it goes. But so far, that's the path I see, and we'll see how far we go.
Thank you.
No worries. I'm assuming the people here are still working hard on the challenge. Feel free to ask any questions. If you need help, like we could come to your, you know. Yeah. So I think the question might actually apply to you too. A lot of my coworkers also who don't use Jupyter often, they have the same sort of question. So if you're running a bash command on Jupyter Notebook, you do need this little explanation mark before it. So if you need to pip install anything, you kind of have to put that before that on your cell. So if you do pip install X, you need the explanation pip install and the library you want to install. So you can't just like import AMD packages. You have to actually install it first. You finished it? You got a first winner? So we got one winner. Oh, second winner? Let's see. Third? Okay, I just want to, like, if you finish it, please put your hand up because we have a limited number of prizes. So I got 2, 3 claims so far. So 2, third thing. Not here. Okay. It's great. We so far got 2 people finishing the MCP challenge and 1 person finishing the GPU. We got 2 more claims here.
One quick announcement. AMD is giving away free GPU credits for people who are interested in working further. So if you stop by at our table at level 2, we have flyers which you can use to connect to a URL and register yourself. We are giving away free GPU credits for whoever is signing up at this conference.
Hello. Let's get started with the afternoon session. So in the afternoon, we will have 3 amazing sessions on agent applications, foundations of agents, and AI safety, alignment, and security. By the way, I'm Jing Xuan. I'm the session chair for the afternoon. I'm a postdoc working with Professor Dong Song. So our first session will be about agent applications. And the first speaker is Deepak Agarwal. Is Deepak here? Yeah. Deepak is a Chief AI Officer at LinkedIn. So the stage is yours.
All right.
Everyone, so happy to be here to kick off session 3 with you. I'm not Deepak, as you can see, but he did ask me to come here in his place. My name is Adam Kaplan. I'm a senior staff engineer at LinkedIn. I work on Agents platform, which is part of Core AI, where I work with Deepak on the future of autonomous agents. So just a quick sidebar, why LinkedIn? Why am I here? LinkedIn's vision is to create economic opportunity for every member of the global workforce, and we believe that we can't do this at this point without agents to help workers unlock value by getting their work done more efficiently. So I promise this is not a producty thing, but bear with me for a minute. There is a point. Late last year, we launched something called Hiring Assistant, which is a multi-agent product that's targeted toward recruiters, so probably nobody here has used it. This is not the target demographic. But this is a system which uses 4 agents with a supervisor agent, kind of a common pattern. I know everyone here is probably familiar with it because I saw that in the previous talks hands were raised. Like pretty much everyone has designed a multi-agent system here. Well, as pre-work, we start out with a preference model that's constructed by analyzing the recruiter's decisions and actions made in past projects and current projects so that the agents can be personalized to a particular recruiter. And so these 4 agents here, the first intake agent, that's helping the recruiter get through the workflow of creating these roles and job descriptions. The sourcing agent goes and finds a huge list of candidates. The evaluation agent helps you hone in, helps the recruiter hone in on the best candidates. An outreach agent actually initiates that initial communication to the candidates in a way that's personalized to the candidate and the recruiter. So this system is supported by a deep ecosystem of tech stack that consists of like open source and sort of where there are gaps in the open source ecosystem, some home-rolled technologies. So why am I talking about this besides to show that we're doing cool stuff? Hiring Agent was shipped in October. That's a multi-agent system delivering value to our recruiter customers for months now, and the reviews are that they're getting significant positive impact. So when we talk about the frontier, this is the frontier stage. Multi-agent systems certainly are the frontier, but I feel like this is like a crashing wave at this point, not a cresting wave. So when we're standing on this frontier and looking forward, I mixed my metaphors here around the curve, but when we're looking forward, we see autonomous agents rising in importance. And these two things are linked, right? And I'll get to some of that in a moment. So what is an autonomous agent, at least by my definition of an autonomous agent, is an agent that starts to take in multiple signals from its environment and use those signals along with its memory to orient itself. And then we go into the typical like React loop that you can see there on the right side, reason about the next best action, take that action with a tool, incorporate the feedback, and on and on. So it's a subtle difference, but very impactful by taking in multiple signals. We're going to get into a bunch of interesting problems that I want to talk to you about here. The first one is memory. Okay, so again, this is a typical memory stack that you might end up with if you're designing an agent within a multi-agent system or not today. You have roughly 3 tiers of memory. The first is your in-session memory. This is your active conversation, messages that the user sent, what you sent to the message, tool calls you made, results from those tool calls. Very high resolution. The second tier, when you have too much of that conversation, is summarizing that history along some axis of classification. If it's like a ChatGPT where you click new chat each time, then there's your classification right there. You summarize each of those. And now you have, in your context, you have the broad strokes of what you've done and the learnings and takeaways from that. When you have too many tasks that have been summarized, now we move back one step further, break everything down into primitives, facts, phrases, shove them in some retrieval system, EBR, or if you want to be fancy, maybe something that's powered by an agent, or maybe a combination of those two, and use it for RAG. So with an autonomous agent, it starts to look a little bit more like this. If you can take in multiple signals at once, and I'm talking about a specific agent here, I'm not talking about everyone's individual agent, right? So those signals can come from 2 different users. So now we end up with these 2 isolated memory stacks. They're isolated because people expect that. There's a certain lack of trust we all have right now, everyone in the world, with agents, and part of getting around that involves us assuring people that when they say something to their agent, it's not going to be repeated back to another person or otherwise, leaked across boundaries. But this presents a pretty big problem, and it was touched on in some of the morning session 1 talks. Take a straw example. If we have an autonomous agent named Evie who is working with a user named, let's say Jane, to plan an event, it's an event coordinator agent. And it's working on, setting up all the logistics for something like this conference. And then we have another person, John, who's aware of that whole setup and reaches out to Evie and tells that agent, hey, we're going to need 10 more rooms or something. What is that agent supposed to do? in the current scenario, the naive context, it's probably going to start to like reach out to the hotel, let's say, I mean, if that was possible. And that can cause confusion because now you have not one single point of contact for that, making those decisions. So the way around that is to introduce another type of knowledge, which I'll call here like common knowledge, for that agent, within that agent, where it's aware of at least what it's doing in other contexts, if not just enough information so that Evie would know that it shouldn't take an action, it should probably tell Jane that there was this change, and maybe we incorporate that information into the main task loop instead of working somewhere and causing chaos. So how do you get things into common memory? We're working on it. That's about all I can say there. It's a big one to solve because the concerns that you would have with this are very broad. There's trust concerns between those two users. If you're in a company, which is likely where this would be happening, there's regulatory concerns about data being shared, like DMCA and things like that come into effect. There's policy concerns from the enterprise administrators. Lots of things that need to be worked through. And then there's the basic human expectations of like what is appropriate to be shared. But I think we can solve this. And the reason I think we can solve this, and first of all, we need to solve this because if we don't solve this, our agents are stuck in boxes and it's gonna be a pretty lame next 2 years. The reason I think that we can solve this is because human memory, we usually experience human memory through language. Like there's actions that you take, but I think that's not really the analogy we use, because if somebody forgets how to use a spoon, we consider that a debilitating illness, right? That's not what we're talking about here. We're talking about how people make decisions about what memory is appropriate of their memory is appropriate to use in what context, and how to let it decay, in these tiers, how to let it decay in this sort of expected fashion. If you can't remember what type of pencil you used to take notes 2 years ago, nobody thinks that's a problem. It's a feature of the system. So because we can express those limitations and boundaries in language, I think that starts to look a little bit more like the reasoning problem. Once we were able to express reasoning through language, we could attack it with the models. Oh, that's something that I'd like to see happen here, and it's pretty important for us. The next place that I want to go is to talk about our modular agentic architecture and how it's essentially come together in practice. So we start here with our sort of typical React loop that I showed in the beginning with an additional box here in the top labeled tool discovery. So the tool discovery is meant to help the autonomous agent explore its environment. So with specialized agents, you tend to have not much agency. There's a few tools that they have. There's a sort of predefined workflow that they're operating in with set decision points. And they make decisions, the LM's making the decisions, but where it goes is kind of controlled. When you have the more autonomous agent, it has a larger set of tools available to it, just by definition, because you're doing the work of multiple smaller agents. 2 years ago, I think maybe 10 tools was the guidance that you can realistically put into an LM. Last year was 30, this year with 03, we're at 100 for that particular model. Great progress, 10x in a year and a half or so, but the amount of tools is 1,000x since then. And we see things like MCP on the scene, providing this fabric that allows existing APIs to communicate their capabilities as tools to LLMs more efficiently than ever before. So there is an explosion of tools. Tool discovery is going to be with us for some time now, for some time yet. Yeah, I'll leave it there. Now, ACT, tool calling. When you have the more autonomous agent where you're not planning every single action that the agent takes, you will quickly realize that there are two classes of tools. Idempotent tools like knowledge retrieval that are fine, you just use them. That's maybe like 10 or 20% of your tools. And the other 80% are destructive, potentially destructive tools. Sending an email they're all like communication-y, right? Sending an email, committing code is communication. Sharing a doc, commenting on a document, or like planning an event. So these things, because they start looking like communication, we found that we have to treat them the same way we treat messages sent to the user. So we have safety validations on the parameters that go into the tool to make sure that they're not hallucinated, that they're appropriate, and things like that. Similarly, when we get feedback back from the tool, we don't just stuff it in the context. We first have to do semantic jailbreaking and other checks, static and model checks, because once data goes into the context, it becomes very difficult to take it out. You might get saved by, if you're in Azure, by their content filter, for example. But then what do? It's hard to back off an agent that's working on a long-running task to get back to a state where you can actually like execute safely, because there might have been tool calls that happened in the middle that you can't forget. So both of the feedbacks from the tool safety and the jailbreak are communicated, both of the validation feedbacks are communicated as tool feedback so that the autonomous agent can reason about what happened and make a decision. For example, maybe it goes and tries to find another tool, or maybe it changes the parameters it uses, comes up with a novel way to reach a conclusion, or gives up. And the last thing that I'll talk about here that we found becomes very important is that there is not enough GPU, right? Okay, so reasoning models are great, and you can make some amazing experiences quickly with them, but you can't scale them. So what we found is that there are a pretty significant amount of user requests that come in, which can be satisfied by the existing context. You don't need tool calls. Your basic, like if I asked the agent what its name was, or whatever, something like that, which it just needs to reference in the current context and respond back in a coherent way. We use a completion model for that. So by doing complexity classification, we can move work off of the slow, expensive reasoning models onto the faster, lower latency completion models, and let our reasoning models spend more time on the harder problems. So in essence, what I want to just leave you all with is that main takeaway that I've had after working towards autonomous agents for the past 2 years now is that if you set out to bend the human expectations in the human world to the agentic world, you're not going to succeed. The way forward here is to take the agents and take the systems that we're building and adapt them to the human shape. This world is designed for humans. Everything about it, the expectations, the communications, the way we work, is designed for humans, and that's what we adapt to. So, I mean, my last minute, something that I'm thinking about recently around trust is like people expect the model to be perfect, never leak info. Okay, when you hire someone, you onboard them into your organization and give them the keys, and why do you expect them not to exfiltrate all your data? If we can understand the behavioral psychology of that and figure out how to adapt our agents to that, to build the infrastructure for them to conform to that, I think we're going to be very successful. So thank you. That's all I have for you.
Our next speaker will be Alu Trivedi. So Alu is head of Gen AI at Oracle Health HDI. Here you go.
Hello everyone, I am Anusua, I go by Anu. So today I'm going to start about talking a little bit about myself and then about Oracle Health. About myself, I'm a computer scientist who had a lot of passion about health and healthcare. Started as a researcher in VA Hospital, worked in Texas Advanced Supercomputing Lab on genomic resources, and then worked in Microsoft Research for almost 10 years, AI for Healthcare, then AI for Good Research Lab. Got burnt out by failure of healthcare in COVID, moved to e-commerce for 3 years, but then couldn't stay away, and back again doing healthcare for AI. So that's a little bit about myself. So you know, it's a deep-seated passion which basically brings out the researcher in me. Now a little bit about Oracle Health. Most of the people I met today were really surprised what Oracle is doing in healthcare. So there are two large EMR systems in the US, Epic and Cerner. Oracle acquired Cerner back in 2021. It was one of the largest acquisitions by Oracle, and now, as a result, we own almost half the patient population's data in Oracle. That's a lot of responsibility, and we want to bring a lot of impact onto our patient lives through the applications of AI. And thus, I'm here kind of trying to do that. So just to iterate a little bit about the need for automating the healthcare system. Just to lay out the land, how the impact of a patient's life goes through a full circle. There's a provider, the hospital systems, or the clinicians who are working regularly, meeting with us, trying to help improve us. There are payers, the insurance, who support us and get treated in the right manner. There is a lot of analytics which goes into who gets, how our insurance is distributed, how our providers can or cannot treat ourselves. And then there is pharma and life sciences, where there are new drugs constantly coming out, trying to figure out, hey, how is a patient's life safely treated? Now, connecting all these various different domains and all these different varied KPIs or success of metric is very different. Providers want to keep as many of the patients into the system as possible. Payers, out, do not want to keep them in the system. So how do you kind of build these generic systems? It's not the job of a single foundational model. That's come the agentic frontier, like the next generation agents, where it's a combination of different tools, not just of a foundational LLM model to bring all these different various aspects to treat a patient's life. Now, some of the applications that Oracle is working on is accelerate the discovery and development of new insights and therapies. Imagine in your EHR, your provider can start seeing an ethical ad to start saying, hey, this drug is not safe for this particular cohort of patients if you have this comorbidity. How useful it will be if you can be recommended to a forward-looking therapy for an oncology or cancer, which there is no drug known today, right? So those are some of the cutting-edge things where life science and provider systems can definitely get married into to solve. There are clinicians engaging with patients and clinical trials. So when you go and visit a clinician, most of the time, they turn away from you and they're just typing and taking notes. How good it will be if you can automate the data extraction from the communication between the patient and the physician and automatically populate the EHR systems, because at the end of the day, that's what most of the systems like Scribe do. So if you can do that in an ethical and private and secure manner, it would give the physician more time to have that direct patient communication and focus on the patient rather than taking the administrative notes. Deliver insight and therapies into hands of clinicians, as I just said, right? Figuring out for oncology patients how to basically make all of these trials and therapies accessible to all. So now comes the agentic piece, right? Why agentic AI in health and life sciences? So healthcare data is extremely unstructured and noisy, and there's a high cost of error for any predictive model. It could be basically cost of a patient's life. So there is very low margin of error that we are working with. Now, and continuously shifting objectives. Some of our colleagues are essentially just medical informatics folks who are working years and years as an RN or in like companies with 3M Medical and just works on evolving codes and concept IDs to map diseases and all of these things, right? So there's a lot of shifting objectives. Every year, these codes keep on changing. How do you make sure that the treatment plan a care manager or physician is developing for a patient does not fall out of insurance and the patient is not thrown out? So that is the major goal for us to bring healthcare for everybody. Now, Agentic AI keeps us honest in like the continuous spanning phase. A lot of tool execution reduces the dependency on just LLMs. And there is, of course, the reinforcement learning, which is a self-correction piece, which helps bridge the decision support, automation, and reasoning. So today, we're just moving from assistants to autonomous collaborators. If you remember, this is something which, you know, the AI godfather, Geoffrey Hinton, said, healthcare is the only place where if you throw tons of autonomous agents, it will keep imbibing without affecting any human workforce because there's so much lack of human workforce and knowledge in this space. So the AI user experience patterns for pop health and life sciences, we're trying to divide it up into two large sections. One is a deep research agent, another is the agentic fleet. The deep research agent, think about it as your analytics consultant, where they anticipate the questions, they embed the workflows for personas across different pop health and life sciences. Your quality manager's workflow is very different from your clinical care manager's workflow, from your physician's workflow. These are different personas coming at different stages of your treatment plan and trying to do different tasks. And this whole end-to-end scenario is what delivering a good healthcare to you. Trying to understand the tasks for those personas and planning accordingly is what the deep research agent's major focus is. And the agentic fleet, think of it as more autonomous tasks happening in the back end, where the agents are driving seamless actions across different cohorts of patients, different campaigns to be launched for different diabetic patients versus COPD patients. Always on monitoring patients, figuring out the adverse events for a drug safety, right? So these are all autonomous agents continuously running in the background as agentic fleet, continuously communicating with each other. So if I'm to break out the components of the AI pattern here, this is how the flow would look like. A deep reasoning agent, somebody can come and ask and get informed and understands the evidence and the data, and then basically informs or delegates the task to the agentic fleet, where the agentic fleet is taking autonomous action, providing assistance, monitoring and triaging the right cohort of patient to the right problem space. And all of these steps are eventually creating high-quality curated data at the back end that you can continuously keep on ingesting, extracting, and normalizing to provide that evidence of support. Because that is what we are lacking in healthcare from the noisy, unstructured data. We have to focus on basing our thoughts. So if I'm to define what a health frontier agent could look like, it would be a mixture of primitives. What is a mixture of primitives? The deep research agent, the autonomous fleet that I just spoke about. If basically we can define it as a mixture of primitives combining basic agent-based or tool-based building blocks. And when the primitives are leveraged correctly, we see a highly emergent order behavior, right? You can have a base LLM, you can keep on tuning it, and then you can have your actions like planning, semantic search, simulation, which is basically now delegating all these agents to do all the tasks. Some examples, as I mentioned, the digital care manager, trial matching to do like site visibility and recruitment of patients, safety agents like for adverse drugs. The digital care manager usually, just to give you an example, is usually sits in between the patient and the physician. To give you an idea about how less percentage of our patients gets it, it's only 1% of extremely ill patients have care managers. What if we can create digital copies of this care manager to scale and benefit every patient? This is an example of a deep research agent where it has basically gone and collected the real-world evidence and started generating this dashboard. It is actually trying to get you the trial cost. It had done some market analysis and predicted your time to market for your drug, expected your trial duration, cost of the subject, all of the breakdown. Now, you can ask a question why certain trial design suggestions have been made. For example, why certain cohort of patients were excluded from this design of the trial study. From there, it will go and kind of try to rationalize that patients with liver cirrhosis are excluded from this phase 2 trial study because of some safety concerns, and it can go on to produce a detailed report for you. So some of the lessons learned is tools are mandatory. We definitely need an auditable planning. Modular monthly agent workflows helps you evaluate your tasks better. Hybrid decisioning is something which is coming more and more on board. And the state and the context continuity is ever important. Some of the guiding tenets: we need meaningful evals versus abstract measures. Results as a service is autonomously solving the problems. Flexibility to use the best in class as they evolve versus locking down into a single LLM or a framework. Providing the right size for the complexity, expecting as many builders as you kind of make your task more and more complex. And, uncompromising on safety and resilience, privacy and security, trustworthiness, and transparency. Lastly, we're hiring, so feel free to reach out and help us build this together. Thank you.
Thank you, Alu. Next speaker will be Ashutosh Nema, who's a consultant of data science at Dell Technologies.
Hello everyone, I'm Ashutosh Nema, consultant data science at Dell Technology, where I lead design and development of Gen AI systems at scale. The topic that we are going to cover today is from hype to impact, right? And it's a bit different than the topics that we have covered till now of agentic application. It's more about how do you bring agentic applications to scale or to production, right? Because it's all the hype right now, but getting it to production is what's the difficult task. So starting with the market, right? We have seen that we are all live breathing Gen AI evolution day in, day out, right? We see models coming in, research coming in almost on a daily basis. It's hard to keep a track of what's going on, and so is for industry, right? Industry struggles with legacy systems, with all of the data problems and all of those things, right? One of the survey that was conducted by Big Fours, right? What that led us to is 95% of the companies and Gen AI leaders are talking about bringing agent tech and Gen AI into the companies, but only, if you see on an average, only 20 POCs make it, right? And within those 20 POCs, only 30% of it graduates to production. So what's causing this lag, right? The research further suggested that strategic misalignment is what's causing it, right? So when we think of Gen AI or agentic systems, we think from a shiny perspective, but we fail to miss the mark of is it actually adding the business value or impact, right? Is it actually usable towards the end goal? But regardless of that, wherever that makes a green light or wherever it's able to go to production, you can see that it's a net positive, right? So the path or the goal at the end of agentic system is clear that there is value out of it, but what are the roadblocks and how do we navigate it? So if you see current challenges that are in agentic adoptions, right? There are strategy and operational challenges, which as I stated before, with strategy misalignment, but also with matrix stride flow, right? Currently model, if you have a machine learning model in production, it's being monitored by business day in, day out. There is a KPI attached to it. You cannot miss that mark any day. So those are the business constraints that are in there, right? Companies are struggling with should we build versus buy, right? That's a big discussion going on right now. Everybody thinks, should we do this POC or should we buy it? From a developer and user perspective, as the technology is growing, nobody can call themselves a master of agentic AI at this point, right? We don't even know what's going to come out tomorrow. So there is definitely a skill gap even with the pros. And at the same time, we have legacy systems, legacy data. It's hard to move those bottlenecks sooner at the rate at which the technology is advancing, right? Now with Gen AI, there is a huge difference between the pilot and production phase, right? As the users are evolving, everybody is using Gen AI, getting used to it, there's a huge gap. So let's say, for example, we tested out a search bar which could go to a product page, like you have it at Amazon, right? Before the reviews, you could just go and search anything related to that product at that product page. We tried doing that and add a fancy Gen AI-enabled name tag to it. With pilot, it worked very beautifully, right? People were able to search what they needed with their product. But when it went to production, what happened is folks were trying to prompt engineer the search bar. So the expectation is different. When they see Gen AI, people have all of different sort of expectation of what Gen AI can deliver to them, right? So those are the constraints under which agentic AI systems are there, right? And then the cost, latency, and safety and evaluation, these are the bigger challenges that are needed to be solved there. Evaluation is an active research space. These are stochastic processes. We don't know how to evaluate it. We are all used to having a deterministic accuracy number at the end of it, right? So these are different systems. But given all of that, right, how to get started or how to get kickstart with one of that POC that could help you cover the first mile and could deliver value to your business. So start targeted and modular. Take any existing process, break it down piece by piece, figure out friction processes that are existing between the system, right? To those, let's say, I'll start with an example, right? Let's say you have an NLP model where the input is text data and the output is labels that are coming out of it. Think, could the input data be reformed with LLM? Could you pre-process it so that the NLP model can make a better prediction? Could the predicted labels, could they be enhanced or augmented in some sort of manner for the user? Now that starts your LLM workflow, right? When you think of it, you combine this LLM workflow, you add a planner agent to it, you add orchestrator, you add validator, that gives you a task-specific agent. When you combine multiple of these task-specific agents, that's when you get your agentic AI, right? So in terms of thinking from an existing production system perspective, think in terms of block. You start adding block by block. What those blocks will also enable you is think in terms of evaluation when you're adding a block, right? It's hard to think after designing a system of how will I bring in safety? How will I bring in evaluation? All of those things, right? So go from an LLM workflow standpoint to an agentic standpoint. Think about augmenting first and automating later. When we think of agentic AI, we quickly think that, okay, this is where we can just replace a human. We are not at that stage with agentic systems, right? What we need is, we need to augment it first, make it easier for a human to use. Once the trust and users perspective builds in, that's when we can start automating it. Iterate fast, but keep safety in mind, right? Also, choose a hybrid model strategy. One model is not going to work for all of those things, right? Choosing a big reasoning model at all places, even for smaller validation, doesn't work. These are the constraint and enterprise environment. We have limited set of models available out there, right? With open source, when we are experimenting at our own pace, that's good. We can pull in any model from Hugging Face and play in. That works. But with enterprises, that's not the case. They're very restrictive in what models are available, how you can scale them, how you can use them. So think from a hybrid model strategy. These are the things you need to. This cannot be retrofitted, right? So these need to be planned ahead when you start with your POCs. Again, the last point, score by impact, not by shine, right? Make sure that those agentic are actually adding business values at this point. And all of the points that I'm covering here, these won't help you build the best agent, but will help you build the most reliable, human-friendly, more of user-friendly, and help you get a business buy-in, right? Once you get that business buy-in, that gives you a momentum to get actual agents to production. So you got started with POC, right? Now what next? How to go to production and what to keep in mind. So when taking any agentic POC to production, right? Think about memory. Memory will play a big role with this agentic systems, right? If you have a lot of agents working throughout your system, you'll need to start off thinking memory as a service layer. It needs to be short, long, episodic, all of those kind of memories, because each agent will be needing its own requirement. Think from a workflow design perspective, right? As I said, it's stochastic processes. So we need to put in strategic, deterministic things in place. It could be a validity check. It could be an LLM, it could be a machine learning model in place, right? All of those things. Think from a term of model fit and mix, right? It doesn't make sense to overkill agentic solutions, right? Although adding a reasoning model won't solve it. If agents are not, if it's not able to do it, it could be replaced with something else for now. And when the models graduate, we can take it to the next level, right? From scaling and enhancement perspective, think of context engineering. Now, this is a bigger challenge. When we work in POCs, we think of, let's say, I'll take an example of few-shot learning. With few-shot, you might have 10 examples in your POC for an agent to perform, right? But in production, that 10 examples, running it every time will cause latency, will cause more compute. That compute could be used for reasoning or some other purpose, right? So think of context engineering. Could those examples be shortened by run specific, narrowing it down to what's useful, what's not, right? So think from a context engineering standpoint, think of agent ops. Agent ops is a totally new thing that we need to consider. Classical ML ops was one, but now using A2A standard, MCP standards, all of those things, how your agent is communicating outside, inside, all of those things. Tracking telemetry of the model is again a new thing that's coming out. We need to monitor each tool call, each thing, each step that was executed. It's becoming more and more important to debug the systems, right? Think from knowledge boosters. So all of these LLMs by itself are good at answer generation, right? When we make it agentic, we make them good at decision making. But if you want to make that decision in terms or context of your domain or your enterprise solution, that's when added with search and adding a knowledge graph to it gives it a context awareness, right? So think of it as a human brain. How will you think? We have everything mapped out. Till the agents have things mapped out, making them grounded to your enterprise solution is difficult. So this is like, let's say we talked about how to get a POC running. We talked about what to consider for production. Now how to make sure that your teams are evolving from POC to POC, right? Because let's say you built an agent today, would be outdated 6 months from now. Will be new LLMs coming out, more capability, more rigor. All of your agent could be just solved by one LLM if we think that way, right? We don't know, and we need to build that strength or resilience in our teams that we keep on evolving from POCs to POCs. Think of internal benchmarking, right? So whenever we develop a POC, make sure that you have your own data set specific, prompt specific, LLM specific, what is the performance. Now where this will help is in terms of productionization, somebody might need to come in and debug that prompt later. Currently we debug the code same way, right? And you might not be there. So who makes sure that why this prompt was written a certain way? Because it's all feelings out there. So we need to make sure that there is a structured process of tracking it. What benchmarks was it evaluated on? These necessarily not be external, but your industry domain specific benchmarks, right? Design for reusability, make sure that even though one of the POC that you do fails, there are plugin modules that could be reused to other POCs, right? Like, for example, you might have had a search capability built in. That search could be expanded to other POCs. Think of those manner. If you developed a validator agent, can I pick it and put it in some other agent? Because everybody will be building agents, planner, validator, orchestrator. These are some components that will jump in from agents to agent, right? Think of it from modular perspective. Having a human-centered design, right? Again, we are automating things for humans, not replacing humans. So we need to think from that manner, right? It's more of a co-pilot that agentic systems will bundle. At the same time, thinking the UX, UI from agentic perspective is also needed, right? It's not the traditional clickable UI that we all had. It's more interactive. How do you enhance that UI so it builds trust, right? Let's say an agent is reasoning and going to a step. How do you make sure that those reasoning steps are communicated to the human? So there's a trust built in, so they know, okay, agent thought this, and hence it's went there, right? That's more of if I would have done it, why would I have done it, right? More of those kind of things. So with that, this is Dell's example, right? That's where all of the learnings that you're seeing are coming from, like Dell's next best action. It's a recommendation engine for troubleshooting that we have in-house for our internal agents, right? It helps to get customer support faster. It recommends them what should be the next action given a customer reaching out, right? It's the same process we had, if you see, we had a ML model in baseline. We had a matrix tied to it. We identified frictional gaps, rapid experimentation, right? That gave us learning and feel of the system of what LLMs are, what tool calling is, how many tool calls do we need, what is the complexity of tool call we can attempt, right? All of those learnings. Once we had those learnings, we combined those and decided on the experiments that we can go forward, which align strategically with the business, right? It may not be fancy. If a simple summarization solves it, why do you need to build a rack for it, right? So those kind of things. And again, when this POCs graduate to production, we thought of it from both enhancement as well as augmentation perspective, right? Enhancement meaning it could be plugged into the system, but augmentation is, could it be assisting the system further? Could it take to a new journey or new use case for the user, right? With that, we were able to achieve this seamless integration into production. The system is being used by 10,000 plus agents throughout the globe, leading to at least 10% reduction in time for solving each case, as well as reducing repeat dispatches and making the flow more easier. So that covers my talk. Thank you.
Yeah, for the next talk, we'll welcome Michelle Tabat from Salesforce.
Go. Oh, that's going to show my slides. Let me see if I can. Nope. Okay, well, I'm doing it without my notes. All right. Hi, everybody. So wonderful to be presenting today to all of you. My name is Michelle Tabat, and I am a principal researcher at Salesforce. My research focus area is on the business value of applying agentic technology into organizations. So this talk is specifically, I'm really glad that I went after Anutosh because I felt like he really set up a lot of the context about how some of the challenges and some of the strategies, and I'm going to narrow in really specifically on one of the challenges that I hear a lot from customers and business leaders, which is around how do I actually measure and demonstrate the ROI of these agents. So lots of people I speak to very excited and enthusiastic about the promise of making our teams more efficient, making our organizations more productive, but actually how do we measure and evaluate that? That's the sort of frontier area that I'm researching at the moment. Okay, so a lot of the ROI calculations and reports that I've seen have been very simple. They can be like, this task takes 10 minutes, and now we have an agent that can do it. And so we save 10 minutes, and that's the sort of time savings calculation. And that sounds, it sounds pretty good on paper, but in reality, you can sort of badly overestimate value if you're not thinking about the real effort that takes people to do this work and the context of the business in which the agent is working as well. So my research focused specifically on starting with this premise, which is demonstrating time savings starts with understanding the work that humans or people do today, and then how agents actually reduce that effort. So why I think this is really important is I believe it leads us to more credible ROI calculations. So rather than thinking about the idealized or hypothetical time savings that agents can deliver when they're working perfectly and every workflow is perfect, really grounding it in human effort data is where we can see much more realistic time savings calculations. So let me tell you a little bit about the research that I conducted. So to assess time savings, what we actually did was an internal survey of 2,700 of our sellers at Salesforce about the time that they spend on sales tasks today. So how frequently they conduct these tasks, how long it takes to perform these tasks, and how complex these tasks are without agents. And then from there, we were able to use that human effort data to help us build out a sort of more general and scalable framework and calculation model to determine those agent-driven time savings and ROI. So I'm going to dive right into the framework about that now. So this framework takes really sort of two core components. The first is task complexity. So when we want to assess time savings, we first want to understand like how difficult is it to complete this task for, in our case, a seller or a user? How many steps does it take? What's the amount of synthesis that's required? What kind of judgment is needed? Is it a risky task? And typically this sort of task complexity will stay static over time. And then on the other hand, you have agent maturity. How reliable is your agent performing? What's the type of output quality? Or if you're looking to develop an agent for a task, really thinking about what are the depths of integrations that I need? What are the relevant systems and tools? How clean is our data? All of these things. And what I think is really important about this element is that this can change over time. So as Anishtosh mentioned before, like a lot of things that we are working on today are MVPs, pilots, betas. So of course we know that they're not at perfect maturity level yet, but we want to be able to credibly evaluate the time savings that we have today rather than like the ideal performance. We also want to be able to look at the ideal performance so we can sort of forecast into the future as well. And also identify any of the gaps, like what would have to be true for us to improve that agent maturity to meet that ideal performance state. Okay, so this is where the model kind of comes in. So we talked about the framework of complexity and maturity, and then to actually calculate those time savings, we bring in the third element of frequency or task frequency. And this helps us really determine how much time agents can realistically save. So I'm gonna dig a little bit into this framework you can see here. So in the top left-hand corner, you have very, very high complexity tasks. And in the bottom, you have very sort of low maturity or immature agents. And I think we might have all had the experience of trying to use a Gen AI tool or an agent to conduct a task that's pretty complicated. You might have to re-prompt a lot. You have to give different types of information. And then ultimately, you kind of didn't get to the output that you wanted. And so you had to go back and manually do that yourself. So that's kind of frustrating as an individual user, but as an organization, if you were scaling this across your employees, that is an enormous productivity loss. And so that's the type of thing that we suggest to avoid is if you have a really high complexity task, like you have to be really conscious of the type of agent that you're going to bring into that scenario. On the other side, we have the very low complexity task, very low maturity. So here you might, low complexity task, say something that takes you 5 minutes or so to complete. If you have an immature agent, it might still have some value, it might save you a minute or so, but when you really scale that, like are you actually providing significant productivity savings to your team? Like not so much. Whereas if you have a low maturity task with low complexity task, with higher agent maturity, if you have something that can scale across your organization, for example, drafting an email, that's something that not only our sales folks do, but everybody in our organization does. That's where you can see that really scalable ROI for some of those lower complexity, less time-intensive tasks. But the real bang for your buck is up in the corner there with that higher complexity, higher maturity alignment. You want a task that, for time savings, it's a little bit effortful, takes a little bit of time to do, but you don't want it to be so highly complex that it needs a lot of human judgment, requires a lot of oversight, right? So say we took a task, under each of these quadrants, we have some time savings percentages. So for example, a sort of medium to high complexity task might save you 60 to 70% of the time where you apply an agent to it. That's because it's medium to high complexity, you're still gonna need some level of human judgment, expertise, review, etc. So you won't save that full 100%. But if it's an hour task, you're saving 67%, it's like 30 to 40 minutes. And this is where the calculation model piece comes in. Like how frequently are you actually doing that task? It might seem like a great use case, but if you only do it once a quarter, you're really not saving that much time for your employees. So you really want to be able to identify those frequent tasks, because if you're doing a task that takes you an hour and you're saving 40 minutes and you have to do that task every day, now that is significant productivity savings. Okay, so you might be wondering, do I need to go out and do a 2,700 person survey to actually determine where the use cases that I'm looking at fit? Lucky for you, no, I did that work so you don't have to. What I would encourage you to do is when you have a new use case that you're trying to evaluate for agent ROI, is go and talk to 3 to 5 high performers of people who actually do that task today and ask them these questions in the task complexity and frequency bucket. Maybe a little hard to see, but I'm happy to share this afterwards. Ask them the number, how mature is the agent that you have to actually address those tasks today, like learning from somebody who actually does that rather than from building it just from a system lens. The last thing here is, you want to estimate for, can I actually, if it's an immature agent, pilot, POC, how quickly can I make that agent more mature? And if you can't do that in 1 to 2 quarters, that's something you should really consider as a business about whether it's the right time to invest into that agent, right? Okay, so you might be saying though, I want a little bit of the shortcut. Can you just tell me which types of use cases I should apply for my business, or I should apply the agents to organizations I'm pitching my agents to? So I will give you that shortcut. What we found was that where we found that agents save the most time is on those frequent mid-complexity tasks with mature agents, or sort of low complexity tasks that happen very frequently, so multiple times a week or more. That's where you see that real cumulative time savings, and you can actually demonstrate that at scale. Low frequency tasks, limited potential, they don't happen that often, you're not going to save that much time. And low complexity tasks, they don't always, you might think like super easy for us to build, but it doesn't always add up to significant time savings that people can really use to be productive. So the last thing I want to touch on in terms of ROI is actually about adoption. So we've talked about all the things in terms of how you can forecast it and how you can evaluate agent use cases, but one thing that we had in our study was we actually asked our sellers, like, what does good look like to you when you're using agents? They said things around accuracy, style, and actionability, all the things that are up here. And ultimately, if we design something that's maybe technically fantastic, but it doesn't meet what good looks like for our users, no one's going to use it, and there won't be any ROI. So that's one thing I really encourage you to think about when designing agents, is thinking about that human-person interaction. All right. Thank you so much for your time. This is how you can apply this framework to evaluate and prioritize use cases for your business, to forecast your agent time savings, and to measure time savings alongside other business value metrics to show the full value. If you have any other questions, I would love to chat afterwards. Really appreciate getting to chat with you all today.
Thank you, Michelle. Our next speaker will be Diva Taka, who is a senior program manager from Google.
Right. Hey everyone, thanks for being here. I'm going to talk about this one specific work that we've done, and through the end of it all, I just want to convince you that there's a lot of value in exploring what new interaction patterns are emerging as we kind of deploy these agents. I feel like the last talk was an excellent example of thinking about those real-life human-AI collaboration frameworks. And if there's anything that you need to take with this, is that you need to get a much better, deeper sense of how multi-agent frameworks are coming together as they're deployed in really messy organizational structures. These agents don't operate in isolation at all. This work was the best paper at Kai. This is with collaborators at Stanford and Google. And you've been hearing a lot of hype around software changing in itself, right? Like, we'd love to think about ways in which AI will replace software engineers, and you've got like this whole stack of tools which are coming in to think about like how much code these models are now writing for us. Great. But there's software in itself is a very messy way of working together, where PMs, developers, and designers kind of like come together to actually prototype, think about what to build in itself. And there's going to be a lot of judgment that gets exercised over here. This is a messy process that's not just a value function of like how much code you can write, but how you choose problems and how these teams come together in their own respective organizational incentive structures. So we felt this is an important enough question for us to study, which is how do teams now prototype software in this new paradigm of LLMs, where a lot of the code is being written for them and the process could theoretically be accelerated. So how do you think about like this new design framework in itself? So us at CI researchers, we love to take like one narrow domain and kind of like prove it out broadly in those spaces. So we kind of like got together multi-stakeholder teams comprising of PMs, UX, and developers together, mostly ML researchers, to tell them that they're designing like this new marketing content creator agent for their clients, which is going to write like a whole bunch of marketing content for them. And they're creating like this generative AI tool, which is run through Google AI Studio and uses Gemini at the backend. Awesome. So we have this idea of like how current roles look like, and that is exactly the prescription that we give them, that engineers should be thinking about like what kind of like a few short examples to design, how can you like think of metrics and find the right data and so on and so forth. So we gave them like the exact tools that they would be leaning onto as in their current roles, and we wanted to see how these roles are now shifting. And they had like a bunch of guides to kind of like think through product design in these new spaces in itself, which I won't go too deep into. A sneak peek into our findings. One, there's like this really large focus on content in itself. So there's this wrangling that's happening now, which is around the model outputs being reverse engineered for what kind of prompts you should be writing, what kind of agent instructions that you should be developing, what kind of like golden examples that you should be developing in itself. So it's really interesting how like the prototyping paradigm in itself is being reliant on the LLMs that we've built at the get-go, which in itself comes with a lot of priors and biases on like relying just purely on current model design in itself. So thinking more about like how these golden examples have been curated is extremely critical, and this is happening purely through the modality of content. Evals are extremely hard, as we all know, but this shows up even more so when people try to exercise their own domain expertise onto designing these prototypes. So you'd expect that a PM would look at evals in a very monolithic way, and a designer would care about very specific functions. That's completely changing. And there's a few key ways in which we like to think about like these silos kind of breaking down. So in an earlier world on the leftmost side of it, you see that expertise was kind of like really guided, that as a designer you're taking very specific decisions, but that's completely changing because now all of the people in these collaborative teams have a shared surface through prompts and content to be able to wrangle these prototypes in ways that they just couldn't. There's this like big focus on like simulating things being really hard, and that's changing because now you're seeing like engineers in itself simulate how their users might kind of like come through with these LLMs to understand like what these journeys are like. So the workflows in itself for engineers are changing, and the expertise that they have is kind of like getting augmented in ways that you wouldn't have expected. Earlier in a predictive AI world, which we all don't even remember about now, there was a lot of like uncertainty around AI outputs, which is now changing because you're able to wrangle things a lot more through the prompt space. But with it comes kind of like its own challenges, because then you're getting like really limited and siloed with what kind of like prompting that you're doing. Technical decisions, again, like completely changed because now nobody gets, only engineers don't get to decide what kind of data sets you're using. Those decisions are kind of like getting more and more decentralized in itself. And the same thing is happening with like user-centered decisions, and prototypes are changing from these like really low fidelity kind of like mocks towards actually going towards things which are usable and functional, because you have like these tools at your disposal in itself. So content is the hero of it all. Collaboration is the hero of it all. So if you're designing agents, care about how these agents work in a very, very messy organizational structure where humans and humans come together with multiple agents to kind of like work through the design process in itself. If you want to reach me and talk more, that's my email ID. Thank you so much.
So thank you again, all the speakers, for the amazing talks. So next, we will have Jocelyn from Berkeley Responsible Decentralized Intelligence Center on stage to announce the winners for the Agent X hackathon and the LLM Agent MOOC hackathon. Yeah. I think just quit. Quit, yeah. So we need all the winners not tonight on, right?
Yeah.
We organize this, or should I organize? I mean, I can help. I can help.
If all the winners, once I announced you, please line up on the left-hand side and you'll have a chance to speak. And we will help you line up. But first off, I'm going to talk for a few minutes just about the competition before I announce the winners. So thank you to everyone who participated in the competition. I'm Jocelyn. I'm a Deputy Director at the Berkeley Center for Responsible Decentralized Intelligence. This was our second agents competition that we ran. We ran one in the fall. This was the follow-on to that as part of the Advanced LLM Agents MOOC. And as you can see, we had almost 1,000 teams participating, 500 startups joining, and over 100 countries represented. So we had $450,000 in prizes and resources from our sponsors. You'll be hearing from a few of our sponsors also after I announce the winners. But thank you to everyone who participated in that. So the winners for the entrepreneurship track, I'm very pleased to announce. First place, Raycaster. So congratulations to you. And maybe I'll ask you to hold your applause until I announce the fourth place too. Second place, TradeStack. Third place, WeCruit. Fourth place, Minimist. Cheers. There was a special prize track from Auth0 for people utilizing Auth0 solutions in their project. And I'll announce all the winners, and then we can applaud. First place, TradeStack. Second place, Chris Pro. And third place, Anub AI. So congratulations to all of them. We also had quite a few winners in the research track. That was very well represented. First place for reasoning and planning, Nova Sky, and second place, Agent V-Bench. Congratulations. And for AI Safety and Alignment, which was sponsored by Schmidt Sciences, we had 4 tied for second place, but the first place was Team Hoosier. Tied for second place was CVE Bench, MedPair, COP, and Ken Hwang, Vineeth, Narajala, Aiden Habler, and Akram Sharif. So congratulations to all of those for AI Safety and Alignment. For the rest of the research track winners for benchmark and evaluation, we had 3. The first place was Agentic Benchmark Checklist. Second place was a tie between Agent Synth and Online Learning to Prompt Leaderboard. Congratulations. Agent Architecture, first place GNX, second place AIOS. Congratulations to them on architecture. For multi-agent, first place EvoGit, second place Social Agent, and third place Efficient Training-Free Online Routing for high-volume multi-LLM sending. Congratulations to all of those research winners. And these were all of the sponsors who contributed prizes and resources, and what we'd like to do is welcome a couple of our sponsors up here. If you are one of the startups or that we announced as a winner, please line up against this wall over here and we'll have you present for a few minutes if you're here. I'd also like to welcome up from Lambda, Ryder, and Auth0, their leaders, to say a few words.
Hi there, everybody, and congratulations to the winner. I am Bhavna Singh. I'm from Auth0, CTO there, and which is acquired by Okta. Can everybody hear me? All right. Well, congratulations to the 3 winners we called out for using our platform. More so, I would say, this is a great gathering, some great ideas, but what I love about these ideas is that you're using the technology, which is, of course, evolving very fast, to implement and bring true use case that will help the humankind, I would say, in different ways. Efficiency, optimization, but most importantly, bringing the price or the cost down. So thank you for all the hard work you're doing. I will also call out that our platform certainly helps with key capabilities for you to build tooling, for you to build agent-to-agent conversations to make it very easy, but also to help you build MCP capabilities. So Whoever used it, thank you so much for leveraging all those capabilities. Hopefully it was easier, and we would love to take some feedback from you as to how it was and your experience in leveraging these capabilities, because we are also evolving them. Thank you so much, and congratulations, everybody.
And Dennis from Writer.
Hi, y'all. Thank you. Congrats to all the winners. Super excited to dig into the demos and check out the awesome stuff y'all did. My name is Dennis. I'm a member of technical staff at Writer. We're hiring. Come check us out. We have our proprietary Palmyra LLMs. We're doing all kinds of cool stuff, especially with Agentic AI at Writer. We're up in the CARE lobby. We have 100 open roles, so please come check us out. We want to hear from you. We want you to ask us questions. And that's it. Congrats again to all the winners.
And Juana. Oh. Oh, from Lambda. Yeah.
Hi, everybody. My name is Leah Alcantara from Lambda. Congratulations, first of all, to all of the winners. Incredibly excited for all of you. I'm a machine learning engineer here at Lambda, and just want to also kind of mention that we are, you don't know us, we're a GPU compute provider, and we have a ton of open roles. I can't speak more highly of this company and all of the amazing things that we're doing right now. So feel free to come check us out. We have a booth on the 3rd floor, and also we're actually currently speaking in a presentation on Agentic AI and Neural OS upstairs on the 5th floor. So please come talk to us, and congratulations again, everybody.
What I have here now is the list of startups and the order that they're going to speak. So I don't know, have they all lined up in this order?
I don't know. I mean,
Yeah.
I don't know.
Okay. First up is Team Hoosiers. And then second will be Agent Synth. Third will be ABC. Fourth will be a noob. And then Agent. So if you could all line up in this order, hoping you can see that. All right, I'd like to welcome up the first team, Agent Synth. Team Hoosiers. Yeah.
Hi everyone, we are Team Hoosiers. My name is Jen, and this project is done with Zhichuan Li. So in this project, we're trying to propose a privacy-enhanced development paradigm for multi-agent collaboration systems. So given a multi-agent collaboration system, there are multiple communication channels, including the inter-agents and the agent to other environments, such as tools, LLMs, and the users. However, any of these kind of components, entities could be malicious. For example, agent could be malicious, or because of third-party tools and because of the third-party LLMs, this can also be malicious. So in these projects, we also see that the sensitive information disclosure is also already being recognized as one of the OWASP top 10 vulnerabilities for LLM integrated applications. So in these projects, our research question is that how can privacy-enhancing techniques can be effectively integrated into multi-agent collaboration systems while ensuring like seamless deployment. So we have like 3 design goals. So our paradigm is called the MARIS, which is a multi-agent data safeguard development paradigm. So we have 3 goals. The first one is configurable and customizable data protection policy, which means that we want to have a single configuration files that can enforce these kind of policies. And the second one is that flexible monitoring across all communication patterns. So as I mentioned, we have like a different communication channels. We want to protect all the protections on top of this one. And the third one is a seamless deployment. We don't want to change a lot of code in the applications, but we still can deploy this kind of safeguard. So overall, we implement our design goals into major platforms, LangChain and AutoGens. And yeah, to summarize that, we propose a privacy-enhanced development paradigm for the multi-agent collaboration system. While it is specifically designed for the sensitive disclosure attack, but can also be extended to other detection purposes. And we also have some like a privacy assessment framework for evaluating the MACS under like different privacy threat scenarios. Thank you for listening.
Yeah, hi everyone. We are Agent Sense team, and I'm Jing Chu. I'm going to talk about our project on scalable task generation for general computer use agent. As we all know that our agents are currently much more powerful in solving complex and multi-step computer use tasks like booking flights, booking hotels, or some other tasks. But data collection for this realistic training and evaluation is very scarce and it's hard to scale. So existing benchmarks mostly rely heavily on like human demonstration, which is pretty expensive and hard to scale. So our project, Agent Sense, offers a scalable and low-cost pipeline to synthesize these high-quality tasks, which achieves only $0.6 per trajectory. And the key idea behind this achievement is using information asymmetry, that is, to generate simple subtasks and chain them into a complex one. And from that, we enable control task complexity. So our pipeline starts with a random persona, which enables a wide diversity of the tasks. And from the persona, we propose initial task and then iteratively generating follow-up tasks to chain them into to compose them into a final and complex task. By chaining different numbers of subtasks, we can control the task difficulties in a controlled way. So for example, we chain 2 subtasks, we get some low difficulty. If we chain many subtasks, we can get a very high difficulty. Based on that, we create a benchmark and we evaluate several sorter models like OS 4 Mini, Gemini 2.5 Pro, etc. And it seems that with increasing the difficulty, even the sorter models are struggling with our benchmark. And with that, I want to conclude that I hope Agent Sense can push forward the development of the agent training and evaluation. Thank you.
All right, hi everyone, I'm Yu Xuan, and I'm excited to introduce our research around AI agent benchmarks. So as we can see from recent analysis, AI agents have become increasingly and surprisingly capable. However, we are still not sure what agent can do and what agent cannot do, and that's exactly why we need AI agent benchmarks. So a typical AI agent benchmarks have a real-world task. Well, an agent needs to interact with the environment, which typically contains a few simulators of the real-world scenarios, and then we'll have a grader to look into the agent's output and decide if it's a success or failure. So we have 2 challenges. One is a complex setup. We need to set up DB websites and container. We also need to deal with non-calculated data, including free-form text, code, and function calls. This kind of complexity raises a huge surface of unreliability, and what if there are bugs? To address it, we introduce our Agentic benchmark checklist. We want to help benchmark builders and users to detect validity issues in an agent environment paradigm and various evaluation designs. We also propose guidelines to help rigorous reporting when validity cannot be achieved. We identify many issues that can skew benchmarks and results and findings. These issues can cause up to 100% misestimation of agent performance. So feel free to check out our work. Our post is on the second floor of the building. And let us know if you have any comments or questions. Thank you.
Good afternoon. My name is Alex Garcia, and I am the CEO and co-founder of Anube.ai. We're all here because we're excited about the promise of autonomous agents. But as we deploy those agents, and having deployed the agents firsthand for the enterprise, I come across one very critical question, is how do we actually measure success? It's easy to mistake success for agent activity, but in actuality, activity does not measure or drive results. And that's why we came up with the key agent outcome, which is a time box metric for defining success for the agent. Each agent outcome is validated by a human-in-the-loop checkpoint, and this validation process ensures accountability that every agent's contribution. This isn't just about automation, this is automation with accountability. And with this methodology, it aligns how customers are charged for the value that agents are achieving for them. Thank you.
So next one is scheduled to be the team of Agent God. Is anyone here? Yeah, come. I mean, like, please, all the other lightning talk speakers should line up there. Yeah, yeah, come.
Good afternoon. My name is Zhizhou Chen, and our project is repurposing Agentic orchestrator for safety evaluation of tool orchestration. So basically, the introduction of autonomous tool use have turned LLMs into powerful agents. However, when those tools are misused, these agents are practically turning into potent adversarial entities. So that is that, it might be good to have a pre-deployment testing framework so that we can yield potentially unsafe tool workflows as many as possible and address them ahead of time. So we argue that this testing framework must satisfy 3 requirements. The first one is that the framework must have the knowledge about the capabilities and how to use the tools. And the second one is this testing process has to be realistic and scalable. And the third one is that this testing framework must have the privilege to invoke the tools so that it can validate these identified unsafe workflows. So our observation is that actually the LLM orchestrator within the LLM agent system innately satisfy all the requirements. So in this project, basically we turned LLM orchestrator into safety evaluator, and then we did a baby version of proof of concept. And for more details, please read our project report. Thank you.
Yeah, hello everyone. My name is Herman. It's a huge privilege to be here. So our project started with simple observation. So almost, I can think of more than 30 years of history of a public web, the input forms remain the same. So you can see it on my screen. Why is even problem? Because actually the role of these input forms dramatically change. So for example, finance companies now spending like 55 USD per click in search, and 75 forms are actually abandoned while users started them. So that's why we in the cross-disciplinary team created the voice agent that actually can guide you through the forms. They contact you from the phone. And I think the main idea was to experiment with tool calling. So this agent actually have a set of tools that can, in real time, fill out form for you, change the the things inside this forum, and that's all. So yeah, I think my time is up, and yeah, you can drop me a message if you're interested in this.
One here very interested in healthcare. Awesome, only one. That's very important to talk about our project MapPair. So MapPair stands for Measuring Physicians and Artificial Intelligence Relevance Alignment in Medical Question Answering. I know lots of recruiters and great companies are here, so hire me. I'm on the job market, final year PhD student. So the project starts from a very interesting idea. Like people ask about, so how physicians are interpreting this patient profile, how does large language models are things in this input profile. Are they really alike? It's pretty dangerous if they're not alike, so that's why we're asking this question. So in a study, we formed a MapPair dataset, which formed 2 datasets into a patient profile and a query. And then we invited 36 physician annotators and 4 large language models to first do the classification and then do the relevance labeling per sentence level. So our results are very interesting. As you can see, if large language model follows the human relevance labeling in the sentence level, in the 4 datasets that we form, it improves the performance. As well, we also tried large language model use its own high relevance sentences to do this improvement, and we can also see the same relevant trend. So that's all for our project. Thank you so much, and look at our project. Thanks.
Good afternoon. I'm Chinong from GNAI's team. I'll be presenting our work on agent-based autonomous manufacturing. The core problem we are tackling is that traditional manufacturing is too rigid for today's dynamic market demands. Our solution is an AI-driven system where workers can control complex machinery using simple natural language. We use an AI agent that leverages standard digital twins called asset administration shell to understand the factory's capabilities and a model context protocol to execute our commands. We validate these 2 ways. First, we conducted a large-scale experiment with 4,500 industrial data files, showing that the top LLMs can automatically generate the control code up to 96% of success. Second, we demonstrate a complete end-to-end process where our agent is successfully manufacturing an AFP and motor cores. Thank you.
Yeah, there should be a link. This one. Click the online side.
This one here?
Yeah, this one here. F11. Do I need? So hello everyone, here I'm introducing the UGit. I'm here, I'm Bicheng Huang. First, let me get through what's the pain points in today's coding agents. As you can see on the right, it's like how a typical coding agent works. There's an agent, you generate code, you run tests, and if the test is good, it's done. If the code is bad, it writes different codes. However, there are some issues here. One is that agents run like in a single-threaded mode. Like typically all the agents model, they run in a single-threaded mode. And second thing is that it's hard for agent and human to collaborate, or the human-agent dynamics, because either is agent do it all, or it's like human-agent frequently interact with each other, saying like human says you are doing it right, you are doing it wrong. And the third thing is that reward function doesn't work. The reward function means here is to how to measure how good the code is. For example, you are saying like the code is 90 score good. That is very hard. You can't just give a single scalar value to how good the code is. And our solution to that is to bring down everything and redesign everything. So the state of the agent is the graph. The code evolves, not actual. And the collaboration is done through the graph itself, not communication.
And there are no scalar reward here. Everything is partially ordered. There's no scale. Everything is done here. And we have some nice website here, as you can check out in the poster. And thank you, everyone. So you will get there's a final code that LLM models are known, and evolution is for creating the unknowns. And we are doing that. Thank you.
Is the team of Agent VBench here? If not, the next speaker will be the team of Youth AI Safety.
So much. Hello, everyone. We're a research team from University of Illinois, working on designing safer generative AI experience for use. And my name is Yaman. So large language models are reshaping how users interact online, but the current safety measures often overlook their needs on developmental stage. For example, moderation systems may capture the explicit content, but they often miss what is subtle and serious from the user perspective. Such as teenagers receiving validation from AI about their intimate relationships, about their emotional vulnerabilities, even their self-harm or suicidal ideations. To better understand what are the risks behind of their interactions, we developed a use AI risk taxonomy and also created a data set from their real chat logs with generative AI to reflect on their risky interactions. And also, we trained a safeguard model for use specifically that improves very much of the specific risk of them. And our ultimate goal is making the AI environment safer and more developmental appropriate for use. Check out the details of our website, and we have a poster on the third floor around the main stage. So come to talk to me. Thank you.
Hi, my name is Julius, and I'm here to present to you iWhisper, our interactive visual spatial reasoning benchmark for LLMs. So with the rise of LLMs as agents, there's also been a growing interest in applying this world knowledge to the physical realm with robotics and the like. However, there's a large gap. LLMs have a lot of world knowledge, but it is known that they struggle to apply that knowledge to the physical world. So how do we help this? Well, the first thing, we want to accurately measure their spatial reasoning and visual grounding abilities by building a benchmark. So what we did is we built a Unity sandbox, and we built on top of it an LLM agent API that works in a way that agents can receive observations from our simulator and apply structured text back as actions. Inside the sandbox, we built a 3D puzzle suite by implementing popular puzzles like the sliding tile puzzle, the geometric puzzle, and the Rubik's Cube. This runs on any operating system, browser, and even HPC clusters. We support any state-of-the-art VLM APIs, and we can even do analytics on reasoning across modalities. We have automatic testing and evaluation, and if you're interested in finding more out about our results, you can meet me at the poster session or go to our website, iWhisper.ai. Thank you.
Hi, I'm representing Team TARS, and we built Simera, a general goal-oriented agent via simulative reasoning with world model. So existing work usually develop architecture for specific environments, and this approach usually suffers from issue with scalability in terms of business and error propagation, and does not offer a clear path towards general intelligence. But humans, on the other hand, are generalists with a single cognitive architecture, but can achieve goals in diverse environments. So human reasoning is not just linear autoregressive reasoning, but also forward-looking simulation-based reasoning using internal world model. Based on this, we built a general architecture for optimal goal-oriented agent, and we overcame the limitation of LLM-based autograph reasoning by introducing more model for planning via simulation. So for experiments, we improved the performance substantially in web browsing tasks. A quick demo. So this user is asking Simura to plan a trip from Pittsburgh to SML 2025. And then Simura starts to look up info, and then find hotels, search for flight, then research action, compose a response to the user. So feel free to scan the QR code to check our blog post and demo, and we have our poster over there. Thank you.
Okay, hi everyone, I'm Yuxuan. I'm excited to introduce our project CV Bench, a benchmark for evaluating AI agents' capability to exploit real-world web application vulnerabilities. So recently, we are seeing an increasing trend where AI agents potentially present major cybersecurity risks. And to measure the real risk, we built a benchmark, CV Bench. We picked 40 high critical severity CVEs from the real-world benchmarks and used open source web applications. We also manually reproduced and verified each task with at least 2 iterations. So in our benchmark, the agent needs to interact with the web application, and we have an application-specific evaluator to evaluate the agent performance. In our experiment, we found that a GPT-4o-based agent can exploit up to 13% of the CVs. So if you find our work helpful and interesting, feel free to check out our paper. Our poster is on the 2nd floor of the building. Thank you.
Hi, this is Team DAMCS. I'm excited to share with you our vision on future of multi-agent systems. In the future, we imagine that agents are deeply embedded in human society. Each of the agents act decentralized way, and by communicating with others, they form a network with other agents and with other humans. Together, they can collaboratively plan and act. Okay, so here's our DAMCS framework. The DAMCS framework contains 2 components. One is the decentralized adaptive knowledge graph memory. Each of the agents maintains individual knowledge graph memory. By communicating with others, the agents are allowed to share states, share task progressions with other agents, and together they're able to complete tasks cooperatively. On the right is the MA Crafter benchmark. So this is a benchmark designed for evaluating cooperations. This introduces item dependencies and introduces cooperation dependencies and constraints. So here's DAMCS agents operate in an open world environment. Their goal is to gather a diamond together cooperatively. And there are cooperative actions such as share, allowing agents to share items with each other. They have to read and through communicate in order to complete the task together. Check out our project by scanning the QR code, and happy to talk with you.
So hi everyone, my name is Fang Zhou, and I will be introducing our work, efficient training-free online routing for high-value multi-LLM serving, which is a joint work with NVIDIA. So as LLM becomes more widely used, balancing cost and quality becomes critical. LLM routing offers a solution by routing query to the most cost-efficient model But the most existing work primarily focuses on offline scenarios and fell short in online realistic settings. And they struggle with high routing latency, deployment costs, and complex query arrival patterns. So to tackle this, we proposed the first training-free online routing algorithm. So we first estimated query features, for example, the cost and the quality using approximate near neighbor search algorithms. And then we formulated the routing as an MILP and proposed an efficient routing rule with learnable routing weights. So these weights are learned on just a few initial queries and can effectively guide future query routing. So we back our algorithm with formal theoretical guarantees. Our algorithm achieves a lot in performance, cost efficiency, and high throughput. So feel free to stop by our poster for more details. Thank you.
Hi everyone. Let me start with the question. Have you ever scrubbed through a 10-hour lecture video just to find that one slide you needed buried at hour 7? Or tried to recall what someone said in a keynote, maybe about multimodal search, but couldn't find the clip before your meeting? Yes, we have all been there. Tech events and online lectures are packed with insights, but they are lost inside hours of video. It takes too much time to get to what matters. LearnPod changes that. It's not just search, it's an interactive AI tutor that watches entire events and lectures for you. Powered by a multi-agent LLM architecture, LearnPod understands video content and transforms long recordings into a conversational knowledge base. You can then ask questions and instantly jump to the most relevant segment. AI is going to change videos forever. Videos will become fully interactive and immersive, alive with meaning for every learner. And that's the future we are building with LearnPod. Please come visit us at the poster area to learn more. Thank you.
We live in an AI world. I think we've already established that. But the hype and marketing that currently surrounds it is significantly different from what it truly is. To know something, there are two ways. One, to know what it is, and the other, to know what it isn't. So today I want to focus on the pitfalls on the over-reliance of AI by understanding its limitations, so that we could be more confident and intentional when we do use it. At a very high level, LLMs are still just autocomplete on steroids. They don't understand meaning. They predict the next token with the highest probability. This works great for several tasks in a wide range of domains, but we need to be cognizant of the fact that linguistic fluency correlates well with logic. So it looks like intelligence, but real intelligence is about abstraction. It's about forming mental models and understanding and conceptualizing ideas. This is why AI is great for scaffolding, but not for skyscrapers. LLMs are great at generating boilerplate and exploratory tasks. But if you're doing anything complex, they fall apart. Let's take an example where language and logic fully decouple. Legal documents. In law, a single wrong word or even a single misplaced word can change the entire meaning of a legal contract. LLMs may generate something that sounds correct but lack the required legal precision. In addition, there are already legal cases where AI-generated legal briefs include fake citations and hallucinated case law. Even the so-called reasoning models that use chain of thought are still orchestrated token emitters with better analysis and tools. Is there really a deeper understanding behind the curtain, or is it just flowcharts pretending to think? So if you're doing anything complex or novel, don't outsource your intellect to LLMs. Use AI for speed, not strategy, for suggestions and not decisions. And always perform your due diligence and keep abstraction and understanding, the hard part, for yourself. I'm not saying any of this because I'm an AI doomer. I use AI every single day, and I build agentic systems. Come check out our project, Smooth Operator. Even for this talk, I used AI to formulate my thoughts, but not to form them. I care deeply about this space, and we need to set reasonable expectations so that AI can grow at a steady and meaningful pace into something transformative, making the world a better place. Let AI augment our intelligence, but not replace it. This is Sainath from iCognito. Thank you.
Perfect. Okay. So hello, everyone. Today I will be presenting the COP, Agentic Red Teaming for Large Language Model using Composition of Principles. So as we all know, as LLM advances, they still remain vulnerable to existing jailbreaks attacks. However, current red teaming methods have significant limitations, requiring white box access, consuming excessive tokens, or being model specific. So our solution is pretty simple, and we propose an innovative agentic workflow that combines simple human-designed attack principles to generate effective jailbreak strategies while using dramatic fewer queries. So here is the overall pipeline. So first of all, the input is the harmful query, and then the red teaming agent will, based on the input, and then combine the appropriate attack principles to form a composition of principles, and then to shoot that out as a new jailbreak prompt, and then using this feedback to create, and then we're evaluating the effectiveness using the judge LLMs, and then use this to feedback, increasing the protect attacks. And then here's the illustrative example of how our COP works. And then in terms of performance, as we can see that COP significantly outperforms the existing method, providing developer a more efficient and transparent way to identify vulnerability before model release. And that's my talk. Thank you.
Or if you want to use this.
Hello everyone, my name is Eduardo and I'll be presenting Continuity of Mind, Grounded Memory-Driven Cognition and LLM Agents. Our research tackles the challenge of enabling structured, memory-driven cognition within large language models. We introduce a meta-agent architecture that repurposes the context window as a dynamic substrate for cognition. At its core, a hidden controller routes control based on the context among specialized agents for perception, belief formation, episodic, and conceptual memory integration, as well as decision-making, creating an explicitly structured external global workspace. This architecture supports both reactive, fast System 1 behaviors and deliberative, structured System 2 reasoning. It significantly improves temporal coherence, interpretability, performance on complex tasks like ALF World, all without gradient-based training. While today's LLMs are capable of intelligent thought in latent space and can generate fluent outputs, they lack persistent internal reasoning. They do not understand their own thought processes before externalizing it. Our immediate contribution is an explicit external framework for coherent memory-integrated reasoning. Our longer-term vision, however, is the emergence of artificial experience, models that internally articulate and reflect on their own intermediate thoughts. We believe this points to a path forward where interpretability and performance are not at odds, but mutually reinforced through structured, persistent cognition. Thank you.
Hello. The story of treating cancer is built on a broken foundation where we wait for cancer to show up and then we treat it. At CRISPR, we built an AI agent where we can analyze all pathways of cancer before cancer has even occurred. How we do this? By applying simple theories like the two-hit hypothesis. We utilize the first mutation, which is the RUNX1 mutation. When someone develops this or inherits this, their likelihood of getting leukemia increases by 50%. Combined with another mutation known as the second-hit hypothesis, now this is when the beginning of cancer phase starts. Our foundation model is able to analyze genes and it's able to predict what's the likelihood of these genes being pathogenic, and we're able to give it a score which determines the accuracy. Once we identify a gene that's likely to be a tumor or could become cancerous, we can then predict the second hit, and we can predict what's the likelihood where the next cell could transfer before it has even transferred. Our foundation model also allows us to build proteins where we can then disrupt and kill these cancer cells using CRISPR therapies. Thank you so much.
Hi everyone, I'm Sarah from TradeStack, and we're a pre-seed AI startup in London, and we're building an agentic back office for contractors like plumbers, electricians, and so on. And I'm just going to share three sort of key insights from what we've learned over the past 12 months. Is from a user interface point of view, this target audience really it has no interest in any new interfaces whatsoever. So we have to leverage the existing interfaces, especially WhatsApp, email, and phone. And then from an MCP point of view, it's obviously great building in this era of MCP, but we've learned that building your own toolkits can give you your own control, and especially when it comes to auth, it gives you important control. And then lastly, human in the loop is really important for us. So our business model is services as a software. So we actually build for our own internal teams, which means we have internal feedback loops, and that obviously is quite helpful in delivering a premium sort of service. Thank you.
All right, hi everyone, my name is Noah. Can I see a quick show of hands how many of you used ChatGPT in the past week? Of course, basically we all use it and it's so powerful, but it also leads to problem. For example, in the recruitment industry, basically everyone is using ChatGPT to help them to refine their resume. So everyone's resume looks so amazing, but what's real, what's not? What's actually from the candidates, we don't know. And there's only way to figure that out, that's by actually talking to them, because you can't fake your first, second response to a question or your problem-solving skills. But the only reason why we are not offering everyone a chance to interview is because it's so expensive. But what if we offer a solution to help you to give everyone a chance to interview and see their performance? That's what we build Recruit. So our solution is that we only need your job description, and then we'll build an interview experience customizable to your candidates based on their background and your JD. And also in the end, we'll give you a report to see how they performed, and you could rank them. And while they are talking, we'll also give you an emotion analysis to see if they actually engaged into the position and the interview process. And also we use AI detection heat map to track, are they using AI cheat tools to help them go through the interview process. So clearly it won't pass our interview. And in the past 4 months, we have done 7,000 to 8,000 interviews already, and we have helped 2 incubators and 2 consulting firms and 7 academic institutions to do their screening process. So if you are interested, let's skip screening, start selecting, and contact us. Thank you.
Hello everyone, I'm Tim Husers, and I'm going to present our research across to data harvesting and polluting in multi-tool empowered agents. Let's take an example. A user is asking for some financial investment suggestions to a language model, and this model can invoke these 3 tools. It can invoke Yahoo Finance to fetch news, stock data API to fetch stock price, and data analyze to do the data analysis. And it may have this control flow. We call it, this execution order, we call it control flow of an agent. And to look into the detail of the description, Yahoo Finance description mentioned that useful for when you need to find financial news about a public company, input should be a company ticker. However, as we see that user input doesn't provide such knowledge, it's only mentioned that Apple is not the company ticker AAPL. So here is a knowledge gap. And if a malicious tool claims to provide such knowledge, it can hijack the control flow and sneak into the right in front of this Yahoo Finance. In this project, we study this threat, and we call it cross-tool data harvesting and polluting. Once hijack successful, the malicious tool can perform the data harvesting attack to steal privacy information, or the polluting attack to pollute the agent context. And we built a threat scanner to investigate how prevalent this threat is. And we found that a lot of open source tools in LangChain and Llama Index are vulnerable to this threat. And thank you. If you are interested, please feel free to find me in the post session.
If all the startup team founders that just spoke would like to come to the front, we'll take a quick group photo with our photographer here. And can you put up Agentic AI on the side? Yeah. So founders, if you want to come to the front, we'll take a group photo. They already took.
So thank all the speakers for the very interesting 19 talks. So now we will dive into the second session of the afternoon, which is about the foundations of agents. By the way, I'm Jing Xuan. I'm a postdoc working with Professor Dong Sang. So I will be the session chair for the previous session, this session, and the next session. So if you have questions, please come to me. So our first speaker for this session is Jose Reynal, who is a professor at UC Santa Cruz.
Welcome. So what I'm going to be talking today is a work that we are doing in Santa Cruz, and it's how to build agents for chip design, hardware agents. A little background to see what we are doing here. I'm a professor at UC Santa Cruz. My background is computer architecture, so chip design, but I always have been doing how to improve the productivity. Obviously, that includes design, verification, different aspects of the chip design. But today the focus is AI agents, how to build agents to help me improve productivity at this globe. Now, obviously, this is a work for a lot of my students, myself, that's my Git commit history. I like to work too on the code. So what's the goal? Because I think it's important we set the goal, what I'm working about. So the idea is to improve chip design productivity. And this includes the coding, the verification, a lot of effort on optimization parts. And there can be some cloud, either CLI kind of interface, and this is something we are working on. It's not how to integrate AI on the EDA tools. There's a lot of people working on that area. It's a different community. Here is how to improve the productivity, much more like what we are talking here at the conference. Because it helps you to understand how do I approach the problem and what do we do. I think it's important to what is my view on LLMs? How do I see them? How do I use them? In a way, they are sort of an alien intelligence. So they are better than humans in some things. So they are better as excellent translators. So they can translate to English, French, much better than me. They have excellent recall, or not excellent, but very good recall, much better than humans. But in some way, they are worse than humans in consistency. They have maybe not very good term, but funny failures. They have many strange failures that you have. So how I'm gonna make it work with this? Well, the first thing is I'm not going only the LLMs, I'm building on agents around. So the agents, I tend to call it many times grounded agents. I tend to call it more verifiable agents whenever I can. The idea is that we always have coupled the LLMs, whatever we use, with checks, and whenever possible we verify. In hardware we can verify many times the results. So what we keep doing is building pipelines in which you can have an output of the LLM and then you check if the result is correct. If not, you keep going back and you keep iterating. Because we have these verifiable agents that we can build so we can iterate and go towards a better solution. So we check with the EDA tools whenever possible, like do we have mistakes, like combinational loops? Do we have things that they shouldn't be happening there? And if we have a verification infrastructure that usually in hardware you tend to have it because it's very expensive to do a mistake. So then you can check with the verification infrastructure. Whenever possible, you validate with previous results. Many times you are doing optimization, you are just transforming the code to get better quality code. So in that case, we can use formal tools to formally prove that the code is equivalent, even though they look very different. So at the end of the day, there are many blocks, and it looks like a compiler. So you have blocks that have the typical React loop, so you can have some reasoning to expand. You might want to extract inputs and outputs, and you have a compiler-like flow. So what makes hardware special is that it doesn't work with a normal, Python is a von Neumann architecture, hardware is not, when you program hardware. And there are many issues. Not von Neumann, pipelining is a very specific way of parallelization that the LLMs don't have very good training and they do a lot of mistakes. And there are a long list of the slightly different on the programming language. But for the non-hardware people, I have a little slide. So if you were having a program like this, you say the result of C is the result of multiplication A and B, and then you write assert that C is the result of the multiplication, and let's assume that this does multiplication. In hardware, this can fail. And the reason is because the result might not be this cycle, might take 2 or 3 cycles later. So there are a lot of checks that you might have to do that the code generation on the LLMs don't have that assumption because there is not enough training set for this type of languages. So how do we do? Because it's a short talk, I'm just going to show you a high-level view what is the idea. So we have 2 programming languages. One is Verilog, the other one is Chisel. So how do you do a reverse pass? So you can build a compiler-like infrastructure, putting the LLMs in the middle to solve this, and at the end there is no hallucinations because you formally prove that the result is correct. So what do you have? You have original Verilog, you have a fixed Verilog, so you have a change, and the original Chisel. You want to have a patch on that Chisel. Now, the first thing, you have to narrow the space because those files are gigantic. So you do a diff, like a fuzzy grep kind of thing. Then you can start to filter per tokens. Then you match where is the likely sources. You have to guide the LLM because you provide the whole thing, it's not going to work. You provide likely sources where you have potentially problems. And you have a hint of database of things that you have been solving before in similar experience. And then you generate many patches. No, just not to fix one, you generate many, and you change the temperature, you try to play to the different variations. You compile and you have a React loop. Then you LEC is logical equivalent check, it's a formal equivalent tool pass, so you can formally prove that they are correct. And then if it gives you the answer, you know, I fixed the Chisel and it's correct and I don't have any problem. Now, if it doesn't give you an answer, then it's like, well, let me expand the search, let me try it. But at the end of the day, you may have ID bug. So how does it look when we try with different LLMs? So it depends on the results, but around 80% of the time, we're able to fix the bugs. We're still working on the type of bugs because the question is how do you add the bug? Many of the bugs, we change the Verilog, but then we, as humans, we don't even know how to fix the Chisel unless we blow up all that section and then suddenly we start to fix. So many of the bugs that we have added, we don't know how to fix them. So we have to see what is a fair comparison. But in 20% of the time, we say, no, sorry, we cannot fix it. The idea is that this is just an example. There are several other flows that we are building like that. Different flow, different pipeline, different idea, but it's the same. So what are the things we are having? We are working on open source, so you can check it, but because we are as active research is careful with the repository. You need to have on this is our second version because in the first version the students were doing a lot of benchmarking, consuming a lot of tokens. And things that we did is like we start to put incremental step parts, we enable caching, the steps are hermetic, help us to debugging. So we are working on a Docker integration. So there are a lot of little things on infrastructure that makes the thing more useful. And we have some other work in progress. If someone is interested in talk to me later. But we are trying to look at things like Verilog format, formatting Verilog, improving frequency. I have 2 students working on this. And the debugging loop. So you have a long verification and then debugging. One thing that is a challenge for our community is that the tools are very slow. So the incremental part is a challenge for us. Like as a reference for people who have not used synthesis tools, it's not uncommon, it takes 48 hours to compile. So to give you the GTS, which is the final result before the chip to get information. So it's a very slow flow. So in conclusion, we are working with hardware agents, exploring chip design, still deciding how to interface. I keep playing with different things. I keep using cloud code, like MCPs. I think the way is to go there, but we're still not convinced how to break down the pieces or not. I'm searching for collaboration and feedback, and if you want, send me an email. Thank you.
Thanks for the great talk. Yeah, our next speaker will be Risto Mikulalen, who's a professor at the UT Austin and the VP of AI research at the Cognizant AI Labs. Yeah.
Coming up. Okay, good. I'm going to talk about a particularly interesting technology that has come of age, especially in the context of AI agents. And this is work that I've been working on for decades, but most recently at the Cognizant AI Lab, which is right across the bay. So the motivation is that AI has actually matured from being a tool from imitating what people do to actually creating new things, to making decisions, becoming agents. And the question is then, how can we discover creative decision strategies? It doesn't come from gradient descent. I mean, that's imitation. And even reinforcement learning is really climbing the nearest hill. You have one individual, you try to incrementally improve it and get to the top of that hill. But there's limited amount of creativity that you can establish that way. This is a challenge that creative decision-making has faced. There may be many different strategies, and they be very different, and each one of them good in their own way. How do we find the good ones? The space is really huge, the space is really large dimensional, and it's deceptive. So the solution is population-based search, also known as evolutionary computation. The idea here is that you have a lot of individuals, the whole population, and it's spread out across the solution space. And it's not just a bunch of individual searches, they talk to each other. You have crossover that allows you to recombine two good solutions in order to find something that's even better. For instance, this one crossed over with that one might give you that peak. And surprisingly, this actually works really well. It scales up really well. In high-dimensional spaces, for instance, you can solve problems with 1 billion variables. Remember, humans can handle maybe 7 plus minus 2, Bayesian optimization maybe 10 dimensions. This is 1 billion variables. Kalyan Moydab on metal alloy manufacturing process showed that. Also very large search spaces where there are potentially 2 to the 70th solutions. That's like a multiplexer design problem of 70 bits. Homer Sarsad and Baba Kodjet showed that you can solve this using evolutionary search. Just to get you an idea what that number actually is. 2 to the 70th looks pretty compact. If you write it out as a decimal number, it takes light 95 years to go from the beginning of the number to the end of the number, 10-point font. So that's how many states there are. You can still find solutions because these searches talk. You find a partial solution, another one in this population maybe finds another part of the solution. You recombine them, and this way you can make progress and find solutions in a space that's large. All right, so, and for deceptive spaces, there are techniques that we've been working on in the evolution computation community for decades. So we can find surprising solutions that are also useful. Now, evolving neural networks is a special case of population-based search. There, our population consists of encodings of neural networks. Most likely lists or trees, something simple that then decodes to a neural net that we evaluate in the environment, and that becomes the fitness of each individual. And then we recombine them using crossover and maybe mutate them to find new kinds of DNA. This way we can discover solutions that are complex, creative, and customized to the task. So this is actually a visualization of a neural network that was discovered this way to control a robot in a competitive foraging and pursuit evasion task. So that's neuroevolution, applying evolution optimization to neural networks. Now, let's get to the agent strategies. So in the real world, what we would like to do is evolve a neural network that takes the current problem or the context as input and produces actions, the decision as output. And then we'd like to do it in such a manner that this neural network, this decision strategy, optimizes the outcomes. It might be, for instance, rehabilitation or treatment of a disease or marketing strategy or something like that, a decision strategy. Now, in the real world, it may be dangerous. I mean, you don't want to experiment different decision strategies on people, like what drugs to prescribe for a patient. You want to have a surrogate model of the world. And here we can use standard machine learning. We collected a big data set of decisions in the past for these situations, this action was performed, this was the outcome. We can train a model, just plain neural network, to imitate that data. That's the imitation. We know how to do that well. Once we have the surrogate, then we can evolve a neural network. Each time we have a candidate, we don't put it in the real world. We ask the surrogate model, how good is this decision strategy? And this way we can quickly evaluate millions of different decision strategies in order to find the good ones. So this is the extension to current AI. We are not just predicting what will happen, which we already know how to do, but we also figure out what we should do about it. That's the new AI. All right, so a couple of examples of that. First, designing websites so that we have optimal number of conversions. You go to this site and you're really compelled to press this button, find my program. That's a conversion. And this is a real-world application. It actually is running in the world. This was designing the widget here, the sign-up widget for this website that advertises educational programs. And it was actually evaluated in the real world while it was searching. And the professionals who designed these websites called this approach the ugly widget generator. Because to them, these widgets look ugly. They did not adhere to design principles, which are, for instance, common colors and all kinds of simple things like that. This is what the humans came up with. It's much more boring. This one is much more on your face and something that converts actually 45% better. So this is what is the running theme of this AI-based evolution and population-based search. It discovers solutions that humans miss, and they perform better. Another example is in cyber agriculture. This was a collaboration with MIT Media Lab, Caleb Harper. They have computer-controlled greenhouses, or they're actually containers where you control how much light goes in, what kind of light, temperature, nutrients, water, everything is computer controlled, and we don't really know what to do. Farmers know about their land, but not in general what you should do. So we evolved growth recipes, and actually here we're just displaying what kind of light should be shone on basil so that it grows better. And evolution discovered that basil doesn't need to sleep. You can have the lights on 24 hours and it will thrive. It becomes bigger and tastier. A huge surprise to the biologists. They thought that plants need to rest, like every one of us, but it turns out that they actually thrive in 24 hours. We would never have discovered that if evolution hadn't done it. Third example, this is something we built during the pandemic. A prediction model of how the cases will develop over the COVID-19 pandemic with certain restrictions that the government will impose. Should they close the schools, workplaces, stay-at-home requirements, mask, contact tracing, various actions that can be done, how they affect the pandemic. And again, we have a prescriptive, predictive model that allows us to predict based on past history and past restrictions, and then make optimal recommendations. How can we keep the pandemic in check while at the same time economic impact at the minimum? If you're interested, there's an interactive demo where you can explore how things could have happened in the past. And it discovered things that we did not know. It first focused on schools and workplaces and later predicted and would have mitigated the Delta surge if the government only had listened. But also it came up with creative solutions like different restrictions on weekdays and weekends, agility, quick changes, and focus on certain dimensions. All right, so how can we trust the solutions? That's a lot of technology that goes into predicting the confidence intervals around the predictions, explaining them with rule sets, and also, even if the LLM, we can evaluate how confident we are with the LLM output. Last point, multi-agent coordination. We can build systems, multi-agent systems using these technologies, and they will result in better abilities in terms of flexibility and reliability. And later on, Dan Fink will give a short talk and hopefully also a demo of the system in the 4:30 session. All right, to conclude, decision-making agents are the future of AI. Neuroevolution discovers decision strategies, including creative solutions, useful solutions that you don't already know. and techniques that exist to make them trustworthy. And this, in the long term, should make AI-driven society possible in science, engineering, business, healthcare, other aspects, education, and so on. So there are lots of resources available if you're interested in diving deeper. We have a textbook or actual monograph coming out in a couple of weeks in HTML later at MIT Press in a physical form on neuroevolution. There's also a tutorial which has a video and slides. And much of this software is available open source, including the uncertainty and neuroscience system as well as the decision making. So that's it. Thank you.
Thank you for the talk. Yeah, next time for the next talk, we'll welcome Man Indy on the stage, who's an assistant professor at the Northwestern University.
Hi, I'm very excited to be here to share our work, how to train agents by reinforcing reasoning. To train the agent, the goal is we want the agent to see, think, and act. So essentially, we try to use the reinforcement learning to see whether the agent can learn about how to reason in the environment. But if we check the current reinforcement learning algorithms, they have demonstrated the success in verifiable rewards, like trying to ask the model to do mathematical tasks or do the coding tasks. So these verifiable rewards can help the model to reason about which part is correct, which part is wrong. But if we move them to the real-world agency environment, it's much more challenging because the model is not just trying to learn from this single-turn reward, but actually they need to handle multi-turn feedback. And also, the state space explodes. So it's not just the finite problem set, but it actually can have multiple combinations of the states. Another thing is, it's not just the one single answer can help the model to decide whether it succeeds or not, but it's much more about multiple trajectories. Even if there's only the same goal, the model will try to predict the multiple trajectories to achieve it. So the environment part, we actually is not just trying to handle the environment that the model can fully observe, but a lot of cases, the model can only observe partially about the environment. All this actually makes the agent training much more challenging, and these challenges actually move us to this MDP, Markov decision process-based formulation for LM agents. So there are two parties in this environment. One is mainly about the agent. Another thing is we want the agent to interact with the environment. So the agent firstly will take the goal from human instruction, and then the agent will observe the current environment to get the status, and then given the state and goal, the model trying to predict the action which will be executed in the environment, so we can get the next environment and the reward. So this actually will formulate as an MDP sequence that we have the states changes and the actions as a sequence. And then finally, we get the reward about a trajectory. So we propose this star PO algorithm to try to capture this sequence-based learning, that's the model trying to learn from this state, thinking, action, reward-based sequence directly, rather than just trying to predict a single answer. And to learn this, we actually ask the model to observe the entire trajectory to trying to get a cumulated reward to decide whether the trajectory is good or not. So we firstly ask the model to do rollout, and at each turn, we want the model to check the initial status and the current status, so the model can get the full historical history, and then the model trying to do the prediction based on all the historical context to decide like what they should perform in the next. And this thinking process will be also included in the thinking tokens, and then the action will be dispatched to the environment so we can get the feedback from the environment. This will finish the rollout stage, and this rollout stage will enable us to get some cumulated reward for the entire trajectory. And then after the rollout stage, we will have the update stage. So we just leverage multiple trajectories to see whether the model can learn from these trajectories about like which trajectory is correct. Surprisingly, if we directly apply this kind of multi-turn based trajectory learning using the RL algorithm, the model is actually not working. For example, if we just check the very simple environment like the bandit machine environment, Sokoban environment, frozen lake environment, you can see like the success rate firstly rise a little bit and then it will drop dramatically to 0. It basically means like the model collapses. It's very surprising to us. So we are thinking like, why? What happens? If we look into this reasoning process, we actually identify the model will firstly, at the beginning of training, have a lot of diverse reasoning chains. And then when the model start to collapse, like at the turn 150, we can see like for several times, the model actually predicts exactly the same thinking tokens. So it basically means like there's some echo trap that the model just stuck into the locally optimized reasoning patterns, and they will not be able to really learn like from the trajectory which part of the trajectory is good and how they can make the good decision making. As a result, we try to monitor like how we can optimize this RL training process and trying to make sure the model can get converged, at least they can do a stable training. So we introduce these several monitor indicators like the reward variance and the like norm. When the norm gradient norm specs, the model will actually clap. So you can use this kind of monitor to decide whether the model get a good training or not. And then this, especially the output entropy, make us to realize like the model trying to identify the data that are really useful rather than using all the data. So compared to the left side to use all the data, we try to ask the model to select the data that are diverse and also informative. And this filtering strategy actually can make the model get much more stable training. And this contribute to the region training framework. And this kind of framework can make the model to learn to act. And the next thing is whether we can make the model to see. So the model will need to handle the multimodal states rather than the text states. For example, from the image on the left side, the model will need to verbalize them into either natural language or to the symbolic-based representation or some semi-structured representation like the JSON format. Essentially, this observation makes the model to change from the MDP process to the POM-DP process, so partially observable MDP. And we can see the MDP process is basically trying to learn the word model from the current status. If there's an action, how can you change to the next status? And POM-DP actually introduced this observation stage. So the model will try to firstly get the observation and then do the state estimation, and then they do the state changes. We try to have this word modeling loss into the model training. So firstly, we ask the model to predict the current status, and then we ask the model to predict what will happen given this action. So this is the next state prediction. And this contributes to the vision algorithm, and all the algorithms actually are well formulated and welcome to play with our region and vision framework. And we can see like through this kind of training, the model is able to observe the environment and trying to predict what they will achieve after this action. And then we want to see like what the model really learned to see and whether this seeing part can be improved also using the RL training, like this kind of agent training process. So for this problem, we ask the model to check different views of the environment and trying to imagine what is in the view. So it's kind of like trying to construct a mental model. Like given the first view, the agent realized there's a door, and from the second view, they realize there's a desk, and then they realize after, behind the back there's a window, and if they change the view, there's a sofa on the right. So at the end, the model can construct a mental model about how the physical space is constructed, and then they can try to reason about the entire environment. So this is the man cube environment. And then we ask the model to think in space by interacting with this environment and trying to get the feedback from the environment. And during the thinking, we ask the model to think over a map, like this cognitive map. And with this map and the reasoning process, this RL training algorithm can make the model have sufficient improvement. So we are thinking, basically, we want the model to not only to do reasoning, but also trying to learn better about how they can abstract this mental model from the environment. So this mental model is more like an interface. This interface is basically trying to connect the large language model with any environment. For example, we can build embodied agent interface, and we still build on top of this MDP framework. So we have this goal interpretation component and action sequencing component, sub-goal decomposition component, and also for the single step, we care about the transition modeling. And then we can construct a agent interface that contain all the important components so that they can connect the large language model with the agents. And if you are interested in this kind of direction, please feel free to check our tutorial about foundation models meet embodied agents. We use the MDP framework to connect all the related recent VLA and VLM and LM agent work. Thank you.
Yeah. For the next talk, Roy Herzig is here. Roy is an AI researcher at MIT, IBM Lab, and UC Berkeley. Go ahead.
Thank you. Hello everyone, I'm Roy. I'm a postdoc at UC Berkeley, advised by Professor Trevor Darrell, and my research focuses on developing structured physical intelligence models as part of broader efforts to advance multimodal foundational models. So first, let me explain what I mean by physical intelligence. Physical intelligence refers to an agent's ability to perceive, understand, and interact with the physical world in a flexible and intelligent way. It brings together key capabilities like perception, planning, interaction, manipulation, learning, all of which are key to truly versatile agents. But in fact, the foundations for developing physical intelligence models were laid by early computer vision pioneers who actually focused on enabling robots to perceive and interact with their environment. This is the classic textbook from the 80s, Robot Vision by Horn, and BKP beautifully captures the idea that perception and action go hand in hand. And although those concepts emerge early in the field, actually what happens is that the internet era shifted focus toward large-scale vision and language models fueled by large-scale data. And only now we are returning to the core principles of physical intelligence by applying computer vision insights back to robotics, enabling more capable and generalizable systems. Okay, so our main goal is to build a physical intelligence model that can perceive, understand, and interact with the real world across robots and environments. And of course, this is easier said than done, so how we can actually achieve it. So there has been actually substantial progress in this area over the past 1-2 years. Recent advancement in vision and language action models such as OpenVLA, RT1.2, they all aim to unify perception, planning, and reasoning within a single framework. Now, these architectures are, of course, impressive, but are we anywhere near done? And the answer is, of course, absolutely not. And as many of us in vision and robotics know, scale alone isn't enough. And a key reason scaling in physical intelligence is so challenging comes down to one key factor: data. You can see that at the bottom of the pyramid, there is abundant internet data, but it lacks the structured, grounded annotations that robotics requires. And to get more useful structured data, we can move up to simulation or even higher quality teleop at the top. But as we climb, the data gets much more expensive and harder to collect, which makes scaling incredibly difficult. So to overcome the data scarcity and annotation bottleneck that constrain robotic learning, my research explores how structured and compositional representations can be integrated into learning-based physical intelligence models. And this idea is at the heart of what I call structured physical intelligence, the core concept behind my work. Okay, so this led us to develop a new concept we call robotic particle-based representations. The core idea is to model the world as a set of visual traces and actions. Basically, a visual trace represents the spatio-temporal trajectory of a 3D or 4D point, while the action is its corresponding semantic label. And this approach gives us a unique combination. On the one hand, it offers a high-level semantic understanding of the action instructions. On the other hand, it captures really fine-grained, low-level motion representations. Here you can see a visualization of a particle-based representations, illustrating how they can capture both motion and corresponding action. You can see both 3D or 4D particle representations. And we use those actually to do many different stuff, whether it's dexterous manipulation or other tasks. And okay, so to summarize, what I hope you take from this talk is that if you're interested in the intersection of vision and robotics, then I believe the future lies in leveraging existing data, but combined with the proper inductive biases to enable powerful learning-based methods. And last but not least, stay tuned. We are doing exciting projects, and they're all on the way, including robotic reasoning, human-humanoid interactions, robotic pre-training, and many more. So happy to discuss this more if you want later. Thank you.
Yeah, this concludes our current session. So we'll be taking a break for 12 minutes. So we'll be back at 3:45 p.m. for the next session on AI safety, alignment, and security. Thanks, everyone.
might be space down over there next to that light.
Okay, great.
Yeah, your best option is probably going to be to plug up here.
Hi, everyone. Let's get started on the third session of the afternoon. So please get back to your seats. You're John, okay. Yeah. Great. So our first speaker is John Dickerson, who is the CEO of Mozilla AI. Yeah, John, here's your stage.
Let's do it. Yeah. At like 15 minutes, is that right? 15? I was told 15. 20, 15. Sure. Hi, folks. Cool. Great to meet everybody. I'm John, CEO of Mozilla AI. Prior to that, I was co-founder and chief scientist of Arthur AI, which is a New York-based observability company. Series B raised about $55 million and is still killing it on that front. Prior to that, was a tenured faculty member at the University of Maryland, leading a lab in market design and mechanism design. So a lot of overlap with multi-agent systems. And so today I'll cover some of the learnings from all three of those experiences, and I'll also cover some of what we're doing at Mozilla AI to support open source AI, and I mean more than just models when I say open source AI, I mean the entire open source stack. And I'd love to talk offline as well about, do we include hardware in that stack? I think there's a real case to be made for trying to be as open as possible, as far as down as you can go in hardware, right? Like open up for TSMC, open up for ASML even, things like that. But first, okay, so I have a little bit of time for this talk. I was in classic professor mode last night, finishing up these slides, and I would like to summarize this talk in one slide, which was experienced by me yesterday, using a closed source system to do very basic research for this deck. So I just asked, completely new chat, what are some statistics about open source AI's impact on the economy, which was flagged by one of the frontier models, closed models, as violating their usage policy. Chatted with some friends at Hugging Face about this, and they said, hey, pass in some context about one of the responses we have for the recent Trump EO. So I've downloaded this PDF, I added in there, and I asked the same question. What are some statistics about open source AI's impact on the economy? Still flagged as a usage policy issue. Started arguing and saying, hey, why'd you flag this? Why'd you flag this? And eventually, this, well, now it is named, I guess, closed source system told me, hey, I made a mistake. Would you like me to start answering your question? To which I said, yes, please do, and it immediately flagged itself as a usage policy violation. So if you remember nothing else from this talk, this is one reason why we might want to have open source AI. It's so you can ask basic questions about open source AI's impact on the economy. Womp. So in this talk, I'd like to say that choice matters. Open source means choice, right? There's no one model or system to rule them all. And we do see, obviously, leaderboard chasing and new models being dropped, new systems being dropped with new state-of-the-art claims and so on. And I'm not arguing against that at all. These are incredible systems. But especially with multi-agent systems rising into being a real thing going into production, we're going to have more complexity in systems, more nuance in systems, more constraints that are put on these systems by maybe being on edge, having to be on-prem, different guardrailing and so on, different preferences from organizations, which means that there is no one-size-fits-all solution here. Okay, so choice is going to matter to the end user, that end user being those of us in this room who are primarily machine learning engineers, those being traditional software engineers, and those being just tech-curious folks who have never coded in their life. All of these three types of, say, ICP or whatever for your product are going to need choice. And some of this is also risk mitigation, right? You want to avoid vendor lock-in, right? For example, one frontier lab might turn off access to a frontier model that's very good at coding because of a potential acquisition by another frontier lab. That sort of thing can be mitigated with choice. So the thesis for this talk is that open source AI needs to be as easy to use as closed source to be a true competitor. So it's not just about model parity. It's not just even about system parity. It just needs to be about ease of use, where I can recommend easily to my mom or whatever to go to an actual open source system that she finds valuable as easily as she could with a ChatGPT. Great. So I do want to have some call outs to the open source world out here, and these are taken from Wiz, which did a large survey of the hosted instances for AI models and AI tooling across their customer base. And I believe these were just from like public hosting, so they didn't do anything sketchy here, but it's a very unique enterprise-focused population that they surveyed. And we can just start going down. The percentages here are the percentages of hosted instances in their customer base